Welcome to the Dreyfus Symposium. I'm Dorothy Dinsmore from the Dreyfus Foundation. We have a full program today, as I'm sure you all know, so I thought I'd make just a few remarks about how we arrived here today. 14 years ago, the Dreyfus Foundation held a conference to focus on environmental chemistry. At the time, the foundation was noticing that the environment was receiving increasing attention from a wide range of sources. We believed that a central part of scientific research on the environment and its protection was going to be in chemistry. In 1996, we made the first awards in the program that we developed as a result of the conference. Since then, our postdoctoral program in environmental chemistry has made awards to almost 100 principal investigators, many of whom are with us today. With that experience, we thought this might be a good time to take a look at some of the most exciting current research. Today's speakers will cover different areas of the environmental chemistry spectrum. We expect their presentations will provide a strong picture of where the field is now. Before we turn it over to Francois Morel for the first session, I'd like to thank the New York Academy of Sciences for co-sponsoring this symposium with us and introduce Ellis Rubinstein, President of the Academy.
Thank you, Dorothy, and welcome to everybody. I want to make a particular point of thanking the Dreyfus Foundation for partnering with us on this event and bringing such a fantastic group of some old friends and lots of new friends to our space. I think you'll enjoy the space as the day goes by, and I'm going to make a couple of remarks, but I particularly want to thank Dorothy and Mark Cardillo and Jerry Brandenstein for organizing this event here, and we look forward to, I think that the work that the Dreyfus Foundation is doing is really extremely important, wonderful work. We, as you're going to hear in a second, believe in cross-disciplinary linkages and bridges. That's what we've been doing for almost 200 years, and the best of our times we've done it really well, and some periods we've done it less well. But we're really in the middle of that now, and we're very much in the middle of your area of climate change and green science and many other important projects, urban sustainability, that would probably be of interest to you. I guess I'm just going to take 2 minutes at the invitation of the Dreyfus team to tell people that really don't focus on us, that we're unique in the sense that we're the only, since 1817, academy that's not really an honorary academy, as you probably know. Anybody can join. So aside from the fellows who have to be elected, we end up with 25,000 members right now in 140 countries. We were also the only local academy that from very early days was an international academy, and Darwin and Pasteur were good examples that were joining it. So if you go back to the 19th century, we were founded in 1817, by the way, 2 blocks away. And if you're taking a little lunch break, you can look at that lattice, which you probably didn't pay a lot of attention to, and you can see on the lattice that there are different eras of New York City, and you can see where we started 2 blocks away over here, and then you can follow our path heading uptown before we came back to the future. So, since the beginning, we had this unusual role of bridging people, thanks to our doctors who were part of physicians and surgeons before it was the Columbia Medical School, who didn't like an elitist model, and they really wanted it to be kind of a club, and even a museum in the early days. What we have done best has been a convener and a disseminator. The Annals is the longest continuously published scientific series. It's a book series in the United States. And the only thing I'd really like to highlight in taking, so I don't take time from your meeting, is that since I was dragged here by Torsten Wiesel from Science, and very happily in the end to come and turn the place around, because it was kind of languishing, and which is why many of you may not really have focused on it for a while. These last 6 years have been a very interesting rocket ride to change, and what we did was we got science back into the core of the place instead of policy, where we were kind of floating into the space that I think Ralph Cicerone does a lot better job of down at the National Academy. And what we're doing is we're running 80 or 90 meetings a year, increasingly all over the world. And the focus for us is to bridge communities that don't meet each other in the hottest areas. We started in the life sciences, and thanks to Karen Pavesi, who I'd like you all to meet during the day, who's maybe is right back in the back there, who joined us from GE and Senator Lieberman's office and has an interesting background. We're really bridging in the physical sciences now in really exciting ways. And the one thing I'll just leave as a concept for you is that because we were able to organize the hottest scientists in New York City so that we finally started to get a synergy amongst our competing institutions that usually behave like it's a zero-sum game instead of actually working together, running 50 or so seminars in super hot fields where program committees come from Yale, Princeton, Cold Spring Harbor, Columbia, NYU, and so forth. And then disseminate this out with very unusual dissemination. And if you haven't seen it, if you go to our website and look for e-briefings, you'll see the concept where you can get very quick looks at what's going on at an event that you missed and only go as deeply as you want to, but you can go all the way down to the slides and so forth. Because of that, people have started inviting us everywhere to come and help them bridge their institutions that also don't work together. So in London, we did a Frontiers of Brain Imaging event in December that was where we were invited by King's Imperial and UCL to get them to work together for the first time in a conference. And now we've been asked to be officially partners with their Global Medical Excellence Cluster, which includes now Cambridge and Oxford, so that they will actually hold events every year, and we're going to do another one in January. Same thing in Beijing, where we're doing one to get Beida and Tsinghua and all of the institutions there to work together. Same thing in Shanghai, and it's beginning to happen everywhere. A fantastic event we did, and that many of you would have been interested in Mexico City with the mayor, called Science and Innovation Week, where we addressed issues that are crucial to the future of Mexico City, like S&T for urban development, green tech and green energy, and bioscience, so that they could think about how to become a knowledge-based economy instead of a manufacturing-based economy. And the audience was 300 of their leaders from the heads of the universities, the heads of the companies, the heads of government, and the financial leaders and billionaires. So that's what, in a nutshell, Academy is now standing for, and I won't take more time to tell you about it, except to say that this is like a core example of what we believe in, which is where you come together and address issues that become, as Francois Morel will be standing for, I see his lab in bio-inorganic sciences, a bridging of all different disciplines, but also related to societal problems. And if we can help you in the future, any of you, we'd be delighted. Please don't hesitate to email me. And please come and visit us. We're doing lots of events. And please get involved in our events when we're doing them all over the world. So thank you again for this. And then with that, let me introduce the great Princeton geoscientist, Francois Morel. He's going to run your show. Thank you.
Well, he's right. I'm Francois Morel. And you can hear from my accent, I'm from New Jersey. I have two jobs this morning. The first one is to introduce the speakers. And some of you got the biographies and so forth, so it's a very easy job, really. I'll do that very briefly. I won't tell you that they need no introduction. I won't give you terrible stories about them. Just say very brief things. My second job is actually to make sure that we're on time. And in the tradition of Camille and Henry Dreyfus, that means with Swiss punctuality. And so that may be the most difficult job that I have. Although we do have a little bit of extra time for Jim, so we're happy. So I shall introduce our first speaker. Our first speaker is James Anderson. Jim is a Philip S. Well Professor of Atmospheric Chemistry at Harvard University, and his talk is Strategic Choices for Global Energy, Constraints from Feedbacks in the Climate System. Jim.
Let's see, Rudy, were you going to switch mics? I'll just use this one. This is fine. Francois, I expected your sense of humor to extend over to the introduction, and I had a counterpoint. So perhaps I'll just go ahead and execute the counterpoint. uncross-examined, but thank you very much for this invitation. And I should point out that both Mark Cardillo and Dorothy Dinsmore have worked very hard on creating what is really an unusual mix of science and an intersection with the public. And today, this morning, I'm going to develop a case that sets the imperative for the timeline that connects energy and climate. And of course, we'll hear a lot about energy this morning. And I want to cast this discussion in terms of the feedbacks within the structure of the global climate system. And as part of this argument, I'm going to build the case that stating this as global warming is a very ineffective way of articulating what the case is, both because it does not recognize the key feedbacks that set the time scale for public policy action, but it also trivializes the discussion to small changes in temperature in your backyard, which really doesn't capture what is occurring within the structure of the system. And of course, you can look directly at the way in which the population is shifting, for example, from New England to the southern part of the United States, to immediately recognize that most people would prefer having their backyard a little bit warmer. And so in developing this feedback structure, I wish to create a new way of viewing this problem. And to do that, I want to step back to the very early part of the emergence of human beings, the modern human beings, which started 160,000 years ago. And at this juncture, what I'm going to do is present time in a rather idiosyncratic system of units that expands and contracts depending on the particular point, against the vertical axis, which is the population of the globe in billions of people, 2, 4, 6, 8, 10. And it took virtually to the Roman period, from 160,000 years ago, to reach a world population of 250 million. And the point here is to develop an intuition about what is occurring now and how that departs from essentially the experience of anyone in this room. It's very easy to remember when the world population hit 1 billion, 1776 is a very close measure of that. 1945, Second World War, world population hit just a little over 2 billion. Notice that it virtually didn't grow until the Renaissance, following the Roman period. But and it's 7,000 generations from 160,000 years ago to the present. But within one human lifetime, it's jumping from 2 billion to somewhere between 9 and 11 billion. And it's coming to grips with that fact and the rate at which this is happening that's so crucial. Now, when we calculate the power required to sustain this global endeavor, we see some very important things emerging. 1945, 1 terawatt is 10 to the 12 watts, represented about half a terawatt per billion people. By 2005, our population now is 6.5. We're running about 2 terawatts per billion people. And when we reach 30 to 40 terawatts by the middle part of this century, we'll be running about 4 terawatts per individual. And this is based on a calculation that Nate Lewis and Dan Nocera did so simply and elegantly in a PNAS calculation. And I'm going to talk about that because this is basically what you have to carry around in the back of an envelope with you. You multiply population times per capita income. Now that's 6.5 billion times about $5,000 per person as an average income, and then multiply that by the energy demand per dollar of output, you get the global energy demand. And I'm going to talk about this in units of joules because, in fact, that's the respected unit of energy. And I'm going to introduce the zeta joule, which is 10 to the 21 joules. And as part of some congressional testimony I did, I said, well, I want to talk about energy in zetajoules because you can track the flow of energy through the economic system and through the global system with the same set of units. And they said, no. Zetajoules will not fly in a congressional hearing. So I said, well, what about billion, trillion? They said, oh, that's fine. Military budget's $1 trillion, petroleum purchases 600 billion a year. That's fine. You can use billion, trillion. So I did. But it's the same unit. It's zetajoule and a billion, trillion. So you can choose your poison. So when we do this calculation, this is 0.4 zetajoules of energy per year driving this human endeavor. And when we calculate it for the middle part of the century, that's a population of 9 billion. The per capita income will be about $8,000 per person. And the energy demand per dollar of output will change perhaps somewhat, but to first order, this is a very reasonable calculation. Now, by the way, the energy demand per dollar of output is about 1.5 10 to the 7 joules per dollar. And if you take a liter of gasoline, that's about 3 10 to the 7. So it takes about half a liter of gasoline to produce each dollar of GDP worldwide. So 0.4 zetajoules to 1 zetajoule by the middle part of the century. What does that mean? Well, of course, it's just a number, but when you translate it into what that means for primary energy generation, we just take the current distribution, which about 80% of that primary energy comes from fossil fuels. And so we can do a demonstrative calculation without choosing sides about how this should be done by just assuming that we're going to generate that 0.6 zetajoules by the middle part of the century from coal. And to do that requires 1,500 megawatt coal burning power plants to be constructed each year. That's 2.5 500 megawatt coal burning power plants every day between now and 2050. Now we can do it with nuclear, with 2 gigawatt power plants. We have to build one of those every day and a half. So when you hear the political discourse back and forth about changing the energy structure of the United States by building 20 nuclear power plants, you can immediately see the trivial nature of that particular case. And so the scale of this problem and the rate at which it's changing is fundamental to our understanding of it. But it's also fundamental to understanding the way the climate is forced by the release of carbon dioxide, because the great monsters of energy consumption, the United States and China, are endowed with an amount of coal that we will never burn ourselves through. And so in the development of life, of course, bacterial reactions set in place all of what we now mine in terms of fossil fuels. At the same time, human intelligence was emerging and developing along a parallel track. The question is, has human intelligence reached the point to realize that we will conflagrate the planet if we consume everything that the bacteria produced for us? So that's the issue that we turn to, and of course, in grappling with the quantitative aspect of this, the Intergovernmental Panel on Climate Change has published this report that combines not only the science but also the mitigation public policy concepts. And this was released in July of 2007. It got the Nobel Prize the fall of 2007 with Al Gore. But let's look at what's inside this. One of the most important points is the carbon emission in gigatons of carbon per year against the time base, 1990 to 2010 in this case. And there are a whole series of scenarios, high carbon burn rates going down to technological intervention that brings down the release of carbon dioxide. But what actually happened was what's so important, and out of PNAS, the Proceedings of the National Academy of Sciences. This is Ralph's journal. Well, we're speaking globally here. Anyway, this is a very important paper. It articulated the actual release of carbon into the atmosphere, and in November of 2007, we'll see the next round of this in about 3 weeks, it began to track what was actually occurring. And in 2005 and 2006, the slope of the release of carbon into the atmosphere was dramatically above the upper limit of the IPCC report. So the forcing on the system is in no way commensurate with what has been going on over the past 20 or 30 years. It's exploding very rapidly, and China is building not 2.5 coal-burning power plants a day, but 2.5 a week at this juncture, all open flue. And that, along with the development of India, Russia, Brazil, and of course the U.S. and Western Europe, is driving both the absolute value and the slope well above the upper limit of the IPCC report. And the ink is just barely dry on this report. So this captures the time rate of change of what's going on. So this is a primary forcing agent on the climate. Now the key thing is in tracking energy through the economic system and through the climate system to recognize the magnitude of the natural system. So coming in from the sun, we have 5,500 of these zetajoules. This actually came from that congressional testimony where I had to switch to billion, trillion. So we get 5,500 of these zetajoules. We reflect about 1,500 back in the visible. So when you see a beautiful picture of the Earth, that's about a third of the incoming shortwave radiation from the sun that's reflected back. The other 4,000 go into the climate system, and they are absorbed in the atmosphere, in the oceans, and so on. And then the system radiates back at steady state the same number of joules that it receives from the sun. It must. As it warms up, the emissivity and the electromagnetic radiation produced in the black body emission to outer space balances that incoming amount. But it's very interesting to note what's going on inside the climate system. There are about 6,000 zetajoules circulating inside the system. That's a very important number. Both the 4,000 received and given off are very important, and the 6,000 that are cycling. Now, it's a little counterintuitive to think that there's more energy cycling inside the Earth atmosphere system than is received, but of course this is very similar to why we wear clothes, and it's one reason we wear clothes. And that is that your body radiates in the infrared into the clothes, and they radiate back into you. If you actually had to exist in a very cold environment, you'd have to eat 20,000 calories a day to maintain the emission of the human body at body temperature. So it's not surprising, but it's a very important fact, because these 6,000 zetajoules now represent the amount by which a very small change can have a huge impact, and the feedbacks associated with that powerful drive are the story we want to talk about. So this very large flow of energy and cycles and the small changes in the escaping infrared amplify that, and amplify it with huge leverage. So let's look at what's happened. We want to look at the way in which thermal energy or heat is flowing into these systems as a result of increasing carbon dioxide and the response of water vapor to that increase. So about 200 zetajoules have gone into the oceans in the past 50 years, about 20 into the ice systems, about 9 into the continents, 7 into the atmosphere. So every major reservoir in the climate system is receiving heat inexorably. And this is very crucial. It gets back to the simplicity of the first law of thermodynamics, that heat is flowing into the system, and it poses the question, how do you extract heat back out after it's entered the system? So let's look at the impact. These are microwave data obtained from space starting in January of 2007. Looking down, this is the Arctic ice cap. This is Greenland sitting over here. So we're now into March and April, and you can see as we get into May and June, the Arctic ice cap is receding over the Arctic. This is August, early September, coming up to the middle of September. This is the 16th of September of 2007. Now, at any time in the past 2 million years, this ice is locked in all the way around the periphery. This is the Northwest Passage. This is a famous opening that was searched for over history. So if we look at this in terms of the time base, starting back in 1980, we had about 7 million square kilometers of ice It dropped precipitously in 2007. Have very detailed information from nuclear submarines in the 1950s where this ice cap was 3.5 meters thick and it remained locked in year-round. Now, the thickness of this ice is less than a meter. And if we look at 2008, and you can go on a very interesting website called Cryosphere Today that tracks this every day, and you'll notice 2008 is as bad as 2007. Why is this? Well, the question, of course, comes if we remove half of the Arctic ice cap in 30 years, what are the prospects for returning to a stable condition? And the prospects are fairly draconian. And if we had this discussion 5 years ago, we would have been arguing about the ice cap lasting until the end of the century. If we'd had this discussion 2.5 years ago, captured in this prediction here by the National Center for Atmospheric Research, we would have been looking at a debate over whether it would last until 2050. We now know it will be gone, the summer ice will be gone in 2015. And this is a profoundly important point because the feedbacks, which are the central point I'm trying to make, are so potent that once you begin to lose this thermal shield, the system runs away, because when you open the ocean up, it provides the inflow of warm water from low latitudes, and I'll show you exactly what that implies for the Greenland case. Also, there's a tremendous amount of heat carried by atmospheric transport that moves over either open tundra, forests, and open water, or over ice. And if it's moving over exposed areas, it transmits a huge amount of heat into this Arctic system. The next point is that, of course, any material emits energy at a rate determined by the fourth power of the temperature. So we're now replacing what used to be an ice surface running at minus 50 Celsius to a surface that's now running 8 to 9 Celsius. And you take that difference to the fourth power, and the infrared flux coming up from the surface is then trapped and sent back down. It's a potent feedback. And then, of course, there's the reflectivity. The dark ocean and open areas absorb a vastly larger amount of sunlight than do the reflective white surfaces. So these feedbacks constitute an imbalance that is driving the time rate of change of the entire Arctic system. And of course, we don't care too much about the floating ice for sea level height, but we care a great deal about Greenland. The spine of Greenland is about 3,000 meters thick, and there's enough ice to raise sea level by 7 meters. And the Arctic ice cap is really the thermal shield that protects Greenland. The other point is that when we begin to melt these northern regions, they contain between 900 and 1,000 gigatons of carbon in the form of methane and clathrates and CO2 in the permafrost. Now that's 1,000 gigatons compared to our release rate from all fossil fuel burning of 8.5 gigatons per year. If this starts to go, and we believe it's already beginning, the release of this carbon is a feedback that's sufficiently potent to keep any of us up at night. And I think, Nate, you were the first person to start listing what keeps you up at night. And I think part of today is to delineate all of those components. This is a potent feedback. And we already see massive meltdowns in the lake systems in northern Siberia and northern Alaska. Methane is pouring out of those lakes so fast that it forms a fountain in the middle of a lot of these ponds. And the isotopic data from that carbon release says very clearly that methane is 40,000 years old. So we're not talking about small variations and fluctuations over the past 50 years. This is deep into the last ice age. Okay, so the axiom then that we recognize here is that it's the net flow of heat and not globally average temperatures that guide the course of the human endeavor. And I've always tried to make the point that looking at average surface temperature of the Earth is the most degenerate variable that can possibly be discussed, because not only does it wash out what's actually occurring because of the heat capacity of the ocean, it deflects attention from the subsystems that are actually responding in a far more rapid way than the average temperatures. Now, corollary to this comes back to this question of feedbacks controlling the flow of heat that set the stage for irreversibility. So the point is, at what juncture do we pass that point of irreversibility? That's the issue to focus on. Now, I just pulled this up off the web from this Cryosphere Today that plots the ice area anomaly in million square kilometers along the vertical axis against years from 1978 to 2009. And here's the bottom out in 2007. You can see in 2008 we're diving down. We probably won't quite reach that, but the pattern is very clear. And the loss of permanent ice this last year has been remarkably large, and that's irreversible. So let's look back for a moment in the paleo record. Let's go back to the Eocene. This is a rendering of the Arctic Ocean. And in the Eocene, there was almost no temperature difference between the equator and the polar regions. Palm trees, alligators, various tropical plants and animals were roaming the edge of the Arctic, and there's no question about this. This is based on fossil evidence. And what was it about the climate structure 50 million years ago? Well, we know we had 900 to 1,000 parts per million of carbon dioxide. We know the sea level height was 230 feet above where it is today. There was no ice in either hemisphere. And as time marched from 40 million years ago in the Eocene toward the present, this beautiful thermostat that's created by the carbonate silicate reactivity at the Earth's surface drew down the carbon dioxide out of the atmosphere. And as that occurred, the temperature followed suit. Now, we know 4 or 5 million years ago there was no ice in the northern hemisphere. And when you draw carbon dioxide down to about 250 parts per million, the subtleties and the orbital parameters of the Earth take over, and at very low carbon dioxide, you go into and out of glacial periods. But as soon as you begin to drive the carbon dioxide level up in the range of 350 parts per million, that trapping swamps the subtleties of the orbital parameters of the Earth. Now, we're at 390. In steady state, there's no way that ice exists in the northern hemisphere above 390. And when you look at the slope of that carbon release, you realize that we're headed very rapidly toward 600, 700, 800 parts per million. So if we look back again at this IPCC forecast, let's look at their ice forecast. This starts back in 1980 to 2000. This is July, August, and September. This is the ice that's locked into the Arctic. This is the percentage of total ice based on that initial condition. Now, of course, that happens to be true because it initialized the calculation. So at this juncture, the forecast hasn't told us anything. But let's look at what the official IPCC forecast is for at the end of the century. Its forecast is considerably more ice than is there today at the end of the summer. So this is the primitive state of ice forecasts, and that extends to Greenland. Now, Greenland, of course, is the issue. This is the meltwater in 1992 along this spine that's again 3,000 meters thick. And when you look at the cross-section of Greenland, it looks very much like a medieval cathedral. It's very, very deep. It comes out and then it drops off very quickly at the side, and it's supported by the flying buttresses that constitute the ice structure along the edge of that. And, of course, we now know that it's not a monolithic block of ice. It's melting, and it's delivering warm water all the way down to the base, which lubricates the base of those flying buttresses. And it's not a question of melting. It's a question of collapse. And so I was there just 2 weeks ago investigating the icebergs coming out of the Ilulissat fjord on a project where we're using ice-penetrating radar to dissect the structure of that Greenland glacial system. We're using robotic aircraft for this. That's not an aircraft, that's a seagull. And there are two types of these in Greenland. They're dead and or hardy. Those are the two varieties of seagulls that we found. But these icebergs are about 300 feet high. Of course, only an eighth of them are above water. They're about a quarter of a mile wide, and they're pouring out of this Ilulissat fjord. And this is accelerated by a factor of 5 since 1998. And part of this trip, we visited the universities and the institutes, and what they had discovered was that warm water coming up from the northern edge of the Gulf Stream moved up the coast, the west coast of Greenland, and into these fjords, and raised the water temperature inside the fjords by just 2.5 Celsius. And that was enough to melt the base and lubricate the flow. So what's happening is the vertical force from the mass is pushing downward, and the loss of friction between the bedrock and the ice allows this to flow out like a river, and that's what's generated this. So it's a very, very powerful component. Now, we went through this in a small fishing boat. These icebergs are spellbinding. I mean, this again this extends up 300 feet or so, and these are pouring out and they're breaking up. This is actually the glacier that sent the iceberg out that sunk the Titanic. And I can tell you, there's no question that it would sink anything that ran into it. There's also meltwater at the surface, and we want to talk a little bit about what happens with increasing sea level, because unlike global warming, nobody gains from increase in sea level height. So let's pick on the center of Cambridge, just for an example. This is a 400-year-old university sitting here that has property laid out in this yellow part, and they're about to drop $10 billion on a new campus just on the south side of the Charles. And if we add 1 meter of sea level rise out of the 7 meters contained in the Greenland ice cap, it looks like this. If we add 3 meters, it looks like this. Now, the debate is about how long the Greenland the glacial system will remain intact after the Arctic ice disappears. So now all of a sudden we've got a debate about whether we've got 60 or 160 years after the departure of the Arctic ice cap. Well, for an enlightened 400-year-old institution, 200 years is nothing. Now, there's some humor associated with this if you look at this, because MIT goes under before Harvard goes under. So, Dan, you might consider switching. We can put 5 meters in. This is still just 2/3 of Greenland, and now this looks like a Revolutionary War map where George Washington was here for the summer of 1776, and the Brits were down here, and Dorchester Heights was here, and you've seen these maps. This is a fundamental problem, and the university is now just coming to grips with Plan B. Let's look at the Gulf Coast. Here's 3 meters. With 3 meters, the southern third of Florida goes underwater, and most of the Gulf Coast. Let's pick on New York. Here is New Jersey, and I don't know where Princeton is, but here's, yeah, you better go home and check. But here's 3 meters on Manhattan and the Jersey coast. So the point is that this is a profoundly important problem, and if you look at the capitals of all countries across the world, you see the same pattern. This is an issue that's profoundly serious. So let's pose a couple of questions and end up here. How do we know that we have regained control of this climate system? Well, heat is flowing into this system. The only way we would know is if heat were flowing out, and that ice cap reforming. Now, once we lose the ice cap, it's extremely difficult to turn the system around. And so we would only have hard evidence that we could regain control over those feedbacks if we in fact saw ice reforming. So there's a simple question, but what means do we have at our disposal to remove heat on this scale? And by the way, the amount of thermal energy, the amount of heat required to melt the Arctic ice cap at the rate it is melting is 1/10 of a zeta-joule per year out of the 6,000 cycling in the climate system. And 1/10 of a zeta-joule per year is tiny compared to the global budget, but of course it's a fairly large fraction of the global production of energy by humans, which is 0.4 zetajoules. So alternatively, we can pose the question, is there any known strategy for extracting heat from these global reservoirs on the scale of a zetajoule? And the answer to that is that there's no rational strategy in place to do that. Now, you can block incoming solar radiation. 340 watts per square meter come in. If you remove 1% of that, that's 3.4 watts per square meter. That's comparable to the rate of forcing by carbon dioxide in the system over about 15 years. So we can do it. The question, of course, is by what mechanism? And there have been a number of suggestions made. Paul Crutzen came out and suggested that we put aerosols into the lower stratosphere. Now, for many of us who've worked on the ozone problem, including Paul, of course, that's the worst thing you could possibly do. And he was criticized roundly, and I think that was unfair criticism because people who criticize this simply haven't looked at the alternatives, and they haven't looked at the numbers involved in this. But if we're going to do such a thing, we have to do it with a very dry stratosphere, which we currently have, because if any water starts to leak into that system, you lose the ability to gently reflect shortwave radiation. Of course, this isn't a long-term solution because the acidification of the oceans presents another problem, slightly longer in time scale. Time scales I'm talking about here are immediate because I contend we've actually passed the point of irreversibility. So when we look then at the way in which we can control this, the only option available to us really on the short time scale is to control the incoming forcing from the sun. We can also put reflective material in at what's called L1, which is a gravitationally stable point between the sun and the earth, but there's a real problem about reversibility with that. Aerosols in the lower stratosphere are reversible. We know that because volcanoes run that experiment for us, and there's about a year and a half lifetime for those aerosols, so that's a possibility. Now, I'm not suggesting this. I'm simply saying that people who violently object to engineering the climate don't realize that we're already engineering the climate. It's a question of how intelligently we do it. Now, I just want to end up, because we're going to talk a lot about energy today and a lot about options. And, of course, the fundamental point here is that we receive 4,000 zetajoules of energy per year from the sun, and we need to generate 0.4 zetajoules per year. So there's a 10,000 time ratio between what we receive each day and what we consume. And this takes many forms. Of course, we're going to talk about photovoltaics in a very important way today. But let's just look at solar thermal and wind power for a moment. This is not a political map. This is a map that demonstrates the amount of energy available from wind power potential. And if we look at the red states, just the red states, we recognize that we can generate 5 times the total energy consumption of the United States by wind power alone in that zone. And if we look at solar thermal, which of course is focused more down in this region, we can generate another factor of 5. So we can generate 10 times the total demand of the United States in primary energy from those two alone. Now, those are technologically available to us today. And the United States is incredibly endowed with the ability to generate primary energy from non-fossil fuel capability. If you try to do this in Europe, you have to go offshore. You have a lot of issues related to real estate, but not in the United States. I mean, wind power can go in at the same time you're growing crops. We're dumping 140 billion a year into the farm program. There's no reason why you can't raise whatever crops you need below these windmills. Now, solar thermal, of course, requires area. It requires area out in New Mexico, Arizona, and so on. But I think Nate's going to show us a postage stamp of what photovoltaics. You're not? Oh. Of course, I always use that slide in freshman science because it's so demonstrative. Photovoltaics occupy a little bit more than the panhandle of Oklahoma. And my favorite thing is to take a class of 350 and ask how many grew up in that postage stamp. Very rarely does a hand go up. I ask how many people have actually been through that area, and maybe 5%. This is an incredibly valuable aspect that the United States has. And this is by a paper that Mike McElroy did. This is very accurate because he actually calculated the wind fields globally and calculated the gradient in those wind fields from the ground up. This is for a 2.5 megawatt wind generating power plants or wind turbines. And it's also checked against observational data. So these numbers are very accurate, and this paper is now going in for publication. So I want to finish then by pointing out, again, our title was Strategic Choices for Global Energy Constraints from Feedbacks, and just emphasize that the timescale for corrective action, that is decarbonization, is not set by an increase in global mean temperature. It's set by these feedbacks within elements and subsystems of the climate. And it's the irreversibility in these critical components that sets both the imperative and the timescale. The second point, of course, is the United States is endowed with this remarkable natural resource. And finally, when you look at all of these fundamental considerations of national security, economic vitality, technology leadership, fiscal policy, foreign policy, they're all closely coupled to the same public policy structure and decisions associated with that coupling between energy and climate. And with that, I'll end, and thank you very much. Jeff.
One thing I'm sure you've heard, I certainly have on various occasions, refers to one of the slides you showed, that, well, what we've actually done is taken precautions against the next ice age. I know there are a lot of things to say that I would be interested to hear how you respond to that.
Yes, I respond the same way that I do with people who are delighted that the Northwest Passage allows the transport of oil carriers more easily across the globe, and that is that the profound and serious nature of sea level rise, which is now inexorable, is a destabilization of all societies to the level that no one could possibly suggest that it's a good thing. We also have very strong paleo evidence to say that above 350 parts per million, we're now at 390. No ice can survive in the northern hemisphere. So the idea of protecting ourselves against the next ice age, I find a preposterous argument.
Somehow, if you somehow admit that CO2 is a driver in climate change, then we've got the burner up too high. Right? You can't say, well, we just have engineered it right to avoid an ice age. We're warming at a much faster rate than that decline in 10,000 years would supposed to give us. And so you've used this twisted argument to try to say somehow it really is causal, but it's not really bad because we've got it just right, which sounds tricky. I've got two questions just for my personal clarification. One is, as I understood it, you seem to imply that the Milankovitch cycle forcing was the was in fact mostly responsible for the observed temperature swings. And my understanding is that, in fact, the Milankovitch cycle solar forcing is only responsible for a fraction, perhaps a small fraction of the observed temperature swings. And in fact, it's the CO2 that amplifies that we see there. Is that correct or not?
No, it's a causal process associated with these feedbacks. So
Right.
Milankovitch
Exactly.
is the trigger.
Exactly.
Very similar to carbon dioxide triggering the response of water vapor.
Perfect.
It's the feedbacks that
Right.
amplify and
Exactly.
drive it.
So
Yeah.
it's not
Yeah.
that the solar forcing accounts for that swing. It's just the causal of it triggers it, and then the climate system is in fact responding to drive those swings.
That's right. It's the tail of
Good.
wagging the dog.
Perfect.
Yes.
So the second question then is, if you look back in history, you looked at the Eocene. I often use the Permian as, I think, a better example because, in fact, there was a rapid change in CO2 in the Permian that did trigger a massive isotopically light release of carbon. And in that case, when CO2 levels went up to a few thousand ppm, I think that it wasn't true that the Arctic looked like the picture you said. In fact, it was true that the fossil record shows us that was one of the great extinctions, and 90% of the species on Earth couldn't adapt to that rapid climate change and went extinct. So the situation of that resembles more closely what the human forcing time constant is doing.
Yeah.
Is that correct also?
That's right. That's right. I mean, I have choice of a number of examples.
It's bleaker than what you said.
I happen to have some graphics related to the Eocene with wildebeests running around the edge of the ocean, and so I tend to choose that. But that's correct. Incidentally, it takes a few million years to build up the organic infrastructure that then melts down and releases methane, and so that methane release triggers the introduction of water vapor when methane is oxidized in the stratosphere. And what that does is it puts ice crystals into high latitudes, which absorb infrared, flattens the temperature gradient, and takes the driving force out of the overturning rate that controls the temperature of the tropopause in the tropics. So you can trigger a complete change in the dynamics of the large-scale structure of the atmosphere, which then releases massive amounts of water vapor into the stratosphere, and that remains permanently until you've drawn CO2 down so far that you then cool the system off.
From Caltech. Questioners should identify themselves. Be good. Please.
So we had a question back. Yeah, Dudley, yes.
Jim, would you advocate when talking to the wider public that we speak of global melting rather than global warming? I say this really as a surrogate for Hal Johnston. As Jim well knows, I think you do this in your freshman chemistry course. You can invite people, as Hal has done, to take 2 glasses of water, one with ice, one without, put light bulb above each, thermometer in, and of course you see the temperature go up steadily in the glass with only water. Doesn't change at all until all the ice melts in the other. I happened to have a chance to talk to some reporter group at Kennedy School about this, and they loved that example. It's like Feynman's famous demonstration with the O-ring.
Yeah.
I only mention this because I think it probably is a good way to get the key message across by speaking of global melting. Thank you.
Well, I think global melting is a far better descriptor. I think finding a way of describing this in 2 words is difficult. I think in any scientific venue, the feedbacks are the crucial term and the power of those feedbacks. But yes, as a front page headline, global melting certainly carries more imperative than global warming.
Paul Anastas, Yale University. Thank you for the talk. I want to come back to the map that you showed and completely agree about the wonderful potential for wind energy, for solar thermal energy. And when we look at that and we consider all of the changes that are expected as we go forward with the rise in CO2 levels, and we think about our climate models, some of our climate models deal with certain parameters very well. Other parameters, such as perhaps cloud cover, perhaps the placement of our wind resources might not be as well developed as they could be. So I guess the question comes, as we invest billions in infrastructure to take advantage of these particular wind and solar thermal resources that we have in the snapshot of today, how do we project whether that snapshot is going to be the same with all of the changes that we're expecting 50, 100 years?
Okay, a very good question. My reaction to that is Asia is actually presenting to us a perfect experiment in what happens in nitrate, sulfate, heavy metal organic release from the combustion of fossil fuels right up to the limit of human toxicity. We're sitting right at that cusp in Asia right now, and so we can study the evolution of chemical transformations from the molecular level through to the condensation nuclei, and we're going to hear about the important aerosol component here. And so I have focused here on carbon dioxide forcing because it is going up inexorably. We're talking about forcings of 10 watts per square meter, and the aerosol component is very important, both the direct from aerosol formation and indirect in cloud formation. But the carbon dioxide release is so rapid that forcing is going to take over, and we have a reasonable idea about cloud cover and about the impact that it has on the meteorological systems that move, for example, west to east in the United States. So we're so far from being under cloud control in the southern part of this map and we're so close to human toxicity levels for fossil fuel burning that's not going to change these forecasts in any significant way. It's also important to recognize that we're capturing a few parts in 10 to the 4 through the kinetic energy of wind as it's converted from solar power, and that's not going to change the fundamental dynamics of the lower troposphere. One more?
I was just going to augment that a little. That you can't move the wind field. There's no way. The cloud point is well taken. Changing the cloud field may be somewhat easier, but you're not going to change that map by what we're doing.
That comes from Neil Donahue, and that means it's true.
Thank you, Jim. Our next speaker is Kimberly Prather. She's professor of chemistry and biochemistry, University of California, San Diego. Her title is New Insights into the Role of Aerosols in Climate Change. Do you want to do this, perhaps? Because we lost you a little bit.
Where I'm going to put it. So I just clip it on this thing. I just stick it on there. Right. The pointer is. Can I just set this here, you think? This here. Gotta get this thing in there. Can't see it. Okay.
Okay, well, good morning, everyone, and it's a great honor to be here, and I'd like to thank Mark and the Dreyfus Foundation for the invitation to come and tell you a little bit about our research that we're doing, and I will be touching, Jim did a great intro for a lot of the things that I will be touching on as far as climate change. In particular, when Mark first invited me, he said, make this really basic. A lot of people in the audience won't even know what an aerosol is. There's a chance, so step back. So I'm going to do that. But then I was at the annual aerosol meeting was this week down in Florida, and there's a number of people here that are from that community. So I'm sort of trying to span the range from the very basic sort of background on aerosols all the way through to the impacts and some of the newer research we've been doing. So with that in mind, the research in my group at UC San Diego focuses on atmospheric aerosols. As people know, it's a major component of air pollution. It's been a relatively understudied component of air pollution until the last decade or so. Similarly, basically when you hear about air pollution, for years we heard about ozone. We worried about respiratory effects from ozone and pollutants in the atmosphere. It was only within, as I say, about the last decade or so that people started really drawing attention to aerosols. There's plots for the worldwide that show that as aerosols increase in the atmosphere, there are deleterious health effects that go far beyond just respiratory, but they go beyond respiratory issues, all the way, extending to premature death. And that's a hard one to sort of quantify, but basically aerosols are very, very effective transport mechanisms to get pollutants and toxins into very deep regions of our body that they just wouldn't get otherwise. And so that's kind of where I started. I started out looking at air pollution. I was very interested in sort of the aerosol component, which is the relatively messy side of air pollution, but a very important side of air pollution nonetheless. The examples we see every day, dust, soot, sea spray, bacteria, viruses, pollen, all of those qualify as aerosols. The environmental impacts, as I mentioned, human health is a major target, but also the climate aspect, which is what I'm going to focus on today. Visibility just tells us through there. When you see poor visibility, it's the aerosols that are doing it. Land and ocean fertilization, both from the good side as far as leading to ocean productivity, as well as land fertilization, but also some of the negative sides, such as acid rain and other things can happen as well. So today I'm going to kick off with just sort of a little bit of background on atmospheric aerosols, breaking them down into sort of the direct and indirect effect that Jim just alluded to. I will sort of finish up with talking about what our approach has been. When I came into doing this type of research, there was a pretty big gap. I came in from the chemistry side. I was trained as a fundamental physical chemist who studied gas phase reaction dynamics. And there was just a pretty big gap as far as our chemical understanding of what these aerosols were doing in the atmosphere. And so that I brought in sort of a different perspective of how important chemistry might be on this problem. To be honest, I've been shocked at how sort of there's been a certain resistance for a long time as far as how is the chemistry really important. We still have battles over whether we even need chemistry to explain what's happening in the atmosphere. So those are turning into less and less battles, but still they're there nonetheless. So the approach that we use in my group, is this guy working? Kind of. He's a little wimpy one. But anyway, the approach that we use in my group is a dual-pronged approach. Truthfully, when we started out developing the instruments that we developed, I planned on doing lab studies. I had no field experience. I didn't even know what a field study was. But then in the end, once we had the instrument working, we decided to sort of sniff the outside air and see what we saw. Early funding was very difficult to come by. People thought, no way will this instrument ever tell you anything about sort of what's going on in the complex world. So we decided to take a peek at the atmosphere, see what was going on, and then use that to drive the lab studies that we do. It's turned out to be a really nice approach because, when you go to the lab and you're looking at these complex systems, there's so many choices of things you could study. And to me, personally, and also for my students, it's more fun to study things that have very direct relevance. And we're at that point now. And so we jump back and forth, as I will show you today, and I hope you'll get a flavor of the kind of approach we take between lab and field studies, as do more and more people. We always keep in sight the models. The models are the key tools to predicting where things are heading. As Jim talked about, we're trying to understand how much warmer it's going to be. What are the changes going to be by the end of the century? There's a lot of uncertainty in that. A lot of the reason for that is because the models, as far as the chemistry goes, are pretty cryptic. I mean, they're because it's hard. It's hard to model all of the processes that go on. And so we're trying to slowly feed sort of some of the bigger effects into these models and see how much of a difference it makes, particularly with respect to the aerosols. Another side of things that we look at is the sources. One of the things that we've been able to do, basic research in our group, we measure the chemistry of individual particles one at a time. And we measure thousands, millions, billions of these particles all over the globe. And one of the big questions we ask repeatedly is, where did these particles come from? Why are they there? And the reason we do that is we're always thinking down the road to the policy. I have to think about it. There's a lot of reasons you might ask questions, but I think in the role that we have right now, we need to be feeding into the proper policies being established, and we can only do that one of the best ways, I think, to do that is to actually figure out where things are coming from. The regulators are much happier when you actually can tell them, if you remove this particular source, things will change by this amount. So that's how we think about things. So the final part of the talk, I'll just basically focus on 2 examples of some of the newer research we've been doing. So stepping back to sort of the basic sources of aerosol particles, I think everybody in this audience is very familiar with them. As I say, they're very visual, so it's easy to see that they're there. The part I like, as I mentioned, is that we study single particles one at a time, and they're beautifully, I think, complex. I noticed wallpaper in the other room had some cool images of particles too. I think they were. They all little round things look like particles to me. But basically, the range of complexity spans. These are actually from the ocean. There's just a wide range of particles, and when you just look at the images, which is really the main information we had when we got started, we're looking under a microscope and looking down at these. You can see this complexity, but the sort of the downside of the drawback to doing this approach is that it's slow. You're looking at 10 particles and trying to extrapolate to the atmosphere. So the goal with our research has been to look at a lot more particles as fast as we can, never sample things onto filter paper, and to try and sort of go after things in a more real-time approach, more in line with what people have been using for gas phase analysis for years in atmospheric chemistry. Another thing to keep in mind about aerosols and pollution in general, and I think this has been a great graph that maybe some of you have already seen before. Basically, one of the things that people used to think was, if the pollution is bad, like if it's really high and it's increasing in China, that's China's problem. If our pollution's increasing, that's our problem. Mexico City's is going up, that's their problem. But what's been shown recently is that the atmosphere has no walls. Air pollution is transported globally. We get a lot of our pollution from Asia and the United States. A lot of that is in the form of dust, which is one of my favorite things to study. Dust, I'll come back to. We import a lot of our pollution, and we also we export a lot of our pollution over to Europe. And there's millions of examples of sort of this airflow and basically air pollution being transported from one region to another. So I think this has really shown this international sort of global problem in that we have to work together. There's no more finger pointing. We need to work together to actually establish the problems and figure out ways to solve them. So just a basic sort of tutorial. Jim focused on CO2. Again, that is the main thing that's been studied, and I think obviously we need to keep focusing on the CO2. But the scary part to me, at least about the aerosol side of things, is how poor our understanding is of the aerosol component. I think before we can make any major changes, adding more aerosols to keep things cooler or whatever people keep talking about, we need to establish a much better understanding. So the way aerosols work, Jim mentioned the solar coming in. Aerosols can actually absorb the incoming radiation, which leads to warming. By doing that, they block a lot of the light that's coming down to the surface. They also reflect the light back into space. And so if you don't get the light down to the surface of the Earth, then you aren't going to get the emission of infrared, and you will not get the noted greenhouse effect. So the aerosols are basically acting in a way to sort of shield us. And so a lot of people say, air pollution is a good thing because it's cooling things. And I would have some debate about that, and we'll talk more about that. But basically, this is what's termed the direct effect. The indirect effect has been termed our largest uncertainty in climate change. And basically, at the center of every cloud drop is a particle. And only certain particles form clouds very effectively. We're still trying to sort out what determines whether a cloud forms or not. And so clouds cover roughly 60% of the surface of the Earth. We don't completely understand why they're there or why they're not. In some places, we're starting to see major effects where people are starting to pinpoint aerosols as being important in affecting meteorology and weather patterns. They've been shown in this case, if you have a lot of extra pollution in a cloud, you only have so much water, and so you form smaller drops that can never grow big enough to rain, and so you have much longer lived clouds, which leads to more cooling, but it also leads to suppression of rain and drought. So now aerosols are being linked, or air pollution in general is being linked to potential problems with our water supply, which is significant. These are just 2 images of a cloud drop in the liquid phase versus the ice phase. We've been looking at sort of the differences in the chemistry or the cores of the particles that form these two. Ice phase is very, very difficult to study because their concentrations are so low. So we've been focusing on those in particular. All right. So just to step back, Jim mentioned the IPCC report. This is the fourth IPCC report that he mentioned came out in 2007. Just a few take-homes in this. Basically, if you look at the greenhouse gases, which are on the top, you can see that they're noted warming. Our uncertainties are relatively small. But if you come down to this green box, this is where the aerosols fall. And what I want to draw your attention to is how large sort of these uncertainties are. In fact, if you go from the size of these uncertainties down to sort of our total, sort of net uncertainties for human activities impacting climate, the size of the error bars, or not error bars, but uncertainties are rather large. And so the goal of our research and a lot of other people's research, it's really ramping up now, is to try and gain insight to why these error bars are so large and try and help reduce them so that we can sort of get a better handle on where are we going, where is the temperature going to be at the end of this century. So stepping back a little bit further, this was the third IPCC, and I like this figure still because it focuses in on a topic that's near and dear to my heart, which is aerosol mixing state. And by aerosol mixing state, what I mean by that is the chemical associations. Which chemical species are associated with which other chemical species in the same particles? Because ultimately, that is what affects or impacts the climate properties of aerosols. And so, if you look at sort of the aerosol region, you can see here it's basically our understanding is very low. The point I want to make is sort of these different categories of what I would call mixing state. Basically, you can break the aerosol down into the different types of particles that are floating around sort of individually in the atmosphere. And what you see is what I want you to see is sort of the labels that are used right now. And basically what we think about are sort of the basic things that are emitted. We've got a sulfate. One of the key things I want to draw your attention to is sulfate versus black carbon or soot. They're in separate categories. We look at sulfate as being very reflective, very cooling. We look at soot as being very warming. But one of the things I want to point out is if you actually measure these particles one at a time in the atmosphere, are these really separate? That's really, really important, and I'll come back to this. I'll tell you the punchline is no. Most of the time, no. And so we're never going to get the right answer as far as how the aerosols are influencing climate until we get these particular categories correct. The other thing that I want to point out is mineral dust. Now it actually has in the fourth IPCC a little bit of a value associated with it as far as, I believe it comes out as cooling. But basically, you can see mineral dust is the least understood as far as impact on climate. So basically, why are these uncertainties for aerosols so large? The biggest reason is one of the biggest reasons. Well, there's actually two. From my perspective, the measurements have been lacking because they're very, very challenging to make. But until we have really, really accurate measurements, we're not going to have really accurate models. And so we've been focusing on the measurement component, keeping in mind what the models are actually doing. So the models, because they're so large and require lots of computing power, also because, as I say, the measurements haven't been there to change it, present a relatively simplistic picture of aerosol chemistry. Sulfate aerosol is sort of one of the types of aerosols that get sort of bandied around. There are other modelers that are developing more and more sophisticated models, but those have not achieved sort of the global scale yet. But I think they will get there. As I say, they have to have the proper inputs, though. The chemistry is overall quite complex, and as opposed to CO2 and other greenhouse gases, it's highly variable. It depends on where you are. Because of aerosols, you can have warming in certain parts of the world, and in another part you could actually have cooling. And so you're looking sort of at these large gradients due to the aerosols. And basically, there's really not much known about sort of the chemistry that happens and how that changes the properties. These are all the different processes that could happen or do happen. Very few of these are included in models, or there's major assumptions made if they are for the large part. But this is the direction that modelers are moving. They're trying to go in and do fundamental studies to understand a lot of these processes by looking at sort of stepping back and looking at the individual processes themselves. The questions that we had when we started out are, if we can measure things in real time, if we can measure things fast, if we can measure chemistry well, can we actually measure the climate impacts of real aerosols out in the real world? And that was debatable when we got started. Can we measure how atmospheric particles evolve, and in turn how those particles impact climate? And then climate actually will turn around and change due due to those changes and can turn around and impact the particles. So there's this dynamic interaction between the two systems that is very, very difficult to unravel. How do these changes, as I say, impact the properties, ultimately impact climate? And the two areas that I'm going to focus on are measurements of optical properties and cloud formation that we've been doing recently. So stepping back, what's the way we have looked at aerosols? For years, it's been basically pulling air through a piece of filter paper, collecting bulk samples, and then trying to sort of understand what the aerosols are composed of. And basically, we have to assume an average composition, that all particles in the atmosphere look the same. And that is, or if we want to get fancy, we have to assume what is the mixing state? How were these species originally really split up? And there's a lot of assumptions involved in that. Our approach has been to look at single particles. By doing that, we can get separate fingerprints for each particle and link that back to the sources. We can also say how much a particle has actually undergone aging in the atmosphere. In turn, how these different types of particles impact health and cloud formation and optical properties. So we've been trying to sort of reduce it down to a very simple form, looking at one particle at a time. The method that we developed when I first became a professor, and we've been using as well as a wide variety, I should point out, there's a lot of different measurements in a lot of different groups doing this type of research. And basically, you need as many approaches as you possibly can get. Intercomparisons are critical, especially when you're making sort of newfangled measurements that you're not really sure what you're going to see. But basically, it's a real-time instrument that pulls particles into the system. We scatter light off of the particles. I should mention my training was in molecular beams, and so this is sort of a boiled-down version, but now instead of looking at the gases, we're looking at the particles. So the particles come in, they undergo a supersonic expansion, they pick up different velocities depending on their size. So we can track each particle by measuring the speed between two scattering lasers. That gives us the size of the particle, so this is the particle sizing region. We now know the position of the particle, the speed of the particle. The smaller particles move faster, bigger particles move slower, so we can equate that with size. And we can basically determine when it's going to get to the center of our chemical analyzer, which is a dual polarity time of flight mass spectrometer. So it's essentially two mass specs, where we do laser desorption ionization. We blow each particle apart using a pulse laser into bits and pieces and detect positive ions down one flight tube, negative ions down another tube. It's really important to get as much information on each of these particles as you can. You only get one shot at them. But what we're able to get is size, how chemistry changes as a function of size, and most recently, I'll touch on this a little bit, we can look at the optical properties. We're linking this chemistry, hopefully, ideally with specific sources where it came from, and we're starting to bridge it with the climate parameters. So stepping back to the filter method, what you basically get, these are the basic components of aerosols: organic carbon, soot, sulfate, nitrate, ammonium, and dust. And you measure a total mass, and you look at how it's divided between the different chemical species. And from this, you try to sort of figure out where things came from, which is a bit challenging. This next slide is overwhelming, sort of, but it's just, I'm going to sort of go through and explain. This is our perspective, which is basically, instead of looking at individual species, we break things down as a function of size and the percentage of them in the atmosphere. So we can just count them up and figure out where the major sources are coming from. We can link that with a source or chemistry. You see there's a very strong size dependence. Mostly carbonaceous, fossil fuel combustion, biomass burning fall below a micron, whereas dust and salt, sea salt in particular, fall in the larger sizes. These are actually microbes from the ocean that we see in marine environments. And then we look at where are the reaction products going. In other words, where is the organic carbon, ammonium, sulfate, nitrate, which form by atmospheric reactions, where are those going? So having these aerosols present in the atmosphere completely changes the chemistry of the trace gases. Without the aerosols, there's modeling studies that show a completely different atmosphere if they weren't there. They present a huge surface area, very similar to what people discovered in the stratosphere with polar stratospheric clouds. They induce reactions to happen that just wouldn't happen if they weren't present. So the two examples I want to focus on: impact of soot on climate. This is just to show you the spatial variability, this is a model that's been constrained by measurements by one of my colleagues, Professor Ramanathan down at Scripps and Greg Carmichael at Iowa. And basically what it shows you is what I've been saying, is that the warming that you get from, and this is just focusing on soot, comes mostly from, or comes over land, and you see a very large gradient in the temperature depending on where you are. And basically, Professor Ramanathan has come up with a really nice way of actually measuring, direct measurements, not modeling, direct measurements of heating rate, flying UAVs through the atmosphere. And so they used a lot of those measurements to sort of constrain models and come up with this map. And what they found was the IPCC estimates that the forcing due to, the forcing due to, or the warming due to soot is about 0.4 watts per meter squared, which makes it very strong forcing agent, equivalent to, or second only basically to CO2. Professor Ramanathan's work puts it at about 0.9. Other measurements, depending on sort of what your assumptions that you make, put it up closer to 1.2. Very strong forcing, warming, where a lot of people always say, think of aerosols as cooling. And so the question is, why is there this range? Is there a way we can explain it from direct measurements of the soot that's present in the atmosphere? This has large implications for, as I mentioned, regional weather patterns as well as other aspects of climate. So one of the things that we are interested in is, can we go in and look at the soot and see sort of how it's mixed, and can we sort of use our measurements to further sort of come up with a link with the measurements that are made on the heating rate by Professor Ramanathan. And so basically, we've looked at sort of the optical properties of the soot specifically. Only recently we added that ability. One of the questions is, a lot of people look at sort of how fast does it transform in the atmosphere, because soot will change. As it changes, the optical properties change. Also, the cloud forming properties change. So can we pick that out using real-time measurements? And then how do these impact the optical properties? So thinking about things from a mixing state perspective, if you think about sort of, this is a very hypothetical scenario, where you have 90% soot that you've measured on your piece of filter paper, 10% sulfate, you have two scenarios. You can have every particle looks the same, which is basically what you have to assume, or you can have basically sulfate, which is very reflective and cooling, and mostly soot, which is warming. These two scenarios have very different optical properties and also warming potential. The bottom line, when I first saw this, I used to think, okay, if you put sulfate on the outside of a soot particle, maybe you're going to reflect all the light back to space, and this will be good because you'll shield the warming part, the absorbing part. But what actually happens is you put a material that's got a high refractive index on the outside of these particles as they age, it actually causes a focusing, so you get more warming. So now you've taken your friend, sulfate, which is everybody loves to think of as cooling, and you've made it become an actual sort of accessory to the crime, and it starts to cause extra warming by up to a factor of 3 for soot. So this can start to close the gap. The range that you get for the forcing of soot and sulfate now can start to make a little more sense if we can look at this a little more closely. So a bit of data. This is single particle spectra from a single soot particle. We call it soot because it has a very obvious carbon pattern. This is an electron microscope image. Fresh soot is very fractal aggregates of little carbon spherules that are combined together. And as it ages, you get a picture more like this. As soon as you start to put down species that like water, the particles start to absorb water, and that fractal geometry collapses, and those have completely different optical properties. So the question is, what we're interested in is, how are can we see a difference in the optical properties of these particles versus these particles? And so this is just a bit busy, but basically it's the scattering or optical properties of different types of soot, where we've taken basically each one of these points represents the optical properties of a single soot particle. And what we found was the fresh soot, for smaller sizes, scatters much more, as you would expect for a large fractal type particle. But as time goes on and the particles age, they start to scatter less and less and grow in size, and it collapses into this is the me theory curve. It's basically what can describe the particle based on its shape. And so, in fact, we do see this transformation in the atmosphere. And the question is, how fast does it happen? So this is a time series. We see the same thing in Mexico City or Riverside, which are photochemical environments. Time of day versus the amount of soot. And you see there, the blue is the fresh, this is supposed to be relabeled, sorry, this is fresh soot. And then the red is the age. So it's color-coded to go with this. And basically, the answer is it happens very quickly. you don't have that much fresh fractal soot for very long, unless you're in the center of an urban city where the soot is being emitted. We can look at this for measurements we've made all over the world, and we've basically gone in and said, okay, how often do we see the fresh soot signature? How often do we see the aged or the mixed soot signature? And the take-home from this is that it's safe for modelers to basically go in and realize that it's either sulfate or nitrate, or organic carbon, and also water, that are condensed on these soot particles. And so from a modeling perspective, this is actually really important. We can quit switching back and forth what if. I think we are pretty confident that fresh fractal soot does not stick around for very long. Similarly, fresh sulfate doesn't stick around for very long. They combine very quickly in the atmosphere. So switching to dust, these are just events just from this year. Dust is the largest aerosol worldwide. It's present globally, and you can see it from space. This, as I mentioned, is a huge surface for reactions to happen upon, and being a chemist, that's why I like it. It is rather messy. We actually did some studies, or a study on Jeju Island in Korea. This is during a dust event. People put on the masks very quickly. So let's step back and think about just dust reacting in the atmosphere. This is the part that basically the understanding is relatively poor. If we take two different minerals, aluminosilicates are one type, calcium carbonate's another type, we think about secondary species that might mix on those particles. We take these two particles, we put them into this mix. I made this movie myself. You can tell, I know. But anyway, my students were shocked. But anyway, so basically what you see is here's the core of each particle, and the question is, does each particle sort of react the same? And this is almost embarrassing as a chemist to ask this question, but believe me, dust in models is treated the same. There's one entity in the atmosphere, it's called dust. It has one rate constant with whatever species you're talking about. So all dust evidently reacts the same. So anyway, so we were humoring that sort of view and saying, okay, is this true? Or in fact, do you see different reactivities depending on the chemistry of the core? And so basically these two scenarios right now, this is more the treatment that the sort of the way you look at it in models. We actually were wondering if we would see something like this. And so basically it's really important to do this because this is what we assume, and it's sort of like your standard sort of bimodal, exam scores, where you've got students that got 10s and some students that got 90s, and you say your average is, the students knew about half the material. Turns out none of the students knew half of the material. Same thing here, where basically the properties, the climate relevant properties that you care the most about, you'd completely mispredict from the standard picture where everything sort of reacts the same. Whereas in fact what we do see, as I'll show you in a second, is we see mineralogy plays a huge role. And so basically to do that, we've had to go into the field. We've went in a variety of platforms. We've been on ships. We've most recently done airplanes. We've got a mobile lab. This is really interesting We aren't doing measurements while they're carrying it. But this was actually in India, where there aren't any sort of ways to move our big instruments around. So this is a mass spectrum of a single dust particle in the atmosphere. And you can see the typical mineralogy. This is an image. And then in the negative ions, this is where you can see we can look at the degree of reactivity. We can look at those secondary species and watch them come and go and study how these products change as a function of the minerals that are present. And so this is a messy one, but I'll try and walk you through it. This is looking at single particles with different amounts. If they have 100% calcium as the mineral, it's up in this corner, 100% aluminum down here, 100% iron down here. Same thing on this side. So it's the same particles, looking at the amount of sulfate and nitrate on these particles. And so basically, these are the two classes that I'd mentioned before. And what you see, hopefully, is that the sulfate content on these particles is quite low, whereas the nitrate on those same particles is very high, and vice versa. Here we have lots of sulfate, very low nitrate. So we're seeing completely different partitioning of the species depending on the mineralogy. And this was the very first measurements that actually showed this. There were some lab studies that basically said this could happen. These were the first field studies that actually showed, in fact, that mineralogy plays a major role. And from a fertilization perspective, everything else has major ramifications. Again, so sort of looking at things, stepping back. So we did the field study, we saw the dust, we learned a lot, but we had a lot more questions than answers. So we went back to the lab, and what we can do is we can actually simulate clouds in the lab. We can vary supersaturation ratios, which mimic those that would be in a cloud. So we're changing the RH, basically, above 100%. And we can look at the fraction of particles that activate as a function of supersaturation. So we can start out with a simple mineral like calcium carbonate, and basically we're ramping up the supersaturation. All of a sudden we hit here, and this is activation. The particle starts to grow and turns into a cloud drop. What you see is, for calcium carbonate, that happens at a relatively high supersaturation. We can take these calcium carbonate particles, react them with nitric acid for various differences in time, march it down to calcium nitrate, which is very hygroscopic, and what we see is the supersaturation for this to convert to a cloud drop changes. It gets much lower supersaturations, which says that the reactions are actually changing the cloud formation potential of these particles. This is lab studies, but we can take the kinetics from these types of reactions. I won't go into a huge amount of detail, but we can calculate an atmospheric lifetime, how long it takes the calcium carbonate to convert from not a very good cloud particle to something that is very good. It takes less than an hour. And you can do this for various nitric acid concentrations. And this is consistent. In the atmosphere, when we measure calcium nitrate particles, they're not big old morphologically sort of distorted particles. They're actually nice spheres that we can model with me theory. So the consistency between the lab and field studies is actually quite nice. But the thing about the ground-based studies is you can learn which parameters are important in forming clouds, which particle types are better, which particle types are worse. So it tells you about the things that are important in forming clouds, but you're missing sort of what does form a cloud. So to answer that, we did a series of flights in November of this past year, and the question is, how different is the aerosol that's feeding outside of the clouds into the clouds? Do we see any sorts of enhancements in the particles that are outside versus inside? Is chemistry playing a role? Which for a long time, and a lot of people, and I'll mention this again, believe that size is really all that matters. So here's the setup. We sampled from what's called a counterflow virtual impactor, which is a fancy way of saying we only let the big droplets and ice crystals pass. So we weren't looking at the aerosol inside the clouds. We could switch back and forth. But the goal here is to look at what really were forming the clouds. And so we could evaporate those down and then measure their size and chemistry in real time. And so basically, when we were doing these flights, we were looking at different, we can look at where the air masses were coming from. And they are always coming, for the most part, from these directions. I'm going to talk about RFO1 and RFO3 here, but basically they're coming from pretty similar regions. And so, as I mentioned, we're looking for an enhancement due to chemistry. The big question is there any difference in the chemistry of ice versus liquid clouds? And that has never been addressed before because ice are very difficult to measure. Their concentrations are so low that if you try to catch one and then go look at it, it's really, really challenging. But we only need one particle at a time, so we were able to actually differentiate between those two phases. The big question, these are sort of some of the battles that have been going on in the literature. Andy Andrea came out with size matters more, the big grand statement. How do aerosols affect precipitation? These are some of the questions. And so these are sort of the things that we're thinking about. One of the types, sort of punchline of the whole thing, that we saw repeatedly were these very specific types of dust. Positive ions, we would see, they look a lot like sea salt, but they're not sea salt. They're actually enriched in what we would call hygroscopic or very soluble salts. In the positive ions and the negative ions, they have markers actually indicative of biogenic material. So they were looking a lot like dust, but with dust-like particles, but they're very, very salty. And so the question is, where did those particles? I'll come back to that. So this is again a messy one, but I think I'll walk you through it. So this is this is flying through a cloud, and we're switching back and forth between out of cloud and in cloud, looking at cloud drops. So everywhere there's a green marker, this is sampling from the CVI. So what you see is out of cloud is the sort of reddish, all these other different colors. Every time we switch to the CVI, these salts dominate. They completely dominate. And so this was a surprise. This wasn't, people have seen sea salt as being important. A lot of people think ammonium sulfate should be important, but these salts were not really anticipated. So we looked at the origin of the air mass a little more closely, and every time this happened, the air mass was coming right over the Great Salt Lake region. So we believe these are the dry salt lake beds. And if you think about how a dry salt lake dries out, it's sort of like Mother Nature's made the perfect cloud seed. Because as the lake bed dries out, the most soluble, and Tony Wexler's written a paper about this, the most soluble material will end up on the very top. And so when you have a windstorm, it picks off the very soluble material, the best cloud seeds you can possibly get, and lifts those into the atmosphere. And a lot of people hadn't really thought about this, because most people, when they're trying to understand the potential impacts of these, go scoop the dirt out of the ground and look at everything. They're missing the stuff that gets levitated. So the take-home in this for us is that size is important, no question, but in this case, the chemistry was playing a major role. Just the amount it dominated was a big surprise to us. So conclusions, basically we are working very hard to sort of provide a more accurate picture of the mixing state of aerosols, to sort of be able to really say how they're affecting climate and how things will turn out over time, hopefully. The flight experiments were very enlightening, because they really showed us that it's really important to go back and forth and to actually do the flights and see what's really up there. I mentioned that we're using both of these. We're really working hard with modelers. They say our data are finally useful. There was a pretty big disconnect between what we were measuring and what modelers needed. And so we communicate very differently. And so now we're starting to bridge that gap, and I think that's a really exciting thing to be doing. One thing I want to point out is Jim had mentioned things we might be able to do, and a lot of people talk about this sort of geoengineering approach. I mean, Paul Crutzen, I talked to him, and he said he was just sort of joking when he put that out there as an idea for people to ponder. We never know what we're going to have to do if things get really bad, and it might be good to have some special bags of tricks in our back pocket if we need them. But basically, I feel very nervous knowing how little we know about the aerosols, at least from the aerosol perspective, making any major changes. People really honestly say, put more sulfate up, or, remove this, or whatever. If we don't know things better than we do now, I'd be really nervous about that. And so I think we really need to push very hard in the little window of time that we might or might not have to understand these things better. And one of the ways we look at these particles is that they're actually, in a way, they're very short-lived. So any change we make will be relatively rapid compared to CO2. And so it's a way that maybe we can think about buying some time while we sort of grapple with what the best other approaches are. But anything we change, it will be a relatively quick change, and maybe it will ease some of the strain that our planet is under right now. And as I say, I don't really love the idea of geoengineering, but at the same time, I think it's smart. Jim pointed it out. It's very true. We're already messing with the system. So to say that, don't touch it, we're already doing that. I think we need to understand how what we're doing right now really affects what's going on. So I'd like to acknowledge again the Camille and Henry Dreyfus Foundation for the invitation. My entire group has just been fantastic. They are just, I wouldn't be standing here if it weren't for them. I've established the last few years, since we've been doing the cloud work, a wonderful sort of collaboration with Professor Kreidenweiss and Paul DeMont looking at ice, and Marcus Petters at Colorado State. And the funding sources for the work that I've described are from NSF. And I always finish my talks up with just keeping in mind that every little thing that each one of us does can be amplified. And this is my son looking at a tide pool, which we know has changed already in our lifetime, and I would like to play a role in keeping that tide pool at least somewhat there for his future, for his children. So anyway, with that, I'd like to thank you for your attention.
Thank you, Kim. Exactly on time.
Oh, wow, I was talking fast.
We have time for a few questions. Please identify yourself and use the microphones.
So, Alan Stone from Johns Hopkins. You mentioned that today we have 60% of the Earth's coverage by clouds.
On average, yeah.
What was it like 200 or 400 years ago? Does anyone have any kind of idea? Before we had jet planes and so many smokestacks?
Yeah, that's a good question. I mean, obviously there were clouds. I don't know what the percentage. Do you know what the percentage? I mean, I don't know if it was how much different the cloud coverage was. Yeah, I'm asking you. Do you know? Because I actually don't know.
Yeah, this is pre-industrial. We have extremely good records from Asia, from Europe.
For cloud cover. For cloud cover. I don't think. Do we for cloud cover? I don't think.
Yeah, the albedo of the Earth.
No. I'm just thinking of the clouds themselves. For the albedo, yeah, but I'm saying I think he was asking if we had clouds.
Yeah, it hasn't changed dramatically. We have the evidence from pre-1750.
Right.
So it's obviously an issue. The cloud creation is now with smaller particles. The clouds a little.
We're changing the droplet size.
And you can see from the forcing there that it's a 0.6 of a watt per square meter thereabouts.
Right.
Large
sort of, yeah.
But that's basically the structure.
Mm-hmm. I mean, we know we're also modifying the clouds, not just the number that are there, but we're changing the droplet size and all the other parameters of the clouds. But yeah, anyway.
Yes, Kim. Don Stedman, University of Denver. I and Dreyfus, I'm sure, would be happy that you said the chemistry matters. You also said the regulators are happy if your science tells them how to regulate. My experience of the last 20 years is that's not always correct.
It's not always correct. I'm being optimistic on that statement. But yeah, I mean, I would say they're more, over the time I've been doing this, I would say they've become, maybe I'm just talking to the right people, but they seem more inclined. I've learned which things to say to them where they just sort of glaze over versus which things they act like they're going to go do. And they have made changes, So I just know that certain answers we give them aren't going to budge them. And certain answers, certain directions we can go, we can sort of move things along. I do see a difference. And I have seen it change over time, so.
Question before break? Last question. Oh.
Charles Dismukes, Princeton. You mentioned the case of biomass and comparing that with regards to carbon-based or soot-based particles. As we go forward from here, of course, we're going to have a bigger fraction of that contributing. And sources could include such things as terrestrial biomass, but also lots of people are thinking of using marine-based biomass. And so I presume there will be a difference based upon what you just said about salts, marine salts. So could you sort of predict what would be worse of these two scenarios? And I'm not sure if they're doing pyrolysis or gasification.
Yeah, the biomass that I was referring to was pyrolysis. So it's like biomass burning, combustion. So, and I mean, sort of that's being, in a sense, that's changing also, especially in the western United States, because we're just getting far more, as things are drying, we're getting far more wildfires, and we're sort of in the middle of a pretty vicious cycle. But as far as, biomass burning is sort of the number, if you ask me globally, what's the most important sort of source that I see everywhere I go? To varying extents, biomass burning is a big one for a variety of reasons. In the poor countries, people are burning very ineffectively, burning very poor heat sources and cooking sources. And so there's a lot of reasons, a lot of different that's a catch-all for a lot of different sources. And it's all intertwined. And I think to sort of sort out the fractions and the overall impact, we're a ways away from doing that, unfortunately.
One more question.
Peter Stang, University of Utah. I don't have a question. I'll offer a comment, and that is those of you who are skiers know that Colorado and Utah has the best skiing, has fluffy powder snow. Our water content is something like an inch of water per 16 inches of snow rather than the usual 3.5. And the hypothesis is that this is due to what you mentioned, and that is picking up the salt crystals from the salt flat that then act as seeds.
Is that actually published? Because we talked to people about it, and they are sort of in denial, as far as that it sounds like the skiers have got it figured out, so maybe I better...
Heather Allen, Ohio State. I noticed that the potassium was the largest signal. Can you comment on that? And is that similar than what it would be over the ocean, or is it the dry bed?
Potassium I'm trying to remember which figure.
When you talked about the trajectory and the
in that salts. Okay, yeah. So potassium can be the largest signal, but it doesn't have to be the most abundant ion. Right, you have different sensitivities to different species.
So when it's normalized, then for
that, it would be less than the magnesium and calcium salts are the really abundant ones. Yeah, thank you for pointing that out. We have a very high sensitivity, so you have to normalize to your sensitivity factors.
Thank you again. We shall reconvene at 11 o'clock sharp.
Yeah.
a Department of Biology, and Earth and Planetary Science. And in homage to this, what I would like to convey to an audience of chemists are two things. One, as I'm sure many of you appreciate, microorganisms are really the greatest chemists on the planet. And we know this because of the rock record that tells us that for billions of years of Earth history, they've been catalyzing truly extraordinary reactions that have transformed our planet. Now, in my lecture today, I'm going to be taking you on a journey from iron oxides to infections, which is somewhat of an unlikely pathway to travel. And so I thought I would begin by telling you a little bit about a way we think about biological problems in my group, which is motivated in large part by an Earth historical perspective. So we heard earlier this morning about climatic change in the context of thousands and millions of years of Earth history. And surely understanding past records gives us insight into what is currently happening today to be able to give us a perspective on those changes. But, of course, processes that occurred not only in the past, shaping our thinking about the present, but processes that today occur, be they physical, chemical, biological processes, can give us insight into the past. And so this figure here is a picture taken from a hike in South Africa, where what you're looking at in the foreground are rocks that are 3 billion years old. And in the background, you see a sediment that contains ripple marks. It was a wave crashing on a little beach, dried up, and when we went on this hike, we snapped a photo because it was such a beautiful illustration of this principle of uniformitarianism that pervades thinking in the earth sciences, where we have a dialectic, often intellectually, between trying to understand how modern-day processes work with the assumption that these processes are very conserved through time and may give us an ability to interpret past phenomena. And then, of course, the reverse. And so what I'm going to specifically talk about today is how our work looking at microbial interactions with minerals led us down a pathway where I'm quite convinced some of the fundamental processes that we were thinking about in the context of microbe-mineral interactions may also be very informative in thinking about how we treat certain types of anaerobic infections. So to begin with a timeline of Earth history that now goes back many billions of years to the origin of the Earth, we know that microbial life has been around this planet for almost all of its history. In fact, we have isotopic evidence from carbon isotopes that tells us life was present at least 3.8 billion years ago. And we have a number of other ways of assessing the antiquity of life. And I've grouped them here into three primary categories. Morphological biosignatures that can come in various scales, from that of millimeters to microns to even nanometers. Here you see biogenic particles of magnetite forming inside a cell that makes magnetite to help it navigate within the geomagnetic field. We also have molecular biosignatures, both isotopes of various elements and more complex organic structures that incredibly are preserved in rocks as old as 2.7 billion years old, which we know must be derived ultimately from some form of life. And finally, we have a genomic record, the fossil record of DNA. And from this, we can begin to deduce evolutionary relationships not only between organisms, but also proteins that these organisms contain that catalyze very critical reactions that shape the planet. Now, for me, thinking more as an environmental scientist, I like to consider this a fossil. Now, you might not think initially that this is a fossil because it's a huge ore mine. And in fact, this particular ore mine comes from Western Australia. This is the Hammersley Formation. And it's also known as a banded iron formation because of the type of mineralogy present in this deposit. Now, we have a record of these types of formations that go very far back in time, extending back, at least to around 3.8 billion years, and continuing throughout Earth history. And what is now, I think, very well accepted is that the root of these formations in terms of the catalytic agent that led them to be precipitated is microbial. And here's how it works. So back in ancient times, there was quite a lot of ferrous iron dissolved in seawater. And something catalyzed its oxidation to the ferric state, which then rapidly speciated to form different types of iron oxide minerals that then went through the process of diagenesis to result in these deposits that today we can observe. Now, the catalyst, one of the most important catalysts for this process of iron oxidation, was some type of microorganism performing some type of photosynthesis. And there's a debate over whether the type of photosynthesis was oxygenic, meaning taking, as I'm sure we'll hear a lot more about this later in the afternoon session, water to molecular oxygen, and then that oxygen chemically reacting with the ferrous iron to oxidize it, or alternatively, anoxygenic photosynthesis, where ferrous iron itself was a substrate for oxidation powering photosynthesis. Now, be that as it may, either one of these microbial processes helped bring about the formation of these minerals. And then once they arose, this provided a fertile substrate for respiration, the opposite process, where these iron oxide minerals could serve as electron acceptors, as much as we use molecular oxygen today, allowing the burning of organic carbon. And this is the part of the story that I'm going to focus on and explain how we got from trying to understand the details of this process of respiration to some insights that are relevant for infection. So we began our work by studying a bacterium called Shewinella onidensis, and this is a scanning electron micrograph that you see here. This is a really wonderful organism because of its metabolic versatility. So it can respire oxygen, and in addition, many other substrates, including iron oxides and manganese oxides. Now, as you can see here, the cells are forming aggregates, and some of them are directly touching this ferric oxide below. And from a cell biological perspective, how these cells are acquiring energy from growing on this ferric oxide is a very fascinating problem. And here's why. These cells contain two membranes. And let's focus first on the inner membrane, which is also called the cytoplasmic membrane. This is where the cell is able to generate a gradient across this membrane that enables it to power the formation of ATP within the cell. This is called oxidative phosphorylation. And the way it works is that within the cell, there is some substrate that eventually gets oxidized, providing electrons to a membrane-bound enzymatic system that can couple the translocation of proteins across the membrane to the transfer of electrons through the membrane. And this occurs through various carriers, both proteinaceous and small molecules such as quinones, until those electrons are received by some terminal electron acceptor. Now, in our cells, in our mitochondria, this electron acceptor is oxygen, and that also can be the case for Shewinella. And if it's oxygen, it's not so difficult to envision how this happens because we know that oxygen can diffuse across the membranes to the site within the cell where it is reduced. However, iron oxides are a totally different story because under the pH that's relevant to the problem here, they are very, very sparingly soluble, effectively insoluble. And so how does this electron transfer process work? They simply cannot diffuse within the cell. We now have a schematic for how this works based on a lot of genetic and biochemical experiments that have been done in a variety of labs, and I'm summarizing this for you here. What we now know is that the cell directs electrons to iron outside of the cell, again via a series of electron carriers, many of which are C-type cytochromes. And the part that I want to focus on is what happens at the interface between the outermost portion of the cell membrane, where there are some decaheme C-type cytochromes, and the iron oxide mineral itself. The actual molecular details of how electrons get from these proteins to iron 3 to reduce it to ferrous iron are still the subject of much active research. And one thing that has emerged is that this transfer is likely mediated by small molecules in the environment, such as humic substances. And I'll show you their structure in just a minute. But the general idea is that this is a process that we can call extracellular electron transfer mediated by exogenous electron shuttling molecules. So imagine you have shuttle molecule X. It gets reduced by the cytochrome on the outer membrane. then in its reduced state, it can transfer electrons abiotically to the iron, reducing the iron and then itself becoming reoxidized, so it can serve as a catalyst. Now, humic substances were first proposed to be very important by Derek Lovely and his colleagues who were working at the USGS in Reston, Virginia. And what they found was that spiking groundwaters where microbial iron reduction was occurring with these macromolecular structures that constitute a very important fraction of the dissolved organic carbon in the environment, they were able to stimulate greatly the rates of iron reduction in those aquifer sediments. Now, the reason this is thought to be the case is because humic substances contain quinones, and these are the most important redox-active moieties on these molecules. So because of this, we can simplify our study of extracellular electron transfer in the lab by utilizing a surrogate compound called anthraquinone disulfonate, whose structure is shown here, that has the convenient property of turning color upon reduction by 2 electrons and the addition of 2 protons. Now, I'm a bacterial geneticist, and so as someone interested in the mechanisms of how bacteria catalyze reactions, this color change is very useful because it allows you to do a genetic screen where you can very easily isolate mutants that no longer have this capability. So again, taking this substrate as the indicator for extracellular electron shuttling, we first looked for mutants that had some insertion in a position of their chromosome at random and only one insertion in any given well, and isolate those that could no longer reduce AQDS to the hydroquinone, which stayed clear. And we found many different types of mutants in this process, but I'm going to only tell you about one for the sake of this story. And this one had a defect in the transport of AQDS. Now, how did we know this? Well, based on our analysis of where the transposon insertion in our genome lay, we noticed that it had fallen in the middle of a gene called TOL-C, which from previous research was shown to encode a protein in the outer membrane of many bacteria that was essential for the secretion of antibiotics and various detergents. So when we had this disruption in the middle of this gene, it essentially knocked out the capacity to produce this protein. Anthraquinone disulfonate built up in the cell, and this caused toxicity and therefore led to this apparent phenotype of a defect in reduction. So we were surprised by this because initially we hadn't made the connection between antibiotics and these electron shuttling compounds. But the more we thought about this, the more obvious the connection became. And you can see this when you just draw a few representative structures of known electron shuttles, such as AQDS, and compare them to important antibiotics, such as tetracycline, doxorubicin, which is used in anti-cancer therapy, and pyocyanin, a natural product that I'll come back to in great detail in just a moment. The reason we knew that they were functioning the same way was because when we compared the response of the cells that were grown on a lawn on a plate, here that's what you see in the background here, and looked at the wild type version of these cells and compared their behavior to the mutant that couldn't make this important efflux channel, the TOL-C mutant, what we observed was that regardless of which compound we spotted on these discs that we put down on the surface of our plates, in all cases, the mutant responds similarly in that it was unable to grow within a certain zone of clearing of the molecule on this disc. So in this case, we were seeing that these electron shuttling compounds, such as AQDS, were effectively acting like antibiotics. Now, what this suggested to us, however, was that the opposite also would be true, that possibly redox-active so-called antibiotics that the cells were making might also be able to function as endogenous shuttles. And so the idea here is that the cell might be producing some molecule, excreting it from the cell, which could take the place of these other exogenous shuttles that I spoke about earlier. And the more we thought about this, the more it made sense, because if you take a look back again at how these organisms actually grow in the environment, they're growing as biofilms, and that is communities of cells that are attached to a surface. And as these biofilms develop, as you can see, not all of them are in physical contact with the surface below. Here you see some on top, and there are many embedded in the middle. So now just to draw a cartoon version of this and flip it on its side, this really illustrates what I think of as the respiratory problem that biofilm cells face, regardless of what surface they're attached to. And that is that cells in the middle are quite literally stuck between a rock and the hard place in terms of expending their cellular reducing power. They don't have access to oxygen because that's being scavenged more rapidly by the cells at the top than it can diffuse. And they don't have access to this terminal electron acceptor below the iron oxide because they're not in direct contact with it. So we postulated that precisely in this context would be where the ability to produce your own molecule that you could cycle might be very beneficial for survival. So to test this idea, we came up with a very simple assay, and it works as follows. What we designed was a 3-layer plate. Here you're looking at it from a bird's eye view. Here I'm going to walk you through it from the side, where what we supplied was in the middle a layer that we created of nutrient agar impregnated with manganese oxides, and above it, a very thick layer through which no bacteria could swim. And the beauty of manganese oxide is that under these conditions, when it gets reduced, it turns clear. And so this would allow us to very easily detect the production of some type of molecule, rather the activity of some type of molecule that was diffusing through the agar, enabling manganese to be reduced. So if you look here in green, what you see is this activity happening for Shionella oneidensis. But on the left, there's even more activity for this organism, which is a strain of Pseudomonas aeruginosa that's very important in the context of cystic fibrosis. So this really caught our attention, and it's here that we began to think about this in a more clinically relevant context. So as I said, Pseudomonas aeruginosa is a very important pathogen for individuals with the disease cystic fibrosis. And the reason is because over time, within the lung of CF patients, mucus develops, and within that mucus, it's a very fertile home for the growth of bacteria. And as the disease progresses, Pseudomonas becomes the most important pathogen that colonizes the lung and ultimately leads to the death of these patients. Now, for over a century, microbiologists have known about Pseudomonas' ability to secrete beautiful pigmented compounds of the class called phenazines. So this is their basic structure, and they come in literally all the colors of the rainbow. It's a very aesthetic organism to study because of the beautiful pigmented small molecules that it makes. And depending upon which particular chemical substituents we have at various positions around the ring, that will tune the properties of the molecules up and down the redox potential scale. It will affect their hydrophobicity and philicity, and of course also their color. Now these compounds are versatile redox-active compounds, and we know that also from just very simple visual cues. What you see here is a culture where cells have been grown up overnight. What we've done is just vortex it for 5 minutes on the bench. You can see the bubbles at the top, and it turns this lovely aquamarine shade. If you then let this tube sit on the bench for another 5 minutes, everything below the water-air interface turns back to a more yellow color, which is the background color of the medium, and it's only at the very top that we still have this blue color. And the reason for this is that these phenazines collectively, when they're oxidized, exhibit a blue color, and when they get reduced, they go clear. Okay, so I said that phenazines have been known to scientists for over a century, and much of the attention that has been given to these molecules has focused on their antibiotic activity. And not surprisingly, it's very warranted, and that's because when reduced phenazines react with molecular oxygen, they generate superoxide radical species that are very broadly reactive and can do a lot of indiscriminate damage to cells. However, there's something very important to keep in mind when thinking about these compounds in terms of the biological context in which they're produced. And that is that they are made by cells only at very late stages of development, oftentimes when no molecular oxygen is present. And the corollary to this is that under anaerobic conditions, toxicity is greatly diminished. And so thinking now again more like an earth scientist, something that we also know, of course, is that oxygen has not been around the planet for all of its history. And we know furthermore that derivatives of these compounds can be found in the membranes of methanogenic archaea, which are a very ancient life form that certainly predated the rise of molecular oxygen on the planet. So even from a biosynthetic perspective, we know that the ability to make these phenazines is not dependent on oxygen. And because of this, we wanted to reevaluate whether their function was really an antibiotic one for the cells that produce them under the conditions that are relevant for their production. Now, Another conventional wisdom is that they are secondary. And, of course, by putting it in quotes, this clearly tips my hat, which is I feel this is a pejorative term and greatly unfair, because they're only called secondary because of the way bacteriologists have classically grown microbes in the lab, and that is in batch culture where we study growth here, looking at cell numbers rising over time in hours. And this phase of growth is what we call logarithmic growth phase or exponential growth phase. And when they start to plateau, when bacteria hit their middle age to old age, this is what we call stationary phase. And there's been a lot of attention by microbial physiologists on the adolescent phase of bacterial growth, but very little attention paid to their old age. And we can discuss why at the end if people are interested in that. But it's here in this so-called stationary phase that we suddenly see the burst in production of phenazines. And I've shown for you now two, pyocyanin, a blue phenazine, and PCA, a yellow phenazine. So we had a different perspective, and that was that under these conditions where oxygen is depleted from the cultures, phenazines might actually be key to survival. And so a way we decided to test this was to do an experiment in an environment devoid of oxygen and provide an electrode to reoxidize the phenazines. So we constructed a mutant strain that couldn't produce any phenazine on its own, and we were able to add a discrete amount back to the culture that we knew was a very relevant amount because this is roughly what the organisms will produce in the context of the lung. So here's what we did. We have this electrode set up. We have cultures growing. We have an electrode that can reoxidize them. And what Yuwen Wang, a postdoc in my lab, who was a student in Alan Stone's group, he's also here at this symposium as a Dreyfus recipient, did was look to see how the viability of these cells was affected by their ability to recycle phenazine. So within a period of a week, if they have pyocyanin and the electrode is turned on, they remain viable. They can form a new colony when they're plated. However, if you either turn off the electrode in the presence of the molecule or you do not add the molecule at all, you get a very dramatic drop in viability over this very short period of time. So this we thought was quite interesting and relevant, again, coming back to this cartoon, because the context where this matters for the organism Pseudomonas aeruginosa is in the lung, where they form biofilms, and the mucus that they inhabit has been shown to be hypoxic through microelectrode measurements. Now, how can we test whether or not this idea bears out in terms of the development of biofilms? Everything I showed you so far was looking at growth in planktonic liquid culture. Well, we can begin by doing some very simple experiments by growing biofilms on the surface of agar plates and monitoring their development over time. So here I'm showing you a comparison between a mutant that can't make any phenazine, the wild type, and a strain that overproduces phenazine. And we're going to now go through from day 1 to 3 to 7. And what is very obvious is that whereas the mutant that overproduces phenazines remains nice and smooth, the mutant that can't make any at all flattens out, expands its surface area, and becomes very wrinkled. So what's happening here? It's actually very, very complex, and I'm only going to talk about a small portion. So there are at least 3 different ways phenazines can be influencing this phenotype we see. The first is that they're signaling molecules that direct a specific behavioral response by binding onto transcription factors that recognize them, and we know that this occurs. The second is, of course, that the phenazines are affecting cell surface properties by binding to the cell, and that affects their ability to interact with each other and influence the morphology that we see. But the part that I want to talk about in the remainder of my time is their ability to function as oxygen surrogates, which itself might elicit some type of signal within the cell that shapes the behavioral response that we observe. So the specific question I want to address is whether the wrinkling phenomenon we saw with the mutant that couldn't make any of these electron shuttling phenazine molecules, is that consistent with an oxidant access strategy, as I've been building up to in this talk? So we might imagine that for the overproducer, it would be able to make a nice smooth biofilm because in the zone where oxygen occurs, it can use oxygen as an electron acceptor. That's shaded here in blue. But in the anaerobic portion of the biofilm here in white, it would be able to get by because it's shuttling these phenazine molecules. However, the phenazine mutant, you might predict, would spatially organize itself so as to access oxygen everywhere because it wouldn't have the option of recycling its own endogenous shuttle. So towards this end, we used microelectrodes to measure where in various strains the threshold between oxygen availability and anaerobiosis set in. And we found everywhere we looked that at a depth of approximately 200 microns, oxygen went to zero. So let's now take a look at these colonies in a little bit higher resolution. So if you're at a breathing room in Los Angeles, the idea is to spread out. Of course, you know the joke coming next. In New York, it's to build up. And if we now measure quantitatively the dimensions of these beautiful films, this is of the mutant, recall, that can't produce any phenazine, what you see here that's so lovely is that even at the maximum thickness between any 2 points, it's no greater than approximately 400 microns, which is consistent with the idea of oxygen diffusing in from any given side to a depth of about 200 in either case. So the prediction from this would be that if we were comparing the wild type to the mutant in terms of the depth to which cells could grow, we would see a difference in depth. And that's what we observe. So indeed, when we look here using transmission electron microscopy and measure where the viable cells are residing, we see in the wild type a much greater depth than we see in the mutant, which, recall, is unable to excrete these phenazines, whereas the wild type does. So this feeds the idea. And more importantly, we're also able to observe that it's really the redox balance that is being affected in this morphological response. Because if we compare now the morphology of the wild type to the mutant that can't produce these molecules to a different mutant strain that is defective in the ability to reduce the phenazines, it still can produce them, but it can't reduce them, we see a very similar phenotypic response. It's essentially choked. Even though it has the molecule there, it can't use it. But if we rescue it with the addition of a different electron acceptor so it can restore its redox poise, such as nitrate, it restores the wild-type phenotype. And the same thing is true for the mutant if we add either nitrate or piocyanin. So just to end, what I'd like to leave you with is the idea that this phenomenology that I've talked about in terms of Pseudomonas aeruginosa may be very widespread in nature. And some of the evidence we have of this comes from work we've done with Streptomyces silicolor, which is one of the most important antibiotic-producing organisms in the soil. Here you have a picture of actinorhodin. It's this beautiful blue pigment being produced by the streak of bacteria on the plate. And what we, again, were able to do was compare the development of biofilms of mutants of Streptomyces that were unable to make this redox-active secondary metabolite to the wild type. And again, we have a very similar phenotype. It's slightly different because this organism can produce spores, and that's the white stuff you see in the middle. But in terms of how it flattens out and wrinkles up and maximizes its surface area, it's identical to what we observe in a very evolutionarily distant organism, Pseudomonas aeruginosa. So just to conclude, the take-home message, I hope that you find of relevance to the environment in many different environments, is that when microorganisms are growing as multicellular communities on any surface, be it an iron oxide, a lung surface, a plant root, or an electrode in a marine sediment, in all of these contexts, as they develop beyond a certain critical size, they will become limited for oxygen. And it's in these type of environments that the ability to produce these so-called secondary metabolites might actually be absolutely essential for sustaining their metabolism. So with that, I'll end and acknowledge the people in my lab who did much of the work that I spoke about today. Here's Yuan and another postdoc in the lab at Cell Ramos Solis. They've both been working a great deal on the biofilm aspect of this. My student Mario Hernandez began the work with iron respiration Shewinella, but the two that have made the most important contributions have been a student from Caltech, Alexa Price-Whelan, and Lars Dietrich, a postdoc in my lab. And I've been very lucky to work at two great institutions, Caltech and more recently MIT, and also be supported by the Howard Hughes Medical Institute. So thanks very much, and I'd be delighted to answer questions.
Questions? Re-identify yourself.
Don Stedman again, the University of Denver. Your picture of this layer on the lungs showed the lung surface to be completely devoid of oxygen. That strikes me as a bad idea. Do you have thoughts about how that might be alleviated?
Well, so this I should say is the lung surface of cystic fibrosis patients. Okay, so this is not the typical lung surface that I have drawn. And the problem with the CF lung epithelial surface is that in the disease, there is a mutation in what's called the cystic fibrosis transmembrane conductance regulator. And that's a cyclic AMP-dependent regulator of sodium channels. And in the absence of a wild type, a normal version of this, this protein, sodium absorption accelerates. And because of this, sodium and potassium ATPase pumps aren't inhibited anymore. And so it leads to a large increase in oxygen consumption by CF epithelial cells. And so that's something different going on in the context of the lung than in a normal lung. Another important difference that's been shown recently, getting back to iron, is that for some reason that's not well understood, these mutated CFTR lung epithelial tissue cells excrete a lot more iron. And independently of anything I've told you, iron is a molecular signal for biofilm development. And so then it gets compounded because the cells colonize these epithelial surfaces better, they form biofilms, they scavenge more oxygen, and so all of this contributes to a very hypoxic environment.
Chris McNeil, Chris McNeil, University of Minnesota. I enjoyed your talk, Dianne. I was curious about these quinones. You mentioned that quinones are naturally occurring in the natural organic matter milieu, and that these bacteria can also produce quinone-like molecules. Is there any sense for whether one can come from the other? In other words, the stuff we find in humic substances, is there any sense that those are coming from these soil bacteria, or
yes,
are the...
They are, and that's been shown by many others in this field. One of the best examples is the work of Dianne McKnight at the University of Colorado at Boulder, I believe, right, Francois? So she's been saying this for years, and it's been shown that depending upon which environment you isolate the humics from, they're either derived from the degradation of plant matter or microbial matter. Natural products that are produced by plants and microbes together wind up coming together in the soil to form these really complex structures. So
so I guess the question I had is just a little bit more specific, which is that the so-called terrestrial organic matter, which is largely derived from soil, the vascular plants contribute to that pool, of course, but then you also have microorganisms in that soil as well. And to what degree are the microorganisms responsible for the terrestrial component?
Oh, I see. I don't know quantitatively, no number to put on it, but I would, of course, and I'm sure you would agree, assume that the microbes, through an indirect way, are very much affecting the ability of the plants to excrete what they're putting into that terrestrial environment by providing them with critical nutrients, for example, even if it's not through some direct transfer of these molecules from one cell to the next.
Charles Dismukes, Princeton. Very nice talk. And I don't know much about these particular microorganisms, but I know others, the phototropes, the microbial ones, that if you add molecules like this, you actually catalyze the production of superoxide, and that kills the cells. Whilst here, you're talking about endogenous antibiotics that are actually rescuing the system. So I presume that death by addition of exogenous antibiotic could occur by an oxygen activation mechanism as well, although I don't know that's the case here. But is it the case, and how do you separate that death from the rescue?
It very much is the case. And what's really quite interesting is that these organisms have evolved very complicated strategies to protect themselves against their own... Oh, sorry. Okay. Thanks, Francois. So the very interesting thing is that these organisms have evolved many complicated strategies to protect themselves against the generation of superoxide by their own endogenous molecules. And it includes producing proteins that specifically sequester these molecules within the cell to minimize their activity. The other thing is there are specific efflux systems that recognize these molecules that tightly control the amount that's within the cell. And the third is that they produce extra copies of superoxide dismutase to help quench any reactive species that escape those other two mechanisms. Now, if you add a different compound, it's not the endogenous one, like methylviologen, for example, then they die. Then they're in real trouble because the enzymatic machinery has evolved over the years to be very specific for the ones that they themselves make.
One or two more questions before lunch, perhaps. That's some questions, especially for Dianne afterwards. Thank you, Dianne. We're doing this session quite on time now. See if I can mix the time, that's all.
My order. So please come back. Welcome to the second session. We're going to gear toward chemistry. My name is Beatrice Renaud. I'm the Senior Science Advisor at the New York Academy of Sciences. And as you can hear, there will be some continuity with François, at least in the accent. And I'll try to do a very good, as good a job as he did in keeping on time. So I'm going to be introducing the next two speakers, and Paul Anastas is actually called the father of green chemistry. He coined the term in 1991, and is currently the professor in the practice of green chemistry, and he's also the director of the Center of Green Chemistry and Green Engineering at Yale University. And the title of his talk today will be Transformative Innovations Needed by Green Chemistry in Sustainability. So please welcome Paul.
Well, thank you. This is a wonderful honor. Thank you, Mark. Thank you, Dorothy, for having me. Thank you to the New York Academy of Sciences. This is an enjoyable opportunity. I've been having a wonderful day this morning, listening to all our talks, and I'm going to try to focus on this emerging area of green chemistry. Some of you may be more familiar with green chemistry than others. But it really does boil down to part of the very nature of chemistry and why so many of us in this room love chemistry, which is that it has two components to it. There's certainly the aspect of chemistry that studies the world as it is and seeks to understand the world as it is. And that has largely been how environmental chemistry has been perceived historically, of trying to understand the different chemical processes that are taking place in the natural environment, and also how our environment is being impacted by humans. But there's the other part of chemistry, the creative or creating side of chemistry, that introduces new substances into the world, substances that are the basis of our economy and our society. And those, of course, have a significant impact on the world. And thinking about how these substances are going to be able to be designed, manufactured, modified, so that they are fundamentally sustainable, is what I'd like to chat with you a little bit about today. Because when we step back and take a look at some of the grand sustainability challenges, we can all come up with our own list. But certainly the great challenges of energy, moving to renewable and sustainable sources of energy, water quality and quantity. Obviously, we've heard some very important talks on climate today as well, health, food production, and toxics in the environment. So we all know that these are the great challenges that need to be addressed. Yet we also recognize that simply addressing these problems is not enough. In other words, we've seen so many attempts to address these problems where you're doing the so-called right things, but doing them in a fundamentally flawed and unsustainable manner. In other words, we all want to think about how we move toward renewable energy, but I think there'd be general agreement that from a long-term sustainability perspective that perhaps bio-based ethanol has some challenges. We all want clean water for health reasons, but we know that if we clean our water with particular lethal substances, that might come back to haunt us on a variety of levels. If we're looking at energy saving even in our lighting, We've actually recently published a paper on how the mercury content from the lighting may exceed the mercury released by coal-fired power plants, depending on the nature of the energy grid. And of course, when you're looking at, as we all want to move toward renewable sources such as photovoltaics, our choices of the materials that we design may actually be the dominant factor if they're precious, rare, toxic photovoltaics. So what do we think about when we step back and think about how we design our chemistry, and how do we ensure that we're looking to do the right things right? Well, this is the basis of what the principles of green chemistry strives to do. How it looks at the fundamentals across the life cycle and the inherent nature of our feedstocks, our transformations, our target molecules, our separations, so that they are fundamentally sustainable from beginning to end, and thinking about resilience. Knowledge of what makes a system resilient, not just in order to describe it, such as with an ecosystem or the internet or an energy grid, but understanding the fundamentals of resiliency enough to use it as a design tool as we implement our next generation products, processes, and systems. And how this is going to be needed in order to bring about transformative generations. Why transformative innovations? Because I think everybody in this room appreciates that when we're looking at the unsustainable trajectory that we are on as a civilization, incrementalism won't suffice. A 25%, 50% efficiency increase is not going to bring about the sustainable trajectory. The Varganagel calculations out of the Wuppertal Institute would suggest that if everybody lived at the same level of development as we in the United States, Europe, Japan, that you would need at least 4 Earth equivalents in order to supply the resources for that state of development. Now, we're not going to get another 3 Earth equivalents, and so how do we understand the basis of our material and energy? And that comes down to this one-sentence definition, which is the design of chemical products and processes that reduce or eliminate the use and generation of hazardous substances. Hazardous being defined as adverse consequence, whether it be physical, whether it be toxicological, or it's global. And so this design paradigm has been playing out over the past 50 years, and it has met with widespread adoption both in industry sectors and the scientific community. Just the tracking of the successes by the Presidential Green Chemistry Challenge Awards talks about how a train car 100 miles long of hazardous substances have been eliminated by just the winners. And this has been duplicated in the UK, Japan, Italy, Australia, etc. We're looking at whole industry sectors, pharmaceutical sector, electronic sector, cosmetic sectors, that are crosswalking their R&D portfolios around principles of green chemistry, and we're now seeing this moving into legislative and policy initiatives, and even our NAS, when it looks at the beyond the molecular frontier, is saying we're not only looking at the manufacturing plants, but also how we are looking at the products themselves, the target molecules themselves. So I don't put this up as an eye chart. I say that these 12 principles of green chemistry, if we were to talk them through, would be all about understanding the nature of our feedstocks, whether they're depleting or renewable, the efficiency of our transformations, whether they're atom economical, whether the nature of our separations, the energy we use, the target molecules, whether they're degradable, toxic, etc. And at the end of this discussion, we'd say, is this straightforward? Yes. Is this common sense? Yes. Are these principles almost trivial? Yes. They just happen to bear very little relationship to how we do things today. When we take a look at how we are functioning today, we recognize that there are whole industry sectors just on cleaning up after wasteful syntheses. We understand that everyone in this room has persistent bioaccumulating substances that are building up according to the CDC, all of us, every newborn child. But I'm not waving my hand saying that we're all going to die and this is an unacceptable risk. What I am saying is that this is a design issue that we as chemists know how to design against. We know how to design for degradability. We know that the vast majority of our synthetic materials, when I say vast majority, I'm saying between 96, 98%, depending on which numbers you believe, are depleting rather than renewable. And that many of our issues with regard to safety, security, accidents, and sabotage are dealt with either through engineering and security barriers rather than through a fundamental rethinking of how we carry out these transformations. So I go through this general introduction to give you an overview perspective on green chemistry and how this is a shift from how we've thought about things previously, and shifting it from the circumstantial way of dealing with issues of the environment to intrinsic. What do I mean by that? We've changed the way that we use our chemical substances, the way we handle, the way we transport, the way that we treat and protect people. We put smokestack scrubbers on smokestacks, have people wear protective gear, and all of these approaches to control exposure to chemicals necessarily have two things in common. One, they can, and as a probability function, will fail. And when they fail, the risk goes to its maximum because you haven't addressed the hazard side of the equation. Second, they all necessarily have to be a cost drain. They cannot add performance, they cannot add capabilities, they cannot add efficiencies. When we contrast it with the green chemistry approach, what we're talking about is at the same time that you're redesigning the molecules of the transformation so that they're environmentally benign and more sustainable, you can impart that efficiency, that capability, that new performance into these. And this is why, by building together the inherent sustainability, it will also meet, in many cases, the economic goals that companies are interested in. So what I'd like to now shift into is a discussion of some of the scientific innovations, first generally, and then in our group, and in our center. So when we look at some of the innovations that have taken place over the course of the past decade, it's very broad. I'm old enough to remember when people were saying, "Oh, green chemistry is all about solvents." Then it was green chemistry is all about organic synthesis. Then it's green chemistry is all about catalysis. Then it was green chemistry is all about nanotechnology. And after a while, you start realizing that green chemistry is all about all of these. That it affects the design and generation of some examples shown here. Everything from supercritical fluids all the way through some of our most elegant catalytic work that's too numerous to mention. So I'd like to focus down on some of the specific research that we have going on in our labs at the center, and want to emphasize that, because I'd like to talk about some of our work, that there's certainly quite a collection of work by other research groups throughout certainly chemistry, chemical engineering, our School of Forestry and Environment, everything from some of the wonderful work being done by Brudvig, Crabtree, Batista, and Schmuttenmeyer on some of the photosystem 2 mimics that we'll hear a lot more about today. Some of the wonderful work being done out of the Elamelic group on forward osmosis and new energy-efficient ways of water purification. Some of the excellent work being done on microbial hydrogen generation out of the Petchia group. So there's quite a collection that spans various schools at Yale, but I'd like to just take a little time to talk about some of the work that we're doing in our labs right now and tying them to some of the great sustainability challenges. So right now we are stepping back and saying, how do we address some of the challenges of healthcare? Most people don't have a full appreciation that on average, when you're generating, let's say, a pound of a pharmaceutical, on average you're generating about a ton of waste, much of it biologically active, much of it hazardous. So how do you recognize that even such groups as the ACS Green Chemistry Pharmaceutical Roundtable looks at top 10 reactions that are in need of reinvention from a green chemistry perspective? Well, some of the strategies that we've been taking involve a new look at the benign reagents, coupling, cascading and tandem reactions, and ensuring that we have minimal separation. So we take a look at some of the targets that we're focusing on, and rather than saying how do we look at a specific target and develop or demonstrate a particular synthetic methodology, we look at what are the strategies that are going to open up more skeletal structures, more systems for a wide range of targets that we can control and manipulate as the reaction proceeds. So if you see some of these different molecules, some may look similar, some may look very different, important targets for varying reasons. Looking at how do we use the same approach, the same set of reactions that will give us a wide diversity if we just simply tweak it slightly. I'll go through the example of an old favorite of mine. I say it's an old favorite, retrocondensin, because 20 years ago, over 20 years ago, I had the first synthesis of this natural product that was important to one of our pharmaceutical companies. And it was approximately a 12-step synthesis, and I think the yield was in the low single digits, and I was very, very proud and happy. So we said, how do we revisit this in a different way? And one of the things that we're looking at is a multi-component coupling, cycloisomerization. In this case, we're looking at bringing together 3 components and a one-part synthesis. By looking at this transformation, we're able to generate a wide range of skeletons, some with induced rearrangements, some not requiring rearrangement, and we have been able to generate the core of all the colored emphasis on each of these molecules seems to have has disappeared, emphasizing how the core of these different molecules is generated by this coupling and this controlled cyclization. Leaving that as it is, we're able to access each of these molecules with the exact same coupling. When we move from the enine to the diine, we are also able to generate these structures. You'll recognize the parent of the retrocondensin shown here. Now these are this recently published work on the retrocondensin backbone. These are yields that one would normally apologize for, of 41% and 25%, until you look at a comparison between a one-step versus multi-step synthesis, one isolation, and you generate 2 natural products in this one step. We've opened this up to a wide range of this family, and are able to get these in significantly improved optimized yields. A second area that we're working in outside of synthesis is materials. So Right now, as I mentioned, the vast majority of materials that we're using in our economy are synthetic materials, are petroleum-based, and in order to impart the properties that we want from these materials, it requires the use of additives that are in the news on a regular basis. Whether it's Arnold Schwarzenegger banning phthalates, or the bans coming out of Europe as well, whether it's bisphenol A that has the Food and Drug Administration and the National Toxicology Program at war with one another. There's a wide range of these additives that make some of the materials that we use of high concern. When we look at PVC, some of the ways that we achieve plasticity of our PVC with phthalates are linked to very serious questions of endocrine disruption. And so, while it's easy to talk about we need to move to bio-based polymers, in order to have these polymers, whether it's polylactic acid or the polyhydroxyalkanoates, in order to have these polymers have the properties that are going to allow them to get into market, we're going to need to be able to manipulate their properties. One of the projects that we have going in my lab, along with the Asuji lab at Yale, is how do you build the, in some cases, plasticizing properties or other properties that you're trying to induce, build that into the polymer matrix rather than having additives that are going to leach out, bioaccumulate, and cause problems. The example of one system that we're developing is shown here with this genericized scheme and the specific application. This is largely stealing from the field of liquid crystal display manufacture and imparting properties on these polymers so that you can tweak them with various either electrical, light, thermal, other impulses in order to bring about the properties when and in the time frame that you want. We're also looking at chitin, the second largest material made in the world after lignocellulose, how you manipulate chitin in order to get the properties through the manipulation of the functionality there, whether it's the amine or the hydroxyls. One of the things that is going to be extremely important is as we go to the naturally based plasticizers, such as the citrates and the sorbitols, etc., how you are able to control this while using substances that are only generally regarded as safe by FDA, especially if you're looking at food packaging. So we look at some of the approaches where we're starting with either such substances as candle nut oil or soy, and going through fairly straightforward manipulations of epoxidation and acrylation with some of these grass substances, and are able to make very high strength composites that, along with our collaborator Richard Wool, are being used in structural features, everything from building materials all the way to panels and automotive usage. So we move on to our third area of renewable energy. Renewable energy is obviously one of those great challenges. And when we step back and take a look at our current approaches to some of our bio-based energy, we recognize that when it's competing with cropland, when it's impacting food prices, when the procedures that we're using in order to grow these crops are unsustainable, and with some of the approaches that are the papers that are coming out in Science about the net carbon production from some of the biofuels approaches, for instance, in Indonesia, Malaysia, etc. We recognize that, are we doing the right things right? So what green chemistry approaches might be able to be used? Well, we're working on a project primarily in Uganda and Ethiopia where we have about 10,000 hectares of land and working very closely with our School of Forestry and Environmental Studies, our sustainable forestry capabilities on how do you take this and make it into a sustainable system. Now, if I were to say we're doing the plantings of Jatropha, Castor, Simaruba, etc., and we're getting carbon credits for this project, you'd say, oh, that's a nice climate project. If I said that we are planting these in some of the most arid parts where nothing has grown for millennia and stopping the encroachment of the desert, you'd say, well, that's a nice anti-desertification project. If I said that the seed value, the oil of the seeds, has 4 to 5 times the energy value of soy, I'd say, oh, it's an interesting bioenergy project. If I said that we take the seed husks, dry them, grind them down, use them as natural coagulants to purify very turbid water, you'd say that's an interesting water project. If I talk to you about the phytopharmaceuticals that we harvest from the leaves and use to combat malaria, you'd say that that's an interesting healthcare project. And the point is that this is a hopefully interesting and important sustainability project. And understanding how to step back and look at these interactions as a complex system and beginning to ask those right questions is what this project is most geared toward doing. Now, I'd like to finish up with the fourth area, the one that is just being launched, one that we're perhaps most excited about. That as we look at, when we look at the evolution of toxicology, we know that it has evolved from simply a descriptive science to a mechanistic science, that we move from just knowing that something is toxic to why at the molecular level it can follow a mechanism that makes it toxic. Because of this, it gives us the design handles that we need as molecular architects in order to design things differently and move toward preventative toxicology rather than just simply predictive toxicology. We also know that in order to receive a PhD in chemistry, there is no requirement for understanding the molecular basis of the consequences or the potential consequences of the tools of our trade. And so is it possible, what we ask is it possible, with the advances that are being made in toxicology and toxicogenomics and molecular understanding of toxicity, can we stand on, I'll use the phrase, on the shoulders of giants from the pharmaceutical field that has given us an understanding of the mechanistic basis of biological activity in order to create a framework for those chemists that are making the other 99% of molecules that are not pharmaceuticals, that are not drugs, so that we impart the properties that we want, that we impart the performance that we want of these chemicals without, at the same time, imparting the hazard and the unsustainability. So that's the challenge that we're taking on, recognizing that we are swimming in data that's currently being generated from some of the high throughput screening, the in silico predictors of toxicity, the genomic signatures, and all of these are of direct relevance to molecular design. Yet the connection between this collection of data and the informing of how we make the next generation of adhesive, the next generation of dye, the next generation photovoltaic is not being incorporated. And so we look to try to make something transparent, accessible, and recognize that as we go from understanding of toxicokinetics and toxicodynamics, understanding how to manipulate bioavailability, to structure-activity relationships, all the way up to mechanism of action, that each one of these approaches gives us a design handle. Each one of these, as we increase in level of complexity and in many ways difficulty, we are able to make impacts on how to design next generation of substances. If we want to look at solubility, certainly manipulating octanol water partition coefficients, blood-brain barrier transport, all the way to gas partitioning in the lungs. If we want to correlate this, the important work of Bill Jorgensen at Yale and rational drug design is a wonderful platform that instead of how do we manipulate a drug so that it is able to get into our bodies, is able to cross the necessary biological membranes, is able to make its way to a target molecule, is able to bind to a particular receptor in order to cause a therapeutic biological effect. We want to tip that model on its head, build on the Jorgensen-type models, and say, how do we design it so that it's unable to make it into our bodies, cross the membranes, make it to the organ, and not bind to cause a toxic effect. And so we look at some examples of manipulation of things like molecular weight and how those are going to prohibit the ability of the substance to get in and cause that adverse toxic effect. We look at the example of how volatility, simply controlled, a basic parameter that we all know how to manipulate, and yet will have a dramatic impact on whether or not something is going to cause human health and environmental damage as well. We look at examples of how this can and has been used. We recognize that through understanding manipulations, in this case of this cephalosporins, that by using the zwitterion, this is going to be directly linked to the organic anion transporter and whether or not it's going to have biological accumulation in the cell, where if you instead switch to the anionic analog, it's going to move from the blood into the urine, not bioaccumulate, and therefore reduce its neurotoxicity by 6 orders of magnitude. So as we look at this approach, we have the ability to control structure-activity relationships on a wide range of reactive functional groups, and by avoiding, masking, manipulating these reactive functional groups, we're able to dramatically control the adverse impact on the environment. This example of glycidyl ethers, well, I find structure-activity relationships obviously very frustrating because they don't give you the type of mechanistic detail. They do give us guidance that when you have certain correlations, in this case, length of the chain associated with myocardial effects, and in this case, the length of this particular glycidyl ether associated with testicular lesions. You have the design handles, and these are transparent to synthetic designers. Of course, at our highest level, it's all about mechanism of action, and while it gives you far more design options, far more design handles, and it also is a reality that the vast majority of our toxic effects do not have well elucidated MOAs, much less the full mapping of the key events at which structural interventions can be made. But as the genomic data, the toxicogenomics comes in, we are able to constantly evolve and have more design options, so that rather than simply trying to control the circumstances of our chemicals, we're able to design the character and the inherent nature of our substances, regardless of their end performance. So I'm going to just conclude with some of the big questions that are certainly going to be facing green chemistry. If we're going to use chemistry in a way that's going to move us onto a sustainable trajectory. When we look at our feedstocks, will our highest value applications be what we tap into for our limited, finite, depleting resources, and for the vast majority of others, we'll use renewable resources? Are we going to be able to evaluate synthetic design, not simply by Yale, but the degree to which our our starting atoms are incorporated into the final product? Are we going to be able to design our catalysts from first theoretical principles and make them multifunctional and also designed for self-separation from product? When we think about our solvent systems, are we going to move beyond simple mass and energy transfer reaction medium and instead design some of these substances to be catalytic and enhance separations? And will we design our solvents so that they are obedient and change properties upon imparted stimulus? When we think about how nature carries out many of its transformations, rather than making our substrates more and more functionalized with reactive functional groups, our reagents more and more reactive, knowing that reactivity is, of course, closely linked to toxicity, are we instead going to continue to develop how you impart reactivity at the time and the place that it's needed, much like nature does? And will we move from our command of the covalent bond to a command of weak force interactions, not just simply to explain properties or explain reaction pathways, but as a design tool to impart properties and impart reaction pathways? And finally, I just want to finish up with, will we understand the molecular basis of hazard, and will we be able to design to minimize that toxicity rather than just simply measure how toxic something is? And finally, will we be able to complement our reductionist understanding to an integrative system, because what we're dealing with complex systems that need a systems and integrative approach. With that said, I'm not suggesting that these are problems that are not being worked on at all, just that these are problems that are crucial and not being worked on in, quite frankly, in most of the mainstream challenges that we're facing. Thank you for your attention, and I'll be happy to answer questions as time allows. I actually didn't run late.
Should be 3. That's good. Okay. That's good. Okay, thank you. Paul's talk was so good that I was willing to cede my time to him, but then he did it. No, I'm just kidding. It was perfect. And it was a perfect setup for my my lecture. Sitting here this morning really wondering how I could give a lecture in the same symposium as Jim Anderson. I've been in the same room as Jim before. We're colleagues, but it's really a special scientific opportunity to actually have a topic that brings us together. I'm an organic chemist, and I'm interested in sort of what you might call advanced organic reactivity, making complicated things. And Paul has really introduced a lot of the key topics that I need to use, concepts I need to use in my lecture. One is that synthesis of complicated molecules, and when we talk about complicated molecules, to a significant extent, those are pharmaceuticals. Not necessarily, but often pharmaceuticals. That synthesis is very inefficient. I think Paul used the number that a ton of waste is generated for every kilogram of product. You see different numbers, and of course it depends how you calculate it, but there's no question it's an enormous amount of waste. And you might think, well, it's not that big a deal because pharmaceuticals really correspond to a small amount of the total chemical product that's generated by the world. And that is true. Relatively speaking, pharmaceuticals are produced on a ton to 1,000-ton scale per year, whereas bulk chemicals and certainly petrochemicals are produced on orders of magnitude times greater scale. But the efficiencies associated with these syntheses are really dramatically different, such that depending on how you calculate it, and the numbers are ranges, of course, but depending on how you calculate it, there is about as much waste generated, chemical waste, from specialty chemical and pharmaceutical chemical synthesis. And again, Paul, I think, framed it very nicely, and I think you can ask, why is that? I think there are two explanations. One is that the molecules at issue are very complicated. Now, some of them are drawn from nature directly, from natural products, and they can be isolated and maybe manipulated with relatively little chemistry associated. So a lot of the drugs that you think of, things like tetracycline, penicillin, these are really complicated molecules, but nature gives them to us, or at least close to final form. But others are completely synthetic. And a great example of that are the HIV protease inhibitors, of which there are several on the market currently. These are 5 examples. And if you're not an organic chemist, hopefully still you can look at these and appreciate that these are complicated structures. They have not just a lot of atoms, but a lot of complexity in terms of functionality. These wedges forward and back, this is important to my lecture, these correspond to 3-dimensionality, to stereochemistry. They have what we call stereochemical complexity associated with them. And their syntheses are very difficult, involving many, many steps. And inevitably, when you have a lot of steps, you generate waste. There's another reason, I think, though, and that's, again, one that Paul touched on very nicely, and that is that really the pressure to be efficient hasn't been part of our culture, part of the organic chemistry culture. If you remember any of your sophomore organic, one of the reactions you would remember is the oxidation of alcohols with chromium reagents. And this is something we still teach. And the reason why we still teach it is because we still do it this way. Chromium reagents continue to be used to oxidize alcohols. And this is an important kind of transformation. It's something that has to be done. It is, on so many levels, a horrible process. Not just because it's inefficient in terms of the waste that's generated for the transformation that's being done, so you can calculate that in different ways, but by really a conservative analysis, you'd say that you're generating more waste than you are product. That ignores solvent and all these other elements as well. But on top of that, you're dealing with very toxic materials. You're dealing with stoichiometric generation of things that have to be disposed of, that cannot be recycled easily. This is really ugly chemistry. And so how did this develop? How did it come about? Partly it's because it really did answer the task at hand, which was, in the world in which these reagents were discovered, people didn't worry about disposal. People didn't worry about environmental issues and toxicity and things like that. Well, toxicity, yes, but people learned how to be careful as opposed to avoiding it. And this is a nice example of something that really could be fixed, because you can think about the same transformation in an extremely efficient way. You need some sort of sink to absorb the electrons, to provide electrons, and to take the hydrogens off of the alcohol, ultimately to carbonyl. And one very nice way you can imagine doing that is by reduction of O2, generating water. So here, not only do you have much better efficiency, but of course you've got a byproduct that's a lot more friendly than in the first case. And certainly over the last several years, there's been a lot of effort directed toward discovering catalysts for this, but it's relatively recent effort compared to the long history that chemistry like this has. So I think it's just a matter of appreciating the principles that Paul laid out. Now, Paul points it out that catalysis is just part of the puzzle, so I guess the slide, I would have changed it if I had my laptop in front of me, but it's not all about catalysis. Of course, there are many other issues that are important to green chemistry, but catalysis, I'd say, is very much at the heart. Catalysis and efficiency are almost synonymous, I think, in synthesis of any complexity. So if you'll allow me, I realize that for many of you this is almost insultingly basic, but if you'll allow me to just talk about some elementary principles of catalysis. Of course, catalysis is a kinetic phenomenon. What you're doing is lowering the activation barrier to a transformation, starting materials to product. That's conveniently represented in what we call potential energy diagrams. These are sort of simplistic ways of representing a reaction progress. You can also think about catalysis, and we do in our molecular context, as a sequence of reactions that happen to end up where they started. Okay, so a catalyst is something that does stuff but then is regenerated unchanged. Okay, and of course, along those changes is the conversion of two starting materials to a product. So these are fundamental principles and sort of guide then how you think about discovering and designing a molecule that can achieve this kinetic the lowering of the kinetic barrier to a transformation of interest. Another useful principle in thinking about catalysis is one that Linus Pauling introduced, and that is the idea that what you want to do in accelerating a reaction is essentially lower the energy of the transition state leading to the product. So a way of thinking about that is binding of a transition state and stabilizing a transition state through that kind of binding. That's sort of an abstract concept because transition states, of course, have fleeting existence. The idea of binding a transition state is a very abstract concept, but it's a useful one, certainly in terms of thinking about mechanistically what is at issue in accelerating a reaction. Okay, that's the simplest context. Almost always what you're dealing with in catalysis is not a simple acceleration, but an acceleration in the context of other possible things that can go on. So for example, if you think about methane to methanol conversion, one of the great problems of modern chemistry. Methane to methanol conversion is very, very easy. It's one of the easiest transformations you can do. The problem is that it's almost impossible to stop at methanol. Okay, so getting to partial oxidation of methane is trivial. You can do that with a match. The problem is stopping it from going to carbon dioxide. So this is a great challenge of what we'd call selective catalysis, which would be to lower the activation barrier to a desired product of an intermediate along a more complicated sequence and stopping at that intermediate. In other words, not accelerating the subsequent steps such that you can stop there. That's a terrific problem and one that defines what you would call selective catalysis. Another variant to this idea of selective catalysis is where you've got two starting materials that could go to two different products, primary products, and you want to form one instead of the other. And where, in principle, there isn't much preference, so that selectivity would be determined in the absence of a catalyst by these two barrier heights, and a selective catalyst would lower the barrier preferentially toward one relative to the other, such that you can make one selectively over the other. Okay, this all assumes kinetic control, in other words, where the reactions are not reversible, not at equilibrium. So this is really what we do in my group, and we do it in a particular context. What we do is try to design catalysts that are selective, choosing between two pathways, and the two pathways at issue are forming the two hands, mirror image related hands of a particular product, an enantiomer products. And the reason I'm sure almost all of you know is that most of the molecules of life are handed, and their handedness is directly tied to their biological activity. So it is important to control the handedness. In other words, if you're making a pharmaceutical that's handed, left, right-handed, you can't just make it as a 50-50 mixture because the two hands will probably have different biological properties. And there's, of course, a long history associated with learning about this issue, which I won't go into. Now, this is an interesting fundamental challenge because, by definition, the two hands of a molecule, the two enantiomers, are equal in thermodynamic energy, and if the transition states leading to them are enantiomeric as well, in other words, left and right hand relationship, they'll also be equal in energy. So the only hope, again, of achieving selectivity, in what we call enantioselectivity, is to introduce an external chiral influence and selectively promote one pathway relative to the other such that you preferentially form one product. This is not a new concept. This idea has been around for decades. A Nobel Prize was awarded to this field several years ago to Sharpless, Noyori, and Knowles. But it's a field that continues to thrive because it's still at an early stage. It's at an early stage for many of the reasons, again, that Paul touched on. One is that we still don't know how to design catalysts very well. It's still a very, very difficult thing to do. There's still very few reactions that are done well. And there's a lot that can be learned from catalysts that do work well. And, of course, on top of all that, if we do discover these catalysts, they can solve important problems in terms of efficiency. So why is it so hard to do? One very simple reason is that the energies that you require to achieve the types of selectivity that you want, the selectivities that you require, are differences in transition state energies. Again, these are things that are hard to see, hard to calculate, hard to know with any sort of certainty. They're almost always understood by inference. And the energy differences are quite small. So to achieve what we call synthetically useful enantioselectivity, which is over 90%, which means a 19-to-1, 95-to-5 ratio of enantiomeric products, the energy difference in kilocalories per mole is quite small, in the order of 1 to 2 kcals. And even an extraordinarily selective reaction, one that gives 199-to-1 selectivity, would have only these energy differences in kcals per mole. So That's good in a sense. It means you don't need a lot of enantioselectivity to get a good reaction. The flip side is it doesn't take much. It's hard to understand these small energy differences, and it takes a lot to try to design around that. Okay, so thanks for allowing that sort of protracted tutorial on this topic. What I'm going to do initially is just show you a couple of examples of reactions that we developed a few several years ago, that I think fit this description of sort of efficiency in the context of enantioselective catalysis and did serve to solve problems. And then I'll talk about a newer set of projects, a particular new direction that I think might hold a lot of promise for future discovery. So this is a molecule I showed earlier. This is one of the HIV protease inhibitors, the one that Merck developed. And it really is a famous molecule in the circles of organic chemistry and pharmaceutical synthesis because of its complexity. It's not the biggest molecule that you'll ever see, but it stands out because of its stereochemical complexity and the fact that it is completely synthetic. There is no piece of this that comes conveniently from a natural product. One piece of this, it turns out, in red, which every piece is crucial to this molecule, but one piece that was in red, it's known as aminoindinol, is actually the starting point for the synthesis. And Merck was developing the synthesis of this drug at around the same time that my group happened to develop a reaction that allowed for epoxidation, conversion of alkenes to epoxides in an enantioselective manner. And it actually was applicable directly to the substrate of interest to them, and they were able to use it. It was one of these sort of happy coincidences where really within months of our discovering the reaction, it was applied in a significant context. And then they did a really beautiful job of what we call process chemistry to convert that epoxide to the desired amino alcohol. And this really does illustrate some nice green principles in the overall transformation, taking a coal product, indene is a coal product, to a very valuable chiral intermediate. It's 3 steps, depending on how you count, but the really key thing is the reagents are inexpensive, non-toxic, environmentally friendly, and the byproducts are few and also friendly. So this actually was interesting on a lot of levels, partly because when this happened, this was really developed in the early 90s. Nobody was talking about green chemistry. There was no issue whether this was green or not. Really, the thing that mattered here was that they needed to make as much of this compound as possible, as quickly as possible, because they needed to do the clinical trials of this molecule in an expedient way. And as it turned out, this synthesis, because of its inherent efficiency, allowed them what's called greater volumetric throughput, allowed them to make more product in a given amount of time with the equipment that they had. And that was important. That translated to actually saving lives, more people getting the drug on time. So it's interesting that these principles that, again, Paul outlined so nicely, there's an inherent sort of common sense to them, and that is that the more efficient the chemistry, the better it is. It's just that these pressures of waste minimization, efficiency, volumetric throughput really hadn't been emphasized before. And this just illustrates sort of how this was discussed. This particular example was sort of held up, again, as sort of a very practical thing. Essentially, this is an old slide that was used in Congress to describing this chemistry, and was really talked about in terms of economic benefits. And I show this slide only to point out how, with all this stuff, sort of sales pitch stuff, to try to explain how to Congress why it would be a good idea to fund this kind of research, there's no mention at all of green chemistry, because at that time it really wasn't considered a priority. This was sort of, the green aspect was really sort of a secondary, unanticipated benefit. Now we appreciate, I think, much better that the green component, if we had put that up front, all of these other things would have followed. This is another reaction that my group has developed, and it's another example sort of efficiency in a significant way. This is a method that is very simple. It takes an epoxide that's racemic, meaning that there are 2 enantiomers, left and right hands, in this mixture, and with water as a reagent, takes one of the 2 enantiomers to a product. It opens the epoxide to this dial, leaving the other one behind. And it does so with almost perfect selectivity, such that both the product and the starting material can be isolated in close to pure form. Now, why do I show this example? Partly because it solved the problem. This is a useful chiral building block that was being synthesized at the time from lactic acid in several steps with a lot of waste generation. And inefficiently, this was a lot more efficient way of doing this. But it really does sort of have extraordinary green properties to it, even though it's a resolution, even though you're making a byproduct. Okay, that byproduct is very valuable in and of itself. The separation is very easy, very low energy. The volumetric throughput is perfect because these reactions are done in the absence of solvent. All these elements that allow for a low-cost process and a very environmentally friendly process. On top of that, the catalyst itself involves a non-toxic metal, relatively simple molecule, and one that can be recycled. Now, we did a lot of work on this reaction to try to understand how it goes, and I won't tell you that story except to say that oops, doesn't like that slide there. That we did glean some real insight into the mechanism of this reaction and learned that it involves two metals coming together in a cooperative way, one to activate the epoxide, which is shown here, and the other to activate the water that's shown here. That insight allowed us to design better catalysts by linking them together in specific ways that were extraordinarily efficient, such that we can now, instead of using, as we do here, on the order of a tenth of a mole percent, so 1 part per thousand or 2 parts per thousand catalyst. With the newer catalysts, we could use parts per million or subparts per million catalyst. So not only, again, is it an efficient process, but very efficient from the catalyst point of view. And it could be applied to a number of different products. And again, I realize for this audience, a lot of this is not that useful information, except I'm trying to impart on you the notion that this is a general catalyst, something that can be used to make a lot of different products. The ones that I've boxed are ones that have been carried out in a commercial context. There's, as I showed you in the initial example, there's a connection then to pharmaceutical synthesis. This particular one is manufactured on over 50-ton scale per year by this company Daiso in Japan, and this is the plant that does it. And again, the advantage to this chemistry is that it really produces very, very little waste because no solvents are used. The products and the product and byproduct are both valuable, and the catalyst is recycled. Okay, I'm going to spend the rest of this lecture talking about a newer direction in the group, and it's one that's as fundamental as it gets when it comes to catalysis. If you remember anything from catalysis in terms of enzymatic chemistry or zeolite chemistry or things like that, the catalyst that you most often see is the simplest possible elementary catalyst, and that is H+, the proton. The proton is an extraordinarily effective catalyst, and that is because when associated to all sorts of different kinds of molecules, including classic organic molecules like imines, carbonyl compounds, epoxides, or alkenes, the proton in association with those compounds generates a highly reactive intermediate and increases the reactivity in a very significant way. In each of these cases, to make what we call a very electrophilic species, something that wants desperately to get electrons to react with a nucleophile, and an enormous amount of organic chemistry follows from this, from proton activation. And the proton is good about then coming back off to recycle, in other words, to be used in a catalytic way after it's done its work. So a question that we've been asking ourselves over the past several years is, can we do selective chemistry with the proton? Can we, protons are known to catalyze reactions, to accelerate reactions. Can we sort of harness that reactivity in a selectivity context, and ideally in an anti-selectivity context? And to make a long story short, that's a very hard thing to think about doing because of the very reactive nature of these species and the fact that they really don't have anything to hold on to. They normally, when you think of a catalyst binding to something, you think in terms of electrons being available to bind to it. These things lack electrons. They're electrophilic. Okay, so how do you bind, how do you activate something that's as reactive as these species? And the answer didn't come to us immediately, but the answer, as it turns out, is very obvious in retrospect, and that is, for every cation, there's a conjugate base. There's an anion associated with that to balance the charge. And if you bind that anion with a chiral catalyst, and you can induce communication between this ion pair in appropriate ways, you could hope to impart selectivity on reactions of these reactive species. So the problem then becomes one of binding anions, and if that's a doable proposition. And it turns out that there's been a fair amount of work in the molecular recognition field around anion binding. And one of the more interesting results of that is that hydrogen bond donors of various types, and in particular ureas and thioureas, are very good at anion binders. And when I say very good, I mean that they can bind anions that really have almost no basicity associated, no Bronsted basicity, things that don't really want a proton associated. Chloride is a very weakly basic compound. HCl is a very strong acid. Yet this molecule, this urea derivative, binds Cl- very, very efficiently, even in polar solvents. And people have recognized this for years, and based on that, people have designed sort of receptors for anions based on the thiourea, that's a sulfur like by 2 nitrogens, this functional group, or urea framework, with particular shapes associated with them such that they could bind one anion, let's say in the presence of another anion. And these molecules do things like bind halides or sulfates, sulfonates, phosphonates, all sorts of different anions that have very poor basicity. So the idea that we have developed is one where we might be able to do a selective reaction or a selective class of reactions. Let's say, imagine adding a nucleophile to a multiple bond. To do so enantioselectively, meaning that we're taking an achiral, not handed starting material to a chiral product, to do that in an enantioselective way with a chiral catalyst, with the agency of a strong acid to activate this substrate, and a chiral catalyst then to essentially activate the acid or associate with the acid as its conjugate base, as its anion, and where enantioselectivity may be then induced through this ion pair intermediate. Okay, so it's a complicated idea, but hopefully one that you see in this catalytic cycle. So as I've drawn it here, you can imagine the acid being activated by the chiral catalyst, making it more acidic to protonate the substrate. You could also imagine that this acid protonating the substrate directly and the catalyst binding to that salt, and then in addition to this substrate. So what I'm going to do is show you an example of this, because we've reduced this to practice, and I hope that it's a first example of what will turn out to be a general type of catalytic reaction, selective catalytic reaction. So the reaction we've studied, as you know, organic reactions have thousands of different names. I've even got a name reaction. It doesn't take much. So Pavlov has a name reaction, and it's this one shown here. It's a variation of the Diels-Alder reaction, where you have a cyclization between an electron-rich alkene and an aryl-substituted imine. Okay, and this is a reaction that's catalyzed by strong acids. I'll use the word strong acid or superacid. What I mean by that is something that's essentially that will protonate water quantitatively when it's dissolved in water. Something that's got a pKa in the negative range, okay, as triflic acid does. It's a very strong acid. The kinetic behavior of this reaction is consistent with the substrate being completely protonated before, as in the resting state. So this catalyst protonates the amine to the aminimine, and then what you have is a rate-determining reaction between this olefin and the aminium salt to make this, and then the proton comes off of the aromatic ring, and you get the product. Now, weak acids, such as ureas and thioureas, do not catalyze this reaction. Not surprisingly, ureas and thioureas are very weakly acidic. Their pKa's are around 20, so 20 orders of magnitude times less acidic than molecules like this. But the remarkable thing in the discovery is that if you combine triflic acid with this chiral catalyst, this chiral urea derivative, you induce the desired reaction. You change the stereochemical relationship. I won't go into that in detail, but the bottom line, the important point, is that you could turn on a very highly enantioselective pathway that leads to this product. Is almost a pure enantiomer. So somehow this catalyst is working together with this catalyst that doesn't need help, that does it all by itself, but doing so to turn on an enantioselective pathway. Okay, so it just turns out that this particular reaction is of interest because this framework that we're making here shows up in all sorts of different natural products that have interesting biological activity. And I won't go into detail there, but just to emphasize that there's a reason to want to do this reaction. These kinds of building blocks and targets are quite valuable and of interest, and there hasn't been a good way to make them. So what we've done is to explore this as a methodology. One of the things that we do in my group then is to try to discover catalysts, optimize it, work out its parameters, and then try to show its scope, to show that it's as general as possible across a range of products. And again, I don't hope at all that you will read all of this or absorb it, but just for effect, to see that there are a lot of different products here, and in each case, the product is formed in reasonably good yields, but more important, in very good enantioselectivities. Okay? And this is true for this class of alkenes, these dihydroperols. It's also true for these vinyl lactams. In this case, the reactions are really perfect. There's really only one product generated in very high enantioselectivity, and the yields, which are isolated yields, are close to the theoretical maximum. Okay, so again, just to drive home that it's a general reaction and it's synthetically useful. But what I'd like to end with is how does this work and what does it teach us and how might we use that? So the question is, fundamentally, I mean, I've sort of given you the answer how we think these catalysts might work, but we really weren't certain. The idea, or the question is, how does this molecule that's a simple thiourea, interact with a highly reactive iminium triflate salt? And we know that that's what we're dealing with, an iminium triflate. Well, there are nice NMR experiments that can be done to address the degree of ion separation in this ion pair. And it turns out that if you separate these ions, either by introducing a more polar medium or by sequestering this anion, the chemical shift of this proton goes what we call upfield to a smaller number. And that's what we see with this simple thiourea derivative. This is not a chiral molecule. It's a simple thiourea. You see what's actually a sizable shift in the NMR signal for that proton. When we use the chiral catalyst that works well in our reaction, we see an opposite effect. We see a large shift in the opposite direction, in a downfield sense. What that's telling us is that this proton in this iminium ion is becoming more deshielded, which means that there's something associating with it. It's not that it's becoming less associated, it's becoming more associated. And what we've been able to establish through these NMR experiments and through computational studies is a secondary interaction, one where you have a primary interaction, the thiourea is binding the anion, as we had hoped, but then a secondary interaction where this ancillary functionality, what's called the sulfonamide, is interacting with this proton, this formula proton of the iminium ion, okay, such that you have now a dual kind of interaction, an ion pair interaction as well as a hydrogen bond interaction. And it's the combination of those two that allows the anti-selectivity. As Paul pointed out, using weak non-covalent interactions to achieve catalysis is something that really hasn't been done very much. Enzymes do it as a principle, but in terms of small molecule catalysts, people have tended to rely on strong covalent interactions. These are very weak interactions, but by working in concert, they allow for a positioning of the substrate. And now what you have here is, again, a picture of this now in line drawing and in a ball and stick drawing, where you've got the sulfonate associated with the iminium ion, primarily in an electrostatic manner, and then a hydrogen bond between the sulfonamide and this hydrogen. That combination has the effect of blocking one face of the substrate and leaving the other exposed. Okay, and that's what you want for an anti-selective reaction. You want to block one side and leave the other available to react. So there's interesting questions associated with what is this catalyst, by doing this, is it making this iminium ion less or more reactive? We've been able to show that it's actually making it less reactive. But because we're using a catalytic amount of the acid and of the chiral catalyst, all of the iminium ion that's generated is bound to the chiral catalyst as well. In other words, we're always in this state. Even though this is more reactive than this towards substrate, you don't have any of this in the free state because this equilibrium constant, the binding of the chiral catalyst to this iminium salt is very high. That's a subtle point. The main issue is that we've got catalysts associating with the anion, a secondary interaction with the iminium ion. Again, there's more detail here than is probably appropriate. Maybe I'll just go to the bottom line. The question is, well, what is important in the actual reaction? What I've shown you here is how it binds to the catalyst. What matters is how it reacts with this substrate or with this type of substrate. And the questions that we ask are, well, is it a stepwise or is it a concerted reaction? Is the first step or the second step determining the selectivity? Just to jump to the end, by using sort of classical tools of physical organic chemistry, what we've been able to show, or at least provide evidence for, is that it is in fact a concerted, what we call a concerted asynchronous reaction, meaning that all the bonds are being formed at the same time, but not simultaneously, meaning that not to the same extent in the key transition state. And as a result of that, what we know is that the selectivity of the reaction is determined in the addition of this to that. So that's what we need to study. Again, what I'm showing you is really sort of how the problem evolves. How do you design a catalyst? Well, first step is by understanding catalysts that work. If we can understand this catalyst at a high level of detail, we can use these principles for other things. And again, all the information here is designed to show you that we can now address this question, knowing that this is the determining event, what controls the selectivity. We can study this computationally using different kinds of tools. And one of the things that we've been able to do using sort of standard computational methods is to come up with a picture for the selectivity determining transition state that corresponds to the observed product. So the bottom line is, a reaction that really goes by a fundamentally new mechanism that I think we understand in a very, very deep way. So that's really just an example of the kinds of reactions that one could think about doing. What I won't go into any detail, but hopefully just to impress on you that this is a general concept. Using this idea of hydrogen bonding to an anion or to an electrophile to stabilize a negative charge, either in an anion, in an ion pair, or to developing negative charge in an electrophile as a nucleophile adds to it. And then using some sort of an ancillary functionality, something that can direct the nucleophile or activate the nucleophile in the addition step. We can do all sorts of different things, all sorts of combinations. These are the different examples of different types of products that we can generate around this simple idea. And again, I don't hope for you to see these in any sort of detail, except to maybe appreciate that they're different looking kinds of compounds, very different, all of them chiral, most of them are what we call bifunctional, meaning that they have multiple handles to do subsequent chemistry. And these are things that are valuable for synthesis of complex molecules. So what do we hope to do with this idea in the future? I think that this is applicable to all sorts of different things that I think may be important in making reactions more efficient. One of the great problems in organic chemistry and in catalysis right now is a problem called hydroamination, addition of an amine across a double bond. And it's represented by the idea of taking ammonia and an alkene and bringing them together, adding an NH bond of ammonia to an alkene. That's a very tough problem and a very important problem. Now, there's a variant to that that you can think about using a strong acid catalyst that's shown here. And the idea would be to use a strong acid to activate the alkene, generate a carbocation, stabilizing the anion, and then use a nitrogen-based nucleophile, like acetonitrile, a non-toxic solvent, that could trap that carbocation, ultimately leading to this amide. So this is a real possibility now because we know that we can do this kind of anion binding directed asymmetric catalysis. And in fact, we've got good results in this direction. You can also think about much more complicated things like really mimicking the types of chemistry that nature does well. Nature takes polyolefins. W.S. Johnson was a pioneer at Stanford in doing this kind of chemistry in a synthetic context, taking polyolefins and doing extraordinary tandem cyclizations to generate polycyclic frameworks. This is, in fact, the chemistry that's at the heart of the steroid biosynthesis and the cyclization of oxidosqualene to this tetracycle. This is a transformation that's done enzymatically. A lot is known about the enzyme, and the basic idea is an acid to activate the electrophilic functional group. And then, remarkably, what the enzyme does is use weak secondary interactions, mostly it's hydrophobic interactions, to surround all of these functional groups that are reacting and orient them and stabilize charge and position them just right such that they cyclize in a particular way. This is something that looked impossibly complicated, impossibly difficult, and sort of belonged in the realm of the magic of enzymes until recently. But now it's something that one can think about doing with a small molecule, really just by taking an acid and then a chiral catalyst that could, in principle, then just have just the right minimal number of interactions to stabilize and orient these things. So that's the kind of direction that I can imagine this going. Really using catalysis to do synthesis in a wide range of contexts. So with that, I'd like to end. I hope I didn't go over. I'd like to thank the Dreyfus Foundation for funding almost all the research that I talked about in this lecture. So this project has been the work primarily of Hao Xu, a postdoc in my lab who's got a Dreyfus Fellowship. He's in a very productive collaboration with Stefan Sund, an extraordinary physical organic chemist in my group. So I'm grateful certainly to Hao and to Stefan and to the Dreyfus Foundation for supporting this work and for inviting me here. Thank you very much. Promise no more organic chemistry after this lecture, right? You get the Nate and Dan show.
calculation works out for potential. With the onshore and the offshore, so the offshore. So
I'm got everything. So let's look at it. So the other thing to be careful of is, you said 5 times energy. Did you mean energy or electricity?
No, I did this calculation for primary energy.
For primary energy, that's right. Yeah. So it's 3 terawatts per rate. Right.
That's right.
Yeah. So that's right. So that's what I just would like to look at more carefully.
I think. I mean, I'm aware of David Keith's work, of course. In fact, Danny Kurteva did.
Yeah, I'm just project. Oh, it'll be on both. Yeah. Where is he?
I have no idea. Are you going to switch this?
Okay. Needed.
You guys just about ready?
Yeah.
You're the chair for this, right, John?
Yeah.
I want to mic up the first speaker.
Okay. Oh, that's Nate. Where is he? Right there. You want to mic him now? I'm just going to use this. So why don't you mic him right now? Yeah. So, Nate, come here. We'll put the mic on. Yeah.
But it's echoing with that mic, you know.
No, but it's
pushing that mic out.
We'll push that out of the way. We'll push it out.
Just in case you turn it back.
Really? Sure, my hand.
With the screens the way.
I know. You know, I can't point to the screen because you have two screens. Is that on? Yeah. Okay.
Just when you're done, sir, just push this mic out. Thank you.
Hey. So I'm John Seinfeld from Caltech, and it's my pleasure to introduce the next two speakers. The first is my colleague at Caltech, Nate Lewis, who's the George Argyros Professor of Chemistry, and Nate is going to talk on artificial photosynthesis.
Perfect. Thanks very much, John. It's great to be here and to share with you what we're working on. It's certainly not done. I'll just give you our thinking process and a progress report on really a project that we started in my group, really about 2.5 years ago. I also will give you an introduction to the thinking behind this, coordinated with Dianne's talk next so that I will be efficient in slides as well as everything else, so Dianne won't have to show the same introductory slides. I should thank DOE and NSF. BP funds our work to make solar electricity. These people in Dreyfus fund it to make fuel. I think most people are familiar with this number and set of units now, but for the people that aren't, it's always good to calibrate. If you take all the energy consumed in the world in a year and divide by the number of seconds in a year, the world's energy meter would be somewhere hovering about 15 trillion watts. It will go up. There's not been a year in the history of our planet that we've actually used significantly less energy than in any year before. In the face of economic growth and population growth, most projections of the EIA and the IEA and many other agencies believe that it'll be 25 to 35 terawatts average consumption rate within our lifetimes. And that built in business as usual assumes that we save as much energy as all the energy we currently use. Then you could hold it to double current rate. If you saved even more than that, which turns out to be down to a burden of twice the level it takes a human to eat per capita, you might hold it constant, something the world's never done. Of course, 85% of that comes from fossil energy right now. And that means that just even to meet demand, if it's going to double with aggressive conservation, you need 14 or 15 trillion watts of new energy of some kind. If your goal is to keep the glaciers from melting further and to reduce the rate of emissions by 80%, essentially 80% means reduce it all. And so if you can fill this difference by saving as much, again, energy as all the energy we consume, that means you still have to make as much clean energy as all the energy we consume within our lifetimes. That's what it takes, the arithmetic, to stabilize emissions. You can break it up into wedges on supply and demand. The arithmetic is the same. You have to make as much clean energy as all the energy we use, and you have to save as much energy as all the energy we use if you're going to hold demand double and cut emissions to essentially zero. We know what the consequences of not doing that are likely to be from the ice core data plotted with human fossil fuel emissions in the last 50 years. What's not appreciated widely, I didn't hear it today earlier, is the one number that I think is the most important. important number, which is the time to relax back if we stopped in 50 years at that level of CO2 back to the planet that we got from our parents at 280 or 300 parts per million. That's really characterized by two time constants. The first 3/4 of that 550 ppm delta function pulse would decay in about 400 or 500 years. The next 1/4, best knowledge says, would take 10,000 years. Nobody has a technically credible way of removing the 600 trillion pounds of CO2 that is distributed dilute in our atmosphere. If you do, you should ask Richard Branson. He'll give you $25 million on the spot. So we can say that within the next 50 years, we are going to flip the switch on the delta function laser transient experiment that's going to pulse the chemistry of our atmosphere for a timescale comparable to modern human history. Period. Seeing the ice melting? It's melting much faster than people predicted. Just as Jim said, the permafrost is melting, and isotopic dating, both of the helium and the methane, tell us it's melting in areas that hasn't melted in 40,000 years. None of these things these positive feedbacks are really captured in any faithful way in climate models because we don't have human experience of them, so we can't extrapolate and model when they'll kick in very well. We don't know. In the Permian era, by the way, the one I like to refer to as opposed to the Eocene, when the CO2 did spike in a much more rapid time constant than the more gradual one up in the Eocene, there was a massive isotopically light release of carbon, presumably from the permafrost, that was catalyzed by some other events. We know temperature spiked 6 degrees, 8 degrees on average centigrade, and from that rapid change, similar to the one that humans are now inducing, we know from the fossil record that 90% of the species on Earth could not adapt and went extinct. We do not know this would happen again. We do know there's only one way to find out. Well, if you need about 14 trillion watts, you can get it from nuclear power. If you want to build a new plutonium-containing nuclear power plant every single day forever, because you have to build one for 40 years to make 14 trillion watts. They only last and are commissioned for 40 years. By the time you build the last one, you'll have to decommission the first one. It turns out that there is more energy in natural gas on our planet than there is in all the terrestrial uranium-235 when used in once-through cycles. So it's not even credible to think about, if this is the scale you're going to do, nuclear power without thinking about crediting the Iranians and North Koreans for stepping up to do their part to mitigate global melting, right? So 40 reactors doesn't mean anything globally, right? This is the cruel arithmetic of energy. It's 14,000 to hold CO2 to double if you save as much energy as all the energy we currently use. If you don't want to do that and want to build one a week, you leave 90% of the problem on the table. You could get it by burning fossil energy and capturing and storing it. We have no idea whether or not at scale this works technically. And actually, I think there are very important chemistry problems in the three-phase flows underneath the soil in the Earth of the migration, monitoring, prediction, and modeling of where carbon dioxide would go if we tried to bury gigatons under our soil. I'll just give you a feeling, though, of how big this is, because Deep Picala has done a nice calculation, taking the density of supercritical CO2 at 1,000 meters, and assuming that we did do it all for 100 years, and that it didn't leak, because if 1% of it leaks after 100 years, the net flux is identical as to what we're mitigating in the first place. If none of it leaks, and you put it all down there, the United States CO2 emissions, and the CO2 were distributed uniformly across the continental United States, it would displace the surface of our continent by an average elevation of 5 centimeters. This is good if sea level rises, right? You can change Jim's picture. This is what we mean by clean coal. Right? Just advertising it on television doesn't mean that it works technically at scale. Even the most advocates of carbon capture and storage think you might do at most 10% of our emissions sequestered this way because of these considerations. And so if you don't get it from one of those two things, you have to get it from renewables.
This is a famous numerical chart that I first generated in 2002 for an NRC study. This number is technically in good shape. Hydroelectricity is maxed out, not much room to grow. The renewable, sustainable geothermal flux is in good shape. You can mine it faster than that, but you'll use it up just like using up coal. This is the sustainable amount because we know the temperature at the core and the diameter and thermal conductivity of the Earth, and you know the geothermal heat flux is in every textbook. So there's only 10 terawatts to be had with 100% efficient heat engines covering all the land on the Earth, forgetting about saluting to the French Sergeant Carnot. Right? This number's in good shape. There's only 2 terawatts and all the energy flows in all the oceans and tides. Wind guys are fighting back. Current thinking, and when I first did this in 2002 from several peer-reviewed sources, was that it was about 2 to 4 terawatts of extractable as electrical energy in the high wind speed areas on the Earth. They're fighting back and now saying, well, maybe there's 10, maybe. But of course, the sun couples weakly to drive all the winds. This is still an uncertain number to within a factor of a few. Biomass, if you took all the land not used for food, planted it with the fastest known growing crops, and assumed 100% conversion efficiency with no losses and no energy into the farm, you might get 5 terawatts. And that doesn't assume that you paid the carbon debt, which happens when you decrop something else. That's because photosynthesis is an inefficient machine for converting sunlight into stored energy. In fact, only 1% or less of the total sunlight over a year that hits a crop is stored, even in switchgrass and miscanthus, in all the lignocellulose and biomass of the crop. The reason that photosynthesis saturates at 1/10 of a sun to protect itself from radical damage, because it turns out rubisco is a pretty bad enzyme, and it can't turn over fast enough, so it shuts down the electron flow to prevent radical damage in the canopy at shade at about 1/10 of a sun. And because of that, and because plants have the wrong band gap, they should be black, not green, those two things conspire to make them inefficient machines. In fact, plants rebuild themselves every 30 minutes, and most of the energy in a plant is used to rebuild the plant, to keep it alive. In universities, we call that overhead. But there's a big number. There's an only unequivocal big number. Famous statement, more energy from the sun hits the Earth in 1 hour than all the energy consumed on our planet in an entire year. Another way to think about that is in 1 year, more energy from the sun hits the Earth than all the energy consumed by humans in history. And that statement's going to be equally true 100 years from now as it is today. So it's pretty clear what you want to do. You probably can't see your way clear to holding CO2 to even double, no matter how much energy you conserve, unless you have significant amounts, maybe of wind, but certainly of sun, contributing to the energy mix. 3 ways we know how to do that. Nature did it for us, but inefficiently, and we wouldn't really care about a failed machinery called photosynthesis, except it figured out how to store energy in the most energy-dense form known on our planet, except for nuclear energy. It stored it in chemical bonds. So that's why we care. We can go get it later. But photosynthesis, I said, is very inefficient. Solar cells are very efficient. They can be 20% efficient, but they make the wrong product. They make electricity. There's no good way to store massive quantities of electricity. If there is, you should just do that right now, buy electricity every day at 25 cents a kilowatt hour, at a nickel at night, sell it to everybody at 25 cents a kilowatt hour, and fund your own research foundation. Profits. Doesn't exist. You can pump water uphill. That's good in your backyard. It's good every winter and emptying it every summer, but it ain't good if you want to buffer the day-night cycle of the United States of America, because you need something like 500 lake meads filling every day and emptying every night. This is the difference between the energy density of 1 gallon of gasoline. You have to pump 55,000 gallons of water up the height of Hoover Dam to store the same amount. So we got to find a way to take sunlight and do it ourselves with the efficiency of solar cells, so we don't have the land area impacts of using an inefficient machinery, but that makes chemical fuel that we can store, because it's not enough to build an energy system that you just capture and convert sun. You have to also store it, because my little saying is that he that cannot store will not have power after 4. Johnny Cochran would be proud. Photoelectrochemistry really works. When you take semiconductors and shine light on them due to a magic charge separation property similar to what makes a transistor, this picture from Doman's lab that I own now, shows you can take light and shine it on this semiconductor and make fuel directly with no wires, just like a leaf would be doing. This makes hydrogen and oxygen from sunlight. The quantum yield of this process for wavelengths of light that is absorbed is essentially 1. Even the fact that this is not highly colored, even taking that into account, the total energy efficiency of this system that you are seeing is still greater than that of the fastest growing plant, based on an energy input from the sun divided as the denominator into the total amount of free energy produced in the fuels. So we know that birds fly, have wings, airplanes fly faster, they don't. We already know that we can make fuel from the sun better and more efficiently than nature has given us. We just don't have materials that can do it very well, because that material would have worked even better on the moon, because its band gap for strontium titanate is 3.2 electron volts, so it only responds to a small fraction of the solar spectrum on Earth. There's no known single material, holy grail of photoelectrochemistry, that can absorb a lot of sunlight and last in the presence of sunlight at the same time. Probably the reason for that is that it has to both survive highly oxidizing and highly reducing environments at the same time, at two different parts of that same material. And so we were inspired, actually, by when I was visiting Francois and at Princeton in 2003, when Steve Piccola came up to me and said, "You artificial photosynthesis guys have to figure this out, because there may be no other way." So the photosystem 1 and 2 inspiration of plants is, of course, they separate their products by a membrane, and they use 2 photosystems, not 1, and they actually have a very oxidatively unstable iron-sulfur type of system that catalyzes at a soft site, the reductive process. It never sees the oxidative environment. They have a hard manganese site, the oxygen-evolving complex. It never sees the reductive site. And by separating the products, you also can separate the 2 different species chemically from having to react with each other. And maybe more importantly, you don't want to make hydrogen or hydrogen incipient here and oxygen in the same place at the same time, because you know what happens the instant a cloud comes over this system, goes kaboom. So the inspiration for that was to build our own. Build a membrane with the pigments not being the ones that nature used, but being more robust inorganic materials, and also couple them without wires to make chemical fuel directly in a system that I drew on a napkin in about 2003, right after I got back from Princeton, that we now have lovingly coined the term, because Jonas told us to figure out something to call it, alliteratively powering the planet. What else? There was one more important design principle. The other important design principle is, while we had a membrane, I thought that at the time we could have done that with a photovoltaic cell, but they're way too expensive and arguably not scalable, because crystalline materials out of things like silicon, to give you a scale equivalent, you have to put up 1 million solar roofs every day for 50 straight years to hold CO2 to double. I don't think anybody can put 1 million straight solar roofs a day with the materials we have now. You can't get to scale. So we need to find a way that can get to scale real cheaply. And one way is to think about using this structure of rods, because instead of growing a single crystal that would be brittle and would have to be very pure, if you drew things that were oriented like grass or carpet or trees toward the sun, you could then absorb light, and in this idea, you would be able to use very cheap materials and process them in a very simple way. In order to couple this 2-photon system, one which would absorb the blue light and let through the red, and the other absorb the red light, and separate the hydrogen and oxygen, we need a membrane. And we also need catalysts to convert the electrons to reduce water and convert the holes to oxidize it. And we, of course, farmed the harder parts. We thought of the problem out to Dan Nocera and Jonas Peters. Jonas has now surpassed us by having a great catalyst made of cobalt to reduce water to hydrogen, and Dan has far surpassed us to have a great catalyst to oxidize water to oxygen, which he'll tell you about. And we've still got to develop the pieces here, because if we don't make them all work together at the same time, we don't have much. Why was the nanorods important? The rods are important because planar solar cells in design from Bell Labs back in 1950s have an important physical constraint. You need 300 microns of silicon, for instance, to absorb sunlight. That's the absorption depth in silicon. Any less wastes sunlight by letting it through. Any more wastes silicon. So you can grow 300 microns of a crystal of silicon, but it has to be very pure, because for the light that's absorbed very deeply, the excited state created has to last back 300 microns to get back to the space charge region in the wires to lead to current. And it's this one law that is why all solar cells share about the same cost per watt. Because the ratio between the purity needed to get the diffusion length relative to the absorption depth within a factor of 20% is the same no matter how you make it, no matter what material you make it out of. So this was an unsolved problem that we decided to change the rules, and therefore we might be able to change the solutions. The way you would change the rules is you still need 300 microns long to absorb the light, but if we want to make really cheap silicon, for instance, or other materials that have short diffusion lengths, let's just make them go sideways, only the short distance that they can go, and orthogonalize their direction of collection relative to their absorption. If you change the rules, you can open up a whole new set of design principles. And that's why the rod structure was on that napkin. This radial geometry would in principle allow for a high quantum collection efficiency even for really cheap materials or non-stoichiometric materials or materials you would be crazy to use in this planar design that we are now making solar systems out of in our lab. One example is rust, where you need a few microns to absorb the light, but it's highly non-stoichiometric as hematites found in nature, highly defective, and Keras can only move 40 nanometers. So the only 40 nanometer top part is live, and the other 3 microns is just dead. So we just make 3 microns long, 40 nanometer diameter rods, and they're alive. Make them out of pyrite, fool's gold. So we're making combinations of solar active materials out of fool's gold and rust. You can decide whether we're crazy. We then did theory. A joint student with Harry Atwater and myself, Brendan Kays, did a full device transport physics theory, which we're guided by to show indeed that we know all the transport device physics of silicon and carriers in silicon, that as a function of the rod diameter, there's a sweet spot where you can have low diffusion length materials and still have high full device physics predicted efficiencies, 10, 15% efficiencies at diffusion lengths of a few microns, which is really rotten silicon. There's probably something to this design because, after all, that's what an aspen forest does. Long axis to absorb light, short axis to move the heavy, slow-moving nutrients. It's what root systems do. It's what leaves do. It's what stomata do. It's what retinal rods do. This orthogonalization principle is all throughout nature. So it seems like a good thing for us to try to exploit. The other important thing, as I alluded to, is this is what the periodic table looks like in our laboratory. It looks like a logarithmic scale of the abundance of elements in the core of in the crust of the Earth compared to silicon. And we have a line right there, and you're not allowed to go below the line. No iridium, no rhodium, no osmium, no platinum. Because if we don't have a whole lot of time, we don't have time to screw around with those elements anymore. We got to figure out something that you could make 1 million roofs a day of, and those are above this line. It's heretical for an inorganic chemist, but the important point is that there are materials like zinc phosphide, like iron sulfide, like iron oxide, that are above this line, that are earth abundant, that you would never make planar solar cells out of because they can never be made pure enough, cheaply enough, to satisfy that planar ground rule constraint. We can just change the aspect ratio of these structures and we think open them all up to work. The other important point is that the solar photon flux hitting a plane doesn't change. But if you take something like this high aspect ratio structure and decorate it with catalysts, if you make a fuel cell, you need to use platinum. It's the best catalyst out of all the known ones at all pHs, known in this volcano curve for 50 years, because you need an amp per centimeter squared. But the solar photon flux is only worth 20 milliamps per centimeter squared. And if distributed over this very high surface area, you relax the turnover number on the catalyst because it has to turn over less often since there's more area feeding the same total number of flux. And that means that if this is 3 orders of magnitude higher in surface area, you can use and satisfy the flux constraint catalysts that are 3 orders of magnitude less active than platinum, like nickel or copper or cobalt or MOS2 and so on. And so we don't need the most active catalyst in order to have low overpotentials in principle to either oxidize or reduce water. So we can stay above our line in earth abundance without having in principle to develop new catalyst systems to do that. Second advantage of these high surface area features. Okay. Now I'll tell you what we've done in the last kind of 2 years. We've been furiously working at this. We first decided to test the theory. This is an alumina template. It's just aluminum that's oxidized to make ceramic alumina. You can electrochemically control the pore diameter by etching, current density, as well as the pore depth by how long you etch. We can do this over large areas. This is a 1 micron scale bar, and it gives you a feeling for what we can do with this template. We can then electrodeposit in those pores a material. This is a test material in this case. Cadmium selenide telluride was just a prototypical material that we could test the theory on because we know we can electrodeposit this. We know it's photoactive. We also know that you can't make it have a diffusion length longer than 1 micron, and you need 3 microns to absorb all the light. So in a bulk crystal or thin film, we know it's highly inefficient. So we just sputter a cadmium selenide layer there, put a metal back contact on, electrodeposit from a bath the cadmium selenide telluride in our template. The template, alumina, is soluble in base. We etch it off in base. We're left with the forest of rods that are 3 microns long but smaller than a micron in diameter, and so we should be able to collect things sideways. And then we fill this up with a liquid that's going to collect everything that can get sideways and see what we see. Here's an example of this kind of first generation photon forest. Here's a 1 micron scale bar, long enough to absorb the light, highly dense, and there's also some photon trapping and scattering in between. The key experiment here is to vary the wavelength of light. For a planar cell, as I've said, very short wavelengths are going to be absorbed strongly, and they'll be within that micron active layer and give us high current yield. But very long wavelengths of light near the band gap are going to penetrate too deeply, and the current should die. On the other hand, same material grown exactly the same way at the same time, but in the highly packed nanorod structure should have the ability to collect carriers sideways for both the short and the long wavelengths. So that's a definitive check of whether or not we're on the right track. Here's the data. You can see, in fact, that the planar structure works as advertised and reported previously in the literature. The band gap is about 800 nanometers. You only get a fraction of the photons absorbed, collected as yield, and that fraction increases up to all of them only when you get to very short wavelengths, but you lost almost all the solar spectrum photoactivity in the meantime. But the exact same material grown the exact same way in the radial morphology collects carriers from the band gap all the way through as if you had them all the time, because they only have to move within their diffusion length sideways. Okay, so that's good. So cadmium selenide telluride is below the line. For time purposes, I'm skipping a lot of work. We wanted to grow them out of silicon as the cathode side of this material. Silicon's been shown to be a good cathode in bulk form by Texas Instruments and Adam Heller. It's just that we had no way to grow it nanostructured. So we grow it from the vapor liquid solid growth catalyst method, where you can known from Wagner and Ellis in 1964, and now all the nanoscience people like my old student Charlie Lieber use this as ways of growing individual silicon structures. We need to grow large area arrays, so that's another non-obvious trick. We do that by either stamping or, in this case, photolithographically patterning little gold, nickel, or copper catalyst balls on a silicon wafer. And when we tried to grow structures with that, they should grow epitaxially underneath these metal catalyst particles that cracks the chlorosilane and then precipitates the crystal of silicon. The gold rides on top, and it seeds this just like growing corn, kind of like nanobio corn. Except that we got nothing. And what happens is when you grow from chlorosilane, which is a very cheap method of growing silicon, it's practiced in factories by Wacker the size of this building. And the hard part is purifying it. We're not going to purify it. We got nothing, really, because it turned out that the gold particles moved around and ripened on the surface. And when you start with that template, you've lost your initial pattern fidelity. So we added an oxide buffer layer so that these metal particles that were deposited have nowhere to go. And in fact, they retain their pattern fidelity after a test anneal. And then we crack the silicon and let it grow. And this is my favorite picture, as we get. The 100-micron bar, these are perfect single crystals of silicon by TEM that are 100 microns tall, 4 microns in diameter, spaced on whatever pitch we patterned them initially. They're single crystal. And I know I've got 1, 2, 3 former Bell Labs people here who are ready to jump out of their seats because they know that I'm going to tell you that these are gold-saturated silicon samples at a growth temperature of 1,000 degrees, which they were told never let gold anywhere near silicon because it's a deep-level trap. And the only other option, of course, for growth is we can do it instead of with gold, we can do it with nickel or with copper. You're still going to jump out of your seats. But in fact, the solubility limit of gold, nickel, and copper in silicon is even still, with a deep level trap, enough to give you a 2 nanosecond lifetime, which is a 2 micron diffusion length. And these rods are only 4 microns in diameter, and so we should be able to collect them all. Okay? So this is really rotten silicon, which we can just thermally refine and purify, but we don't need to. And indeed, works pretty well. We get about 450. This is a current voltage curve in a liquid junction of those rods. Single crystal of silicon, expensively purified under these conditions, would give us 500 millivolts open circuit. We're at 450. It would give us 30 milliamps per centimeter squared. We only get 12 now, but that's because we only fill 5% of the optical filling plane at normal incidence. We've got to do better than that. And we still have a shunt left behind. That shunt, we believe, is due to the residual gold on the side walls that we're furiously etching off right now. So in principle, this works. It's really cheap silicon grown on an inorganic substrate that works almost as well as if you grew a single crystal. But I promised you that we would be going toward this membrane. Kate Ploss and the group was inspired by John Rogers' work, and I know Ralph Nuzzo's in the back, and Ralph's, where they've used PDMS molds to make flexible electronics. PDMS, polydimethylsiloxane, known lovingly in our group as fish tank goop, because it's the stuff you buy from the hardware store, has this wonderful property that when you peel it fast, it's stiff, and when you peel it slowly, it's goopy. So we just squirt that stuff in these rods on this array, and then give it a hair peel. And off come the rods, and they only leave little stubs behind. And their orientation is completely preserved in this PDMS film. And so now we have an inorganic, filled, single crystal array of silicon rods that bridge macroscopically a bendable, processable piece of plastic. When we do this with a polymer that actually has enough monomer in it that it'll evaporate, we can control the thickness of that. And what we're left behind with is there's the polymer, there are the rods. These are all single crystals of silicon over large areas. This rolls up. You can unroll it. There's almost no load on those rods, so they don't fracture, they don't break. The advantages of organic solar cells are always touted that they can be rolled up in a piece of plastic, but they're made out of inherently photo-unstable materials. The advantages of inorganic materials, they work very well, but they can't be processed. So we actually have both functions in the same material. And this starts to look like one of our pieces. The second piece is going to be, flip this over, the piece on the top. By the way, I'm sure the Bell Labs people already know the other fact, that what we did is created all the surface area, and we should be killed by all the surface recombination at all that increased surface to volume ratio. But we have a way around that, because Yves Chabal at Bell Labs shown that you could hydrogen terminate silicon and passivate it, and the only problem with that is that it oxidizes in air, and the native oxide is defective because the silicon atoms in the bulk are sp3 hybridized, and they're bonded to all the other silicons, but not at the surface. And this is a strong bond, so it terminates that, except when it oxidizes, that creates traps. So we prevent that. We'd already done that on single crystals by making a metastable surface, a chlorine-terminated surface, and then treating it with a Grignard or a methyl lithium reagent to make a silicon-carbon bond. The important thing about doing this two-step process is we can add methyl as well as ethyl, and methyl's the only group that can sterically terminate every silicon site on a 1-1-1 unreconstructed silicon surface. These have very low surface recombination velocities, less than 10 centimeters per second. They're stable in air for months. And so we can mitigate against that higher surface area because we're chemists. This is an STM image at 4 Kelvin showing that methyl termination on top of the silicon 1-1-1 lattice. We can additionally grow conductive polymers this way by seeding them with a double bond on sites that aren't filled with methyl. We have Grubbs catalysts that then can romp double bonds and get both conductive and insulated polymer sheets as the top contacts around this bottom contact. In addition, we can laminate these materials. So instead of having to grow epitaxial growth of one phase on another, we just grow a piece of plastic and grow another piece of plastic and then laminate them together like making a driver's license. The other piece of plastic is going to have the rods that are oxidatively stable, and so we've started working on that part of the problem with tungsten oxide and had some success growing those rods. Silicon's going to be below because it's a known photocathode. Tungsten oxide should be a known photoanode. It gives us 800 millivolts voltage. You need 1.2 to split water. We already have 450 from the silicon. So in principle, we should be able to put these two systems together and have a demonstration system that is, in essence, an artificial leaf because it has a membrane. It has something that reduces water to hydrogen, something that oxidizes water to oxygen from a two-photon system. The membrane itself doesn't yet manage protons and electrons at the same time. Farmed that out to Paula Hammond at MIT. It's another hard problem. Here are the tungsten oxide rods. They're not oriented and felt yet. We just grew them by vapor phase synthesis to show we can get them photoactive in this form. Again, it's the nanostructured idea. Diffusion lengths are too short to make bulk materials work very well, but we just confine the geometry radially to make sure we can get them all sideways. They work. 800 millivolts open circuit voltage. So that's the N-type photoanode. Long-term stability of tungsten oxide in water is something that is debatable now, but it's very close to being stable. If we can catalyze the water oxidation just a little bit, maybe with anodic films of cobalt with phosphate, we might be able to bring us that last 9 of stability. So we're trying to see if that works. Here's rust. This is rust felt. That's a 5-micron bar. Same idea. 40 nanometer diffusion length, 3 microns to absorb the light. Here's 3 microns thick. It's an average 40 nanometer diameter. So you can see where the ideas are here. We haven't implemented them into the membrane yet, but it's pretty clear where we're going. So what is clear is, even though my friend Amory Lovin says we can save a lot of energy, that's certainly true, but you still got to make a lot of energy. In fact, no amount of saving energy ever turned on a light bulb. No amount of saving energy ever put food on somebody's table. If you save all the energy equivalent to all the energy we use, you still have to make 15 trillion watts just to hold CO2 levels to double within our lifetimes. That's the arithmetic of energy. If you want to do that, you only have 3 big cards. Clean up fossil energy, build a whole lot of plutonium-containing nuclear reactors, and or figure out a way to use our biggest resource, but it's got to be really cheap, and you got to find a way to store it too, or you don't have much. The only proven systems right now, if you're going to make a fuel, have to touch a liquid. So you have to use a semiconductor to capture and convert the sunlight. At some point, it's got to touch a liquid. And so we have to learn how to work with these semiconductor liquid junctions, whether buried or not, in order to try to put together a system that could be rolled out on this scale in this time. We still have a lot of work to do because we're working on the capture and conversion part. And if we can get even lower overpotential catalysts to deliver those electrons into chemical bonds, we would dearly love to have that and couple them in. And that's why we farmed out that harder part of the problem even to the people who have gotten ahead of us, Jonas and Dan. They will tell you about that. I'm sure Dan will in the next talk. So with that, thanks for listening, and I'm delighted to be able to tell you what we've been up to in the last year and a half.
One question.
Just one. Oh my gosh. Hey, Mark.
Do you think that there's any chance that this kind of process could be, or use a phrase you've used, cheap as paint?
I debate this with Harry Atwater. Harry Atwater, being my partner in crime in the material science applied physics system, has costed out what a CVD system would be like. He claims that glass is coated, tin oxide glass, by this same process, and that in a non-vacuum but atmospheric CVD system that you could envision a roll-to-roll process on a piece of glass that would simply do this. I'm still, being a chemist, much more on the Palo Alto side and would rather have a bucket and paint it on. So I'm not sure, because cost at scale is something, I don't know. But we are working on taking randomly oriented arrays of rods and functionalizing them both on their side and their top and seeing what it takes to get all these random things to go all pointing toward the sun, which I think is a pretty interesting self-assembly problem that we ought to be able to do. And so then you could think about other ways to make random buckets of these and then paint them on and then get them. And they don't all have to stand up like this. In fact, you really want them like grass, not aspen trees, right? So that would be the real model, right? You want all the angles. We can do a lot of interesting photonic band gap things with the periodic structures, right, which we're doing, but you really would rather not have them perfect. So maybe. I know better than to say for sure. Everybody's costs are always higher than they tell you, right? Rule number one of industry. Okay. We have to get rid of this because we have Dan. Just leave it in there. We'll change it at the other break, right? Give me mic. Oh, you want me to have the mic? Dan, you can use the slides, and I'll just give your...
So our next speaker is Dan Nocera, who is the Dreyfus Professor of Energy at MIT. Dan?
Okay, thanks. Henry Dreyfus, Professor of Energy, which is a joy because to be here at the Dreyfus event, it's quite an honor to be talking about this today. You just heard Nate talk about this is what we need to do. It's got to be cheap, efficient, and highly manufacturable. The one thing, though, you should realize about energy is 95% of the work, there's always this discover new principles of science. The bottom line is all the physics and chemistry you've done or you know about, you're not going to improve. Electrons are going to go the way they do. You're going to do electrolysis. All those principles there's no discovery there. I really don't think there's any discovery practically. Where the discovery comes is, can you do it cheaper? Can you think of new materials? Can you think of new processes? That's where the discovery comes. It comes in that top line. And so actually, I think a lot of people in the energy game have lots of wasted effort trying to find new principles when what they really want to do is have new materials and new ways to do things, like you heard Nate talk about. Nate's not changing semiconductor physics. He's making new materials to exploit semiconductor physics. So today what I'm going to tell you is the catalyst side of the story. You can see we're a tag team. And it was to try to design a catalyst to split water. And we really wanted to do it under these conditions: cheap, efficient, and highly manufacturable. And I'm going to lead you through that story today. And so I'm not even going to say what Nate said it, but the whole game of renewables is storage, I think. You get a good storage mechanism, you'll see a lot of things start getting driven. But if you have no storage, you're doomed. It's the no power after 4 statement of Nate's. So what does it? And there's the leaf. And a lot of people actually overplay sugar, because it turns out if you go and look at the Calvin cycle, there's very little energy stored here. Sugar is a good way to store hydrogen, but from an energy point of view, most of the energy storage is done up front in splitting water to oxygen and hydrogen. This, not only sugar, but cellulose and lignin, this was an engineering problem that the Calvin cycle took care of. The energy problem is taken care of up front. And so if you want to do what leaves do, you just basically can stop right here. Possibly. If you don't want to use hydrogen, then you need to do this. And I think the jury will be out ultimately whether you use hydrogen directly or not. But there's one fact: you can't avoid hydrogen if you're going to use water as your fuel source. There's just no avoiding it. So I just want to give you a little feeling, why did nature choose water as a fuel? So water, of course, isn't the fuel. It's water plus light is the fuel. And it makes hydrogen and oxygen. So this is, you can do these calculations. In 1 liter of water, you have 13 megajoules of energy. I hate swimming. I don't know. This guy, Michael Phelps, does not impress me at all, by the way. But I went and took there's the MIT pool, 3.2 million liters of water. Now, here's the caveat. You're going to have to manage that 3.2 millions per second, because I want to go into the terawatt scale Nate was talking about. Remember, we needed 15. If you manage that amount of water per second globally as your energy storage, you're up at 42.7 terawatts. So you're not dealing 1/3. You have to deal with, per second, 1/3 the volume of that pool to take care of Nate's problem. And it's all in the bonds of oxygen and hydrogen. So water and light does indeed equal oil and coal. And I want to just remind, this is a good thing. This is going to sound kind of pedantic, but what is a fuel? So there's carbon-carbon and carbon-hydrogen bonds and oxygen. I'm going to burn the fuel. Okay. You know, Browman, it took me 14 hours to do that. It would have taken him like 36 hours to get that to happen. So that's what you're doing. You're taking high energy bonds and you're rearranging them to lower energy bonds, and then you're taking the excess energy. That's all you're doing. That's why this is so intrinsically a chemistry problem. What you're doing is you're storing energy in bonds, and it's bond rearrangements. It's what scientists and chemists do. So really what you want to do here then is take these low energy bonds, and that's what that pool calculation just showed you. You're making really high energy bonds to store fuel. And nature already knew that. That's how nature's set up to be a battery. It has membranes and it puts charges across membranes. It decided not to be a battery for a simple reason. This is an electron and this is an electron, and they have the same charge. And what your goal is to stuff them into the smallest volume you can. When they have the same charge, that's hard to do, but there's one place that you can put them in the smallest volume. That's the bond. So that's why nature chose the bond. I mean, I know it sounds simple, but I mean, the arguments I hear about energy storage are magnificent. It really is freshman chemistry. Calculate the volume of a bond, and that's the closest, that's as much as you're going to be able to stuff energy or electrons into a volume in space. I don't know if it's too bad. I think I forgot it. I had an energy density calculation. The problem with batteries is they're 3 orders of magnitude too low in energy density. You can't help it. Right? The only way you're going to increase that energy density is if you go from 1 electron couples to multi-electron couples. There's been huge battery improvements. For instance, at MIT, you hear A123. Don't get confused. There's no increase in energy density. It's just a lithium iron phosphate. What the improvement in A123 is getting the energy out and in quickly. But it's not improving energy density. Right? So batteries are 3 orders of magnitude off of these bonds. And I doubt you're ever going to be able to improve that anytime soon. So here's photosynthesis again. And it is true in this Caltech-MIT collaboration, though we don't think this is the way to store energy, there's a simpler way to say what Nate was doing, and it's what you did today. You ate food. You're going to try to balance the amount of food you ate to be basically neutral because you live. So you use energy. And most of the energy getting lost, that 10% overhead, is because the plant needs to live. So you want dead stuff. Okay? So this is a dead stuff problem. because I don't have to pay the energy cost for living, and dead is inorganic chemistry. So it's intrinsically an inorganic chemistry problem to boot. But let's look at, I can't help that either. Let's look at this, though, and learn from it. So what happens, and I'm going to leave out all the details of photosynthesis. What happens, though, is a photon comes in, and like Nate said, you set up a wireless current. And that's where all the engineering is in here. It's to set up that wireless current. It's to do light collection and set up the wireless current. What it then does is it slaps two catalysts at the end of the wireless current. So it puts a cathode over here, and it puts an anode over here. And photosynthesis had to do that. Because if you look at the solar spectrum, it can't, remember, water splitting is a 4-electron process, 4-proton process. If you look at the thermodynamic potential of water and you were to try to do it 1 photon, 2 electrons, so 1 photon comes, I move 2 electrons, you would start moving up into the UV. And you would be outside the visible spectral region. So photosynthesis was stuck. It was stuck taking 1 photon to 1 electron hole wireless current, but then at the end of the day, it has to drive a multi-electron, multi-proton reaction. So what it had to do is put in catalytic storage sites at the end network of this 1 electron charge separating species. And then the holes are stored in this anode, the oxygen evolving complex. And then the electrons are stored in photosystem 1. So that's the lesson you take from this, is in this exactly what Nate was talking about. Segment catalysis from light collection and conversion. And I really think it's a losing battle to try to make one thing to do everything. And it turns out, of course, you need both the oxygen and hydrogen to get maximum energy storage out of water. Water is renewable. The biggest problem, we have we have platinum that works great for hydrogen. It's rare. Okay. We have other catalysts to do hydrogen. The thing that's been difficult is the oxygen, getting this other side out. Platinum does not work well with oxygen. It's just not compatible chemically with oxygen. And so the real issue is, for us, this is the problem we attacked, is how do we do this efficiently under simple, cheap, highly manufacturable conditions? And in December, we decided to backtrack, because we weren't getting very far. Everything we did, we had ruthenium. There's ruthenium oxide catalysts. There were molecular compounds. We would get 100 turnovers, 1,000 turnovers. We didn't even publish those papers. The catalysts would die. So what we did, I'm going to just lead you through the last 8 months in the group, and I'll show you the student who did this or started it. But we just sort of had a self-help session. As a lot of you know, I need those sessions frequently. And so we decided to have a little sort of therapy session in December called group meeting. And we just said, let's go back to photosynthesis and let's start evaluating our biases. And we realized we had tremendous biases. So here's the first one. Photosynthesis. There's Jim Barber's crystal structure, an amazing, I think, one of the most amazing contributions in the last few decades to science, just because I love photosynthesis. He got the crystal structure. The Berlin group has, and then the Berkeley group in XF. So those 3 groups have put in front of us now what the leaf looks like and what the machinery looks like. So we have the Kodak moment of photosynthesis. And that looks really complicated, and the complexity is overwhelming. But then we started looking at this and said, in terms of making oxygen, getting that oxygen side, this is a little piece of rock. It's manganese, oxygen, calcium, oxygen, manganese. That's it. So you look at this incredible complexity of photosynthesis, but you realize the thing that's making oxygen is a piece of rock, just simple metals with oxides in a cube. The next thing you realize, and Nate alluded to this, and this is the one that really messed us up, and we realized how much of our life was getting sidetracked by this problem. If you're in this business, Eric is in the business, he was talking about catalysis. You make a catalyst, what's the first question they always ask? How stable is it? How stable is it? How stable is it? And so this is what inorganic chemists do. We finally can induce stability. We will make ligands and put them around metals, and I don't care what you do to that metal. We'll try to make that metal be stable under whatever oxidation state you want. And we realize that's a mistake. And the reason is you come to this system, and this is what Nate was talking about in terms of overhead. This is the D1 protein. This cluster sits in that D1 protein. And around every 30 minutes, 40 minutes, it's so oxidizing in there that this system starts off and will take sulfate. From sulfate, it makes cysteine and then sets up a biosynthetic pathway. Every 30 minutes, it remakes the D1 protein and then reinserts the manganese cluster. So this thing is massively unstable. But you don't care because it seems to work. So here was the thing we had to release ourselves from for this problem. When we started talking about stability, and I know, again, this sounds simple, but you can't believe. I mean, it's just, I guess, our biases was messing us up. It's functionally stable. When we say stable in this game, what we're really saying is functionally stable. A lot of times people misinterpret that as structurally stable. This is massively unstable structurally, but it's functionally stable. And then finally, O2 is made from neutral water, low over potential. You need proton carriers. So these were the things we decided to retarget in the design. And now I'll just quickly go through a catalyst design. There were two other pieces of information we had. And one is this is photosynthesis. Light comes in, and you're making oxygen and hydrogen. Hydrogen goes into sugar. You eat the green leaf. When you eat the green leaf, it goes into your body. In your mitochondria, you have the fuel cell, cytochrome C oxidase. It literally undoes what photosynthesis does. It takes O2 plus 4 protons and 4 electrons and goes to water. Whether you realize it or not, I mean, this is, just think about it. When you eat green leafy vegetables, what do you chew on? You're not chewing on the plant, you're chewing on the sun. Because those photons literally got stored in those bonds, which is released from cytochrome C oxidase. So when you chew leafy vegetables, you're just crunching the sun. You're eating it. And that's because of this thing, cytochrome C oxidase. Now, why was that important to us? This was my old friend. He actually taught me everything about photosynthesis when I was a young guy. Jerry was one of the few people who could have done this. By the way, he's died because of lung cancer. I have like 1,000 pictures of Jerry, and not one doesn't have a cigarette in his mouth. I just tried to find one without a cigarette. I couldn't. But Jerry is the only guy who could have said something like this because he studied this, photosystem 2. He was the guy who identified the tyrosine radical in photosystem 2, the famous tyrosine radical for the experts. And what Jerry had done is said, and I've dressed this up with the new structure. He used the old structure. The new structure wasn't known at the time. But Jerry even said, not only is it sort of the thermodynamic reverse, but look at this chemically. To make O2, this is one of the prevailing thoughts of making O2, that a hydroxide, this deprotonates, hydroxide attacks oxo, you make an OO bond. It's not very different than Eric's chemistry. A nucleophile is hitting an electrophilic oxygen. When Eric does his chemistry, it's a nucleophilic olefin. So a lot of the work, just again to show you the complexity of these problems, a lot of our design has been following Eric's manganese oxo work. Because it's the same thing, I'm just going to use a different nucleophile, hydroxide. Jerry was also studying cytochrome C oxidase by Raman spectroscopy, and these are the postulated intermediates of cytochrome C oxidase. It's exactly the opposite. I mean, that I still find, this is when nature is beating you over the head. Not only is it thermodynamically the same way, it's almost down to the microscopic atoms of how you make and break bonds that's undoing it. And you look a lot different than a leaf. But chemically, you aren't.
Smarter.
What? I don't know. Leaves are pretty smart. And then we had, so what we did, to start studying this, a few years ago, we started studying the O2 reduction process. And I don't want to go through this whole thing. A lot of you know we spent a lot of our life studying this idea of proton-coupled EDT. How do you couple electrons to protons to drive multi-electron reactions? This was incredibly important to that understanding. If you look at this, oxygen goes in, and I'm picking up one electron. Cobalt 2,3 goes to 3,3, so I go to superoxide. What we figured out for the O2 reduction problem in these cycles, this is the key intermediate. If this is basic enough, it takes up a proton, and then it drives a 2-electron reaction. So that's the PCET. You couple a proton to drive the multi-electron reaction. If we made these systems where this wasn't basic enough, it wouldn't pick up a proton. It would simply pick up an electron and then release peroxide, which you don't want to do in a fuel cell. In a fuel cell, you want to go O2 to water. So there's lots of lessons here. First, cobalt's a good metal for handling oxygen. Part of the reason is it doesn't make too strong a metal-oxo bond, so you can get it on and off. Secondly, you want to do this is sort of the Jerry intermediate, the oxo-hydroxy. It's all here, and you got a couple proton transfer to get there. So we spent 3 years learning about how to run the downhill reaction. And then we were presented with a few problems to go the other way. And so here's the first one, and now you'll understand why we were so bothered by the stability issue. There is not one mechanism. So if you come back here, every single time you're going from cobalt 2 to cobalt 4. There is no way to avoid these oxidation states with cobalt. You're always going to have, no matter what mechanism, if I do this is kind of a radical coupling mechanism, or if I do the sort of Eric Jacobson nucleophilic attack on an oxo, I'm at cobalt 4, I'm on cobalt 3. So now we'll go to freshman chemistry. The rest of this is a freshman chemistry lecture. You take cobalt 4 or 3. It's a D6 cobalt. Harry, my old boss, got his PhD with Basolo telling everybody when you're D6, you are substitutionally inert. It's a rock. When you go to D7, you go high spin and the ligands begin exchanging. That's cobalt 2. So I have a real problem on my hands. If I'm going to cobalt 2, this thing is going to lose ligands. It's unstable structurally. If it's here, it's stable. Now, I told you inorganic chemists can almost do anything, and we can. So what do you do? How do you attack this problem usually? Well, it's unstable. I will enforce a ligand geometry so that it can never come off. I'll put a chelating. I'll put it in a cage. So that's what inorganic chemists do. What's the problem there? It's the ligand field argument. If that ligand structure is stable for cobalt 3, I'm telling you it has to be unstable for cobalt 2. If I force the ligand to stay on cobalt, I'm doomed, because I'm going to have the overpotential of forcing the electron into this electronically unfavorable situation. So what we started to realize is we're always building in overpotential. So we don't want to do that. We want this to be unstable. And then, so I'm just connecting the dots of how we work through this problem. So we have cobalt 2 we know is going to be unstable. Cobalt 3 we know is really stable. There's 9 orders of magnitude difference in this stability issue. So that is a good thing. That gave us an inkling of how to control this cobalt. Cobalt 2 becomes unstable, but if I bring it back to cobalt 3, it will go back together again. And you got to figure, so what we started thinking is we could establish a healing mechanism, sort of a repair mechanism, a simpler one than the leaf, that if we do make cobalt 2 and it does escape, we can bring it back to cobalt 3. The next thing is what do you do it with? And we
literally went to the freshman chemistry books. This is 1 KSP we could get. Now, this isn't cobalt, that's calcium, but that's 2 plus 2 minus. Cobalt is 2 plus 2 minus. So that's kind of our electrostatic, bringing a 2 plus 2 minus together involving phosphate. And then what we knew is if we put these ligand field arguments in, D7 is going to be high spin, unstable. So it's going to have a smaller KSP, or bigger KSP. This will have a smaller KSP because it's cobalt 3. So phosphate looked good to us to be this carrier, this transporter of cobalt if it were to become unstable. And then this guy, Steve Reese, we have been studying proton-coupled electron transfer for years. And in 2007, we worked out lots of details. As some of you know, I worked with Joanne Stubbe on ribonucleotide reductase. It's a big enzyme in your body that does radical enzymology based on tyrosine. And the way we figured out how to activate tyrosine in ribonucleotide reductase is we can put on end caps to the peptides, drive electron transfer this way, but we need to dump the proton. And what this study showed is that HPO42- is perfect for this proton-coupled ET, absorbing the proton. Now, you're in water. You can't absorb the proton with H2O because you make a strong acid, H3O+. So even though there's a ton of water around, it's a lousy base for protons. You can go to OH- if you want to stay under simple pH 7 conditions, but the problem is there's not enough of it. So the phosphate ends up being the thing you couple electron transfer to. So phosphate had two purposes for us. One is it could give us a repair mechanism, and then secondly, it could be the proton carrier in the activation of this cobalt in the oxygen-oxygen bond breaking. So here's Matt Cannon. He's an organic chemist from Harvard, worked for David Liu, came to my group to learn some inorganic chemistry. And I'm just showing you because this is such a terrible cell design. Over here is a piece of glass. We use ITO. You can use any conducting surface. We used ITO because it has a big overpotential for making O2. We didn't want to get confused by the electrode participating. So it's pure glass. You can see through it. Over here's platinum. Here's a frit. Here, and we just put water, and then we put the phosphate in there, HPO42-. This is how simple it is. Turn on the potential. You go up. In our case, this is 1.3 volts versus NHE. Remember, making water to O2 is around 0.9, so we're a 4/10 past where we should be. This is to prepare the electrode. And you'll start seeing current rise. So the current's going up. So the electrode is absorbing current. And if you look at different periods, you start seeing this cobalt phosphate film forming. Absolutely amorphous. Okay. You can grow it to any thickness you want, pull it out, and then put it in pure phosphate, and you can control the film thickness. If you just leave it in, it will go to around 2 to 3 microns. But we can grow this to around 50 nanometers. It will go on any surface, over any area you have, over any geometry, which is good if you remember Nate's talk about all those little trees, because we're going to have to get this catalyst on there. It's an amorphous material. And this thing, when you're looking at it as the film's forming, you're seeing lots of oxygen come off. And what I'm showing you here is that all the oxygen's coming from water. If you use isotopically labeled water, here are the predicted isotopic statistical amounts of 16, 16, 16, 18, 18, 18, and we're dead on. So every bit of oxygen's coming from water. Phosphate is not decomposing. We've done the P31. There's nothing else. Cobalt can't make oxygen. It can't transform into oxygen. So everything's coming out of water. If we extrapolate, the overpotential is around 0.3 volts, 0.28 volts. There's a pH dependence that you can basically turn into an overpotential. And the reason why that pH dependence is interesting is, and we're pretty sure of this now, we're doing in situ XF studies. We can see the cobalt-3 and cobalt-4. And it's just like that cycle I showed you with the porphyrin. It looks like it's a cobalt-3 hydroxide. You oxidize, this is sitting on an electrode, you bring it up to cobalt-4 in a proton-coupled electron transfer step, and you make that cobalt oxide. And that's where we see O2 production. So we're doing a lot of in situ XFs. We even have almost the structure of the active site. It's going to be a big surprise to people. It is a molecular entity, and it doesn't look a lot different than the oxygen evolving complex of photosystem 2. So it's an oxo cube. You can use methyl phosphates, so you can use other buffers. This is methyl phosphate. What's cool about this is you can put it into chloride. Now, usually you make chlorine or hypochlorite in salt water. This is up to 0.5 molar. This is 0.5 molar sodium chloride, and you can see that we're beating out at this pH and this overpotential. We're beating out chlorine production. So you can use salt water and you can make O2. And then these are our latest results. Remember, I talked about this repair mechanism. We can make 32 isotopically labeled phosphate. And you can watch, if you have this under potential, you see phosphate exchanging. So we put hot phosphate, we make the hot phosphate electrode, and then just put it in a cold phosphate solution. You start seeing the hot phosphate show up. If you turn the potential off, remember, you're cycling. If I turn the potential off, then it has more time to go to cobalt-2. It's substitutionally labeled. You get more phosphate in solution. So when you're under cycling, you're not making cobalt-2, or you're reoxidizing it more quickly so the phosphate can't get out. Danny has also done hot cobalt. So here's 57 cobalt. If you turn the potential off, you just make the hot cobalt and put it in a pure phosphate solution, you'll see cobalt showing up in solution. If you then turn the potential on, you see the cobalt getting sucked up. Turn the potential off, it starts going off. Turn the potential on, it goes right back on. So that is unequivocal evidence of this exchange mechanism. I want to enforce, it's not a lot. This is only 2%. So the thing's pretty stable. But even the little parts, because you are making cobalt-2, it is substitutionally labile. We have this repair mechanism. So these films are just stable. You can let them go for days. They just don't change in phosphate. So this is, I'm just going to give you the quick mechanism, is you can take cobalt-2 to 3. Once it's to 3, phosphate puts it on the electrode. You get to cobalt-4 oxide. We still need to nail this down, but all the XFs, beautiful edge for cobalt-4 oxide. We've been doing this at Stanford in the linear accelerator. We can do it in situ while the electrode's running. We come in the back on a mylar electrode. That thing then makes O2. You come to cobalt-2. You reoxidize that up. If some of it falls off in solution, you pick it up with phosphate and you repair it. So that's how the cycle's working. I don't look at it as homogeneous or heterogeneous. It's both, okay? It's all occurring at a molecular center. We wouldn't be able to beat out chloride if it wasn't. If you had a density of states in a solid state material, you would be oxidizing chloride to chlorine. The bottom line is the outer sphere electron transfer of chloride to chlorine just can't beat out the inner sphere reaction of oxygen. That's very molecular thinking. And because it's a molecular system, we have the ability to control it. I showed you a milliamp per centimeter squared. Just increasing the surface area, and this is in methylphosphonate. We just bring up the phosphate buffer. And now you get up to 10. This is 10 milliamps per centimeter squared. Here's the O2 being made. This is real time. Then over here we're making hydrogen. Now we're applying a potential to this. I'll get to that in a minute. Here's the electrode, a close-up of the electrode. The O2 is pouring off of this. We think it's running per cobalt right now at around 200 to 1,000 turnovers per cobalt per second. So this thing is really churning it out. Where we have a terrible cell design. Well, let's look at this. This is what manganese is. It's self-assembled from manganese. Actually, upon oxidation, the core self-assembles. This is self-assembled from cobalt. Cobalt's pretty cheap, not like iron, but if you remember Nate's chart, it's in a good zone. You have phosphate to do the equilibrium in place of the D1 protein, and everything that's happening in terms of O2 generation here, we're able to do here, and it's better because it's cheap. This is expensive to do. It's highly manufacturable, and it works in the presence of impurity ions. This is what we're doing now, though. Remember, an electrical current's coming out of the wall. So now you see where Nate and I are like this, because now, again, you separate catalyst function from charge collection. And this stuff you can just lay down on any surface. So I think we're ready to go for Nate right now. And so you drive this, and then you do this reaction. And that will have all the things like Nate said of an artificial leaf. And I just want to tell you something to recalibrate. If I just take this catalyst with the ohmic drop, because we have ohmic drop, I got to move protons from one electrode to the other side. All right? And I take that ohmic drop, I take the overpotential on cobalt, and then I had platinum on the other side. In this calculation, we've been able to use a nickel alloy, and we're 0.2 volt over for hydrogen production to get rid of the platinum. Taking all of just that function of the catalyst for 30 meters squared PV, run-of-the-mill PV, I think this was for 12%, you get 6 million amps. The average house needs 20 kilowatt hours a day. That's only 5.5 liters. This is you're not dealing with a lot of water. You can store the amount of storage that an average house in America uses. That means this thing was running at 10 milliamps. By the way, if we go up to, right now we have stuff from Corning, 250 meters squared. Okay, so this is a cheap catalyst. You can just put as big a surface area as you want in the smallest area. In 2.5 hours, you generate enough hydrogen, you do enough hydrogen storage. For that part, I mean, in the full system, you got to send it through a fuel cell, so multiply by another 2 hours. The point of this is you're already in the ballpark to start thinking about doing storage at a local level. So this thing, I don't think is as far off as scientists believe, because you can just see with the science that Nate and I are talking about, we aren't that far off of taking care of this vision. I really believe it. We went to the damn moon. Are you telling me we can't do this when we're almost in the ballpark? And this is the deal. We've done it before. So 70s mainframe, then PCs, and look what happened to mainframes. Right? Here's the mainframe of energy, personalized energy. Look what happens to the mainframe. So I am out to destroy the grid. I mean, I get people, I really am. I will destroy the grid. I'm committed to destroying the grid. And it's an easier problem because in this system, you have to re-network. In this system, the end user, you're done. Right? Maybe in a smart community, you might have a little networking. But it's a much easier problem in terms of a systems problem. So let me tell you where we are. This is the last slide. In this instance, just using this as an electrolyzer. So you can make a cheap electrolyzer now. We're making cheap electrolyzers out of plastic using this stuff in water. That's something we're doing in our lab right now. This is cheap. But in the full system, you have also the PV, what Nate talked about, the fuel storage. If it's hydrogen, you got to do compression. And then you need the fuel cell. All right? If you use batteries, you can dump this, but I can already tell you, I'm doing a big energy study. Batteries are never going to be economically competitive. They have no hope because of this 3 order of magnitude energy density problem. So drive your cars on them, but you're not going to be storing this amount of energy with them. So here's the 4 components. Let me just tell you what's happened since the discovery. If anything, it's become like a lightning rod for this personalized energy thing. So you've got to start partnering to do this. I'll tell you who the PV company is. It is Wacker. They're ready to go with large-scale manufacturing to try to figure out exactly what Nate says to get costs down, to try to make, and then put this catalyst on it. This part I wasn't so confident about this when I was on. At first I said 10 years. Then I was on CNN and I said somebody said, how come scientists always say 10 years? So then when I went on CNBC, I said 8.1254 years. And now I'm down to 5 years. I really believe it. And it's not because of this discovery. This part, fuel storage and fuel cell, Air Liquide's vice president, she got on a plane the day the paper came out, was in my office that morning. They have amazing technologies that have been sitting on their shelf. So this whole thing right now is let's now do design to cost and not over-design for this personalized energy need, especially in the developing world. So this is just using the system as it is now. The people I decided to partner with were not energy people. It's always yes, but, yes, but, yes, but. We have a grid. You're crazy. You know what the PC guys, they've already done it. So you know the names of the people who are signing up for this. So it's the Sun Microsystem guys. It's the Ethernet guys. It's the Mac guy. Okay? They really want to do this now. But what Nate was saying is, in all of these things, why doesn't the third world or developing world have a grid? Because they don't have money. So you can't they can't buy this either, right? So this whole thing is, what science are you going to do to keep driving costs down? And now I don't need to talk to you about this. This is exactly what Nate said. But this is now easy to interface. We have a nickel alloy that's kind of okay. It's working in water. Now, why is that important? Look what you do there. That's a big cost saving. So I don't know how a lot of you feel, but once you start working through these numbers, this idea of personalized energy is not far off. And now I will tell you, there's a really committed team of people, some really famous business people actually on the board of Caltech, who are they've come out of retirement. We talked them out of retirement, and they are supercharged to see this go. And I don't think it has to be far off. And so now we have to do the hardcore reality of what we really need to get back to your question, Mark, and then do design to cost. It turns out very few people have done those calculations. They kind of throw numbers around, but really haven't, especially in the developing world. I will tell you here, we have all of India taken care of for distribution. So the Tata brothers are ready to go. We have North Africa ready to go. China's a much more complicated beast. We're working on that. But I'm going to give myself 5 years. If I don't do it, you can make all the fun you want out of it. Okay, with that, thank you for your attention. Yeah. Yeah. Well, so that was kind of in that number that I was using at that 20 milliamp. That's sort of your run-of-the-mill 12%. I think it was 280 watts per meter squared. So that's what that number is right there. Average. That's average. That's what you want with storage.
Yeah, I mean, your whole point here is storage that carries you through.
It's the storage. I mean, I was at the Clinton Global Initiative, and I was there with T. Boone. And we all had to just give one word. And I forgot what T. Boone said. But, money. But it's just storage. That's the only word. So it's just storage right now, I think. I'm simplifying the problem. Look, PV has real costs. So there's got to still be an amazing amount of science done. But I really believe we're capable, and I think we're missing the point by not selling this to the public. I will tell you, after this came out, I literally have over 10 to 15,000 emails from people who said, please use my house. It's an incredibly empowering concept. This energy thing people are afraid of. It's over there. It's from a foreign country. All of a sudden, they're saying, wait, I could live like this? Why hasn't anybody at least had this discussion with us? I will tell you, the Senate got overwhelmed with messages, so now the Senate wants to see me just to find out what the hell I'm talking about. But I don't see why, as a community, we should not be selling this message. I think it's doable. Of course, it's going to be with huge commitment. You're going to empower the scientific community, right? So it's not going to happen the way it's getting funded now. But if we went to the moon, you're telling me I can't do this? And I will tell you the number of technologies that have come through my office from these big companies, like, it is stunning.
that the capstone speaker of this incredible symposium is Ralph Cicerone. Ralph Cicerone has been a major leader in science, in education, and in public service, and even in baseball. And he has made really significant contributions in all of these areas, and I think has had a tremendous impact on the world because of his leadership. And I think it's very special for us to have him as the final speaker. And he's currently the president of the National Academy of Sciences, and his topic today is putting science to work in developing science policy.
Thank you, John. I'm certainly enjoying today. I think one of the beauties of a career in science is that you make friends who become almost as important as some extended members of your family. And I've seen some of those old friends today, and making new ones, it really feels good. And certainly the subject of today has been enormously exciting and very important. This title of my talk isn't exactly what was printed, and it isn't the title that I chose. In fact, Mark and I can't figure out where the title came from. I thought he chose the title. He says my secretary did because I didn't furnish a title when I was supposed to. But when I saw the title, I said, why not? So give it a try. Let's see. So here's a quick outline of what I want to do. We've heard a tremendous portrayal of some of the facts and projections and deductions that people are making. I want to give just a quick version of my own background on the climate constraint that we're looking at, that we face, although this is obviously nowhere near the full story. And of course, the biggest part of that constraint is fossil fuel use to furnish energy. It's a huge challenge. And I want to go over some of the goals and constraints on energy pathways, but the issue there is that climate is not the only constraint. It's not the only challenge. And when you begin to mix in the other constraints and challenges we have due to energy needs and energy usage, the choices become more complicated. And the bottom line is something that won't surprise any of you, but I have just a few examples to illustrate why we really should expect more progress from science and technology than we're going to see from human behavior changes. And in fact, we're going to need it very much. So this is a cartoon of something that Jim Anderson referred to and other people did. Kim, it's from an old paper of ROM, 1989. Only I changed a couple of numbers here and there. To a first approximation, to a very good approximation, the Earth's climate is simply controlled by the planetary energy balance, certainly over periods of time that are more than a couple of years. And the input side of the energy budget is 342, slightly less than 342 watts per square meter, averaged over day and night and averaged over the entire year. About 105 watts, and I'm sorry for those of you who are looking at the other screen, but about 105 watts is reflected directly from the tops of white clouds and white shirts and reflecting water and everything else, snow and ice. The remaining 237 is absorbed by something in the atmosphere or Earth's surface. These numbers are all measured pretty well, so this is not just a theoretical calculation of a Stefan Boltzmann law or something from the temperature of the sun. That's not it. They're mostly measured pretty well. And as Jim Anderson pointed out earlier today, to be in a approximate energy balance, that means that 237 watts per square meter are radiated back out to space by the Earth atmosphere system, but the radiation from the surface of the Earth is considerably larger in blackbody radiation. Now, the presence of a few greenhouse gases in the atmosphere, water vapor, carbon dioxide, and ozone, is just to emphasize several of the natural greenhouse gases. But if those gases didn't exist, we could calculate the temperature of the surface of the Earth very easily. In fact, we can do that calculation for Mars from measured sunlight intensities as well as the reflectivity of the surface of Mars, and we got the right answer. There are day-night variations on Mars, but you got the average perfectly. If you try to do the same calculation for Earth, you calculate a temperature which is sub-freezing. In other words, you underestimate the temperature greatly, and it's because of the greenhouse gases, as Jim said, causing more infrared radiation flow around the near surface. And as I think Kim also mentioned, the re-radiation, the greenhouse effect is simpler than simply decreasing the energy emitted to space. It's much more complicated, but if you try to do the same calculation for Earth, as I said, you calculate that the Earth is sub-freezing. We know that's not true. It's only when you include the presence of greenhouse gases that you can calculate the correct temperature. Similarly, for Venus, we would undercalculate the temperature by several hundred degrees because Venus has such a thick atmosphere, largely CO2. So the greenhouse effect is real. The issue is, of course, that we're adding greenhouse gases. Now, the classical graph, it's been said many times that this is perhaps the only scientific graph that's been shown in the White House from time to time over the last 20 years, is this one. It represents, each of these dots represents the average of measurements taken about every hour on the slopes of Mauna Loa and done almost entirely by Dave Keeling over the course of his career until he died 2.5 years ago, and it's been continued by his son, Ralph Keeling, who was one of Jim's students, and by any number of other scientists around the world using all kinds of independent techniques. There's no question that you got this kind of a behavior of CO2. Now, I can remember around 1970 when I first met Don Stedman, we were trying to do some calculations having to do with acid rain, and we thought we'd start with the carbonic acid content of acid rain. So I asked Don, how much CO2 is in their atmosphere? So he went to a book written in 1963, the first book written on atmospheric chemistry by Christian Junge, who was a Max Planck Institute director, and it said 310 parts per million. So Don told me there were 310 parts per million. So Junge's book written here was talking about the late 70s. You've all heard the story how when Al Gore was an undergraduate at Harvard and Roger Revelle was teaching a course, he showed the first couple of years of data back here showing that CO2 was increasing. But the number was around 316 parts per million. And as Jim Anderson said earlier today, the globally average number in clean air is something between 385 and 390 parts per billion. And that we know about the time of the Industrial Revolution, the number was about 280 parts per million. We know that from dated ice cores taken in areas of high snow and ice accumulation so that you can get a high time resolution in the dating of the samples. So direct measurements of gases trapped in ice cores tell us how much CO2 there has been in air over the last couple of thousand years, in fact, back 700,000 years. We know that in periods of glaciation, carbon dioxide amounts were about 180 parts per million, up to about 200 parts per million. In the interglacial warm periods of the last 700,000 years, the carbon dioxide amounts were between about 270 and 290 parts per million. So this is well out of the range, and Jim Anderson showed you some of those data. Now, the other thing about this, well, we'll skip all the annual cycles caused by photosynthesis and respiration and decay, and just look at the underlying trend. The red graph is actually data from the South Pole because the annual cycles there are so small, the seasonal cycles. The underlying trend tells you how much carbon dioxide has accumulated in the air every year, and it turns out to be approximately the same as that produced by fossil fuel burning, only it's really only about 60%. So every year, in fact, the number is surprisingly consistent. Over this 50-year period, the fraction of the CO2 released in fossil fuel burning that is visible in the air from accumulation each year is about 60%, 57, 58%. And I'll tell you where we think the rest of the carbon dioxide goes later. This is not the only greenhouse gas that humans are influencing. This is a section of data over the last 30 years of nitrous oxide at a number of stations around the world These are now parts per billion, dry air mole fraction, showing, again, essentially a factor of 1,000 less than carbon dioxide. But nitrous oxide is also increasing. Similar story with ice cores. That going back to the Industrial Revolution, the ice core record of nitrous oxide was off the chart below. We're not quite as sure where the nitrous oxide is coming from, but it's certainly related to the global nitrogen cycle, fixation of nitrogen, assimilation of ammonium into plant material in animals, then death and decay, nitrification, denitrification, releasing N2O. So, and of course, nitrogen fertilizer is very, very important in producing world food supply. We're now producing more synthetic nitrogen fertilizer than natural nitrogen fixation produces by about a factor of 2. And as human demography, the protein needs are highest in the teenage years. As long as we have a young and growing population, the demands for nitrogen fertilizer are going to be great. You know, it's an expensive product, and one of the holy grails of many people is to try to produce nitrogen fertilizer microbially using tricks from molecular biology and genetics, and we hope that works someday. It will save a lot of money and energy and natural gas. But the exhaust end of the nitrogen cycle that releases the nitrous oxide back into the atmosphere will continue to work, and we expect to see probably increasing rates of release of nitrous oxide into the atmosphere. About 20, 25 years ago, several of us were trying to figure out the role of the other trace gases along with CO2 and how they would increase in the future. And at that time, we calculated that these other trace gases like chlorofluorocarbons and nitrous oxide and a few others would essentially double the carbon dioxide greenhouse effect. And fortunately, it has turned out to be slower than that, largely due to the control of chlorofluorocarbons. Well, I'm going to start to move more into science policy. You've heard some really complicated things today, and I doubt there are many people in this room who understood every detail of every presentation. That's the way science works. We go deeper and deeper into our specialized fields, and it's wonderful and impressive, but it's increasingly difficult to communicate with the public because there's so much vocabulary, so many concepts, and so much of an empirical base that we do. It gets harder, so we have to establish a framework. Should the public care about any of this? And you've heard the energy picture. Well, one very interesting guide to scientific policy that was developed, and of course we never show them the integral signs, but the gist of it is a way to compare all of these radiatively active greenhouse gases that have the property of being infrared active between about 6 micrometers and 16 micrometers, where the bulk of the outgoing planetary radiation is. It's called a global warming potential, and it's the ratio of two integrals, where X represents the concentration in air of a gas in response to a pulse of an input. So if you put a puff of, say, a chlorofluorocarbon into the atmosphere, X of t describes the way it decays. So if it were a simple single time constant and there were a rate of decay, let's say 100-year lifetime, then the response to an impulse function would be an exponential decline with a 1 over t time constant of about 100 years. So that's the impulse response. The A is the radiative efficiency of each gas, which stems from its infrared signature, line intensities, pressure broadening, band intensities, as it turns out, pressure broadening effects, location in the spectrum, and whether or not that particular absorption feature interferes with some other absorption feature that's competing for the same infrared photons. And the integral from 0 to th is a measure of the effectiveness then of that gas due to its concentration and its time decay multiplied by the spectroscopic properties, of course measured in the laboratory, integrated over some time horizon. And this global warming potential has been adopted as a way to compare all the other greenhouse gases with carbon dioxide, taking carbon dioxide as the normalization integrating over some time horizon. But you heard earlier today, I think it was Nate Lewis? Who was it who talked about the different time constants of carbon dioxide? That you can begin to see that even this tool doesn't get you a clear answer. So I'm going to show you a few of these numbers now. And this is a little hard to read, but you see carbon dioxide across the top. And I said multiple time constants. But there's certain numbers for radiative efficiency measured in watts per square meter per part per billion. And then the so-called global warming potential integrated over 20 years, 100 years, and what's the other one? 500 years. And by definition, carbon dioxide is 1. But now compare other greenhouse gases. Methane. The lifetime is fairly definitely known to within probably 15%. It's due to hydroxyl radical attack on methane. It's pretty well known to be about 12 years. And its global warming potential is 72 times that of carbon dioxide, meaning a mole of methane is 72 times more effective as a greenhouse gas than a mole of carbon dioxide injected. However, if you integrate over 100 years, the number comes down to 25. And if you integrate over 500 years, the number goes down to 8 because the methane pulse has decayed. Well, why have we settled on this 100-year time horizon? It's been just putting a finger to the wind, saying 100 years seems more relevant for human policy response. But in fact, it might be easier for us to manipulate methane concentrations and to cause a decrease in atmospheric methane in 10 years than trying to do things that are going to affect carbon dioxide over 100 years. I only want to point out a couple more of these numbers. Look at nitrous oxide. Global warming potential of between 300 and 150 times that of CO2. So even though the concentration is a factor of 1,000 less, the impact of N2O is not 1,000 times less than carbon dioxide. It's only a multiple because of this large global warming potential. Look down at the bottom, though, at the synthetic chemicals. Carbon tetrafluoride, which I don't think I ever had more fun, maybe a little bit more in research than calculating properties of carbon tetrafluoride back in the 70s. I calculated that the survival time of a carbon tetrafluoride molecule in air is tens of thousands of years. In fact, it takes some really exotic excited state chemistry in the upper reaches of the atmosphere to destroy the stuff, as you might guess. There are very few carbon-fluorine bonds known in nature in the first place. This is really synthetic, symmetric, and it has very strong infrared properties so that its global warming potential, if you integrate only to 20 years, is 8,600. If you integrate for 500 years, it's 18,000. Recently, it's been shown that sulfur hexafluoride has a global warming potential just as large, even larger, due to its spectroscopy. And a new calculation just earlier this year showed that nitrogen trifluoride, Michael Prather and his colleague revised earlier numbers to show that nitrogen trifluoride, which, by the way, has not been included in anybody's work previously as a greenhouse gas needing a policy response. Interestingly, nitrogen trifluoride is used in semiconductor industry for cleaning and as a fluorine donor for etching in a way to replace perfluoroethane and carbon tetrafluoride. So these are some inadvertent things that happen. They cannot be completely ignored, and I'll show you just one graph. These calculations are now fairly easy to do, and that is, if you'll remember those numbers from my first cartoon graph of the energy budget of the planet, it shows that the combined effect of these greenhouse gases is about 2.6 watts per square meter now. That's due to the concentration increase that's been observed in the last several decades, an increase which is due in every case to human activities. Fossil fuel emissions of carbon dioxide, I'll give you a little bit more detail of that. Methane is the second most important greenhouse gas. And Kim pointed out that black carbon is estimated to be somewhere in here now, much more uncertain but significant, and so forth. Anyhow, this total extra forcing is about 1.1%, 1.2% of the solar constant. You can pick up encyclopedias and read about geological changes, and people have speculated that the sun has caused. Jim gave more details on this morning, but what I wanted to say is that there is no model of stellar evolution, there is no mechanism we know of that would cause the sun's output to change by this much, and that our current first principle climate models have said if it did, we would have large climate changes. So this is a significant perturbation wherever it's leading us. That is the perturbation on the planetary energy budget due to these human-forced greenhouse gases. Now, this graph is from Judith Lean. Some of you may know her. She's a physicist who works for the Naval Research Lab. She's a very good experimental solar physicist. And it shows measurements that she and her colleague in Switzerland, Klaus Freilich, have strung together from several satellite instruments showing the output of the sun, solar irradiance, total energy, total power, measured at Earth orbit. And you'll notice, those of you with sharp eyes, that this is exactly 4 times 342. There's a factor of 4 pi and 4, or 4 pi and 4, so you end up, the geometry, if you change the units, you get exactly what I said, and this is the right measure. The point of it is, it's the first time in human history that the solar input to the Earth has been measured with enough precision to be able to say, is the sun changing? Could it be causing this observed climate warming, which none of us have shown you the evidence for yet today? And the answer is no. The peak-to-peak variability is 0.1%, and I just told you that the greenhouse effect of the human-caused greenhouse chemicals is 11 or 12 times larger. This is an oscillatory periodic function, and the human-caused enhanced greenhouse effect is sustained and growing. It's not oscillatory. So until about 7 or 8 years ago, I think we were fairly free to say, maybe the sun's minor variability is causing the observed climate change of the last half of the 20th century. You can't do it anymore. This really shows that the sun's variability is not causing the observed climate changes. A few more words on methane, and then I'll get back to the main story. About 20 years ago, we did this work. There have been some modifications to it, but the red part of the pie chart shows methane release rates on an annual basis due to activities that are under the control or at least the impact of humans. And the yellow part of the curve is natural methane sources. Well, it turns out that this picture, we constructed this from a lot of direct measurements, the known lifetime of methane, and some isotopic data on the isotopic concentration, isotopic composition of methane, deuterium, carbon-13, and carbon-14, to place constraints on all of these. And I'll say that the best known number, the one we're most sure of, is the enteric fermentation by cattle at about 80 million tons of methane a year. That one is really well known and has been well known for a long time. Some of the numbers that are not so well known are rice paddies. Despite a lot of efforts, this number is still very uncertain. But the overall picture is about right, because we know that atmospheric methane concentrations have risen by about a factor of 2.5 or 3 in the last 100 years, and that's the red part. If we only had the yellow part, atmospheric methane concentrations would be down by about 70%. So the big picture fits. We think we're pretty good on the methane picture, but not perfect. Okay, now, several people mentioned related facts, but the growth rate in the use of fossil fuels to convert energy over the last couple of 100 years has been staggering, and the current number of the global release of carbon dioxide just from the burning of fossil fuel is about 8 billion tons a year of carbon. Just several years ago, it was 6 or 7 billion tons, so it's growing rapidly, and the color breakdown is just the different forms of fossil energy. Now, in addition to this release rate of carbon dioxide, there's probably another 2 billion tons a year of carbon dioxide being released by human activity from deforestation, mostly tropical deforestation for agriculture. It's not just the burning of the above-ground biomass, but it's the exposure of soil organic matter, which wasn't exposed before, which now gets oxidized and releases CO2. That release rate is more variable, but the current estimate is about 2 billion tons of carbon a year. So the total release rate is about 10 billion tons of carbon a year. And as I said, about 60% of it shows up in the atmosphere, and the remaining part of it is taken up by oceans, and I'll tell you more, and other biosphere. Now let's go a little bit closer to policy in the world. This is obviously a historical set of data with projections past 2008 into the future. And it's from a couple of other people have used this particular database. It's the United States Department of Energy Information Agency, which is a semi-independent part of the government. And they're very reliable. They've done good work over the years. We know what a few of the errors in their database are, but they're pretty good. I apologize for the units, but Jim and I have talked about this. I maintain talking to the general public. BTUs are easier. He says zetajoules are. But these are not scientific units. That's why I have to apologize. These are British thermal units. But that's what the U.S. Department of Energy uses. So in 1970, the worldwide usage of energy in all forms was 207 quadrillion BTUs. And that figure doubled by about 2002, about 32 years later, to be about 415. The current usage is 463. And you'll see the color parts of the bar, which begin to get into an interesting story. The blue part of the curve used to be dominant. And as we've gotten up to the present time, the red part of the curve, which represents carbon dioxide emission from emerging markets and developing countries, has become larger. And as we look into the future, and I think Jim may have used some similar figures today, the world energy consumption in the next 22 years, and 86% of this is due to fossil fuel, is projected to go up about another 2/3, with most of the growth occurring in developing and emerging markets, whereas the mature market economies like the United States and Canada, Western Europe, and Japan are projected to have a growth rate of maybe only 1% per year, taking into account continuing improvements in energy efficiency. Well, you begin to see where we are. The carbon dioxide that was emitted into the atmosphere in this period of time is still there, and it's almost all attributable to advanced countries, rich countries. As we move further into the future, their emission rates surpass those of advanced countries, but they can say, well, look, our per capita emissions are still much less than yours, and by the way, you've loaded up the atmosphere with this stuff that's going to survive for hundreds of years. So you can see why the international discussions on how to deal with this situation have been resulting in finger pointing. And somehow we're going to have to get beyond that. A couple people mentioned today the rate at which coal-fired power plants are being added, for example, in China. So these data are from the year 2006 from the U.S. EIA, once again, as reliable as we're going to get. There are a couple of international sources which are similar. And it showed that in the year 2003, we were pretty sure that the U.S. coal-fired power plant capacity was producing, or could produce, about 310 gigawatts of electricity instantaneously, and the China production was about 240, and so forth. The year 2010, it was projected that China would have increased by almost 50%, and the U.S. by about 3%. And then continuing to the year 2030, the Chinese number would be roughly triple what it was in 2003, and the U.S. would have gone up about 50%. But when I was putting these numbers together, I realized that something was wrong, because the growth rate in China in the last few years didn't seem to be caught. So indeed, these numbers have now been changed by the U.S. DOE's EIA just in the last month or so. These are now the updated figures for China for the year 2008. And we know that they're still not satisfying all their demand for electricity, because There are credible reports of factories having to close for lack of electricity and not enough coal miners and everything else. So a lot of today has been spent acquainting us all with the dimensions of the problem, and when I close about what we can do, I think that's still an important part of what we're doing. Well, this is another cartoon, but it embodies what's needed to manage, if we're really concerned about the carbon dioxide carbon constraint. This portrays fairly graphically what's going on instead of writing differential equations. We have a bathtub representing the carbon dioxide loading of the atmosphere with an input being and here it says 7.2 billion tons per year, and I've already showed you that today's fossil fuel burning is already up to 8, and if you include deforestation, it's 10. So call it 8 to 10. Whereas the drain has been measured pretty well to be a capacity of about 3 billion tons a year. It's been measured by field experiments, by isotopic tracers showing carbon dioxide uptake in the ocean, by soil carbon balances, by increase in vegetation in mid-latitudes. So tropical deforestation releases CO2. The CO2 is fertilizing the biosphere in the northern mid-latitudes where carbon is being accumulated. Hands a little bit because it's not that clear, but soil carbon balances and isotopic data keep coming up with these numbers, that the natural uptake capability of the oceans and the biota are about 3 billion tons a year. So we have a system that's out of balance by 4 or 5 billion tons a year. So that you might hear someone say, well, we want to stabilize the amount of carbon dioxide in the atmosphere. All we have to do is hold emissions constant. No. Emissions have to be trimmed by 60 or 70% to hold the carbon dioxide amount in the atmosphere constant. So this is another fact that we're dealing with. Now, what is a dangerous level? There are international agreements signed by President Bush 41 that committed all the nations of the world to take actions necessary to prevent the accumulation of dangerous levels of greenhouse gases, but they didn't define dangerous. Now, Jim gave us one operational definition of dangerous today by talking about an irreversibility of change like sea level. Another kind of irreversibility might be represented by loss of biodiversity. Things that are truly irreversible, I think, qualify as dangerous. But the fact is, neither we nor the general public have done a good job of defining dangerous. And in this bathtub cartoon, the Japanese defined it as a level of carbon dioxide in the 400s because they were also taking into account the radiative forcing due to other greenhouse gases, which would mean that the equivalent carbon dioxide was probably around 700 parts per million. Okay, you've heard a lot of numbers today about the challenge of scale. If we truly wanted to reduce our emissions of carbon dioxide in terms of carbon into the atmosphere by of order 5 billion tons a year or 10 billion tons a year, because you heard Nate Lewis's rendition of the energy growth rates growing to an equivalent of a dozen or 14 terawatts. Some of you may have seen these so-called carbon wedges that Steve Pacala and Rob Sokolow prepared a couple of years ago. I'm going to now describe what a 1 gigaton carbon wedge looks like. So the target that they adopted would be reducing emissions about 7 billion tons a year, and avoiding just 1 billion tons a year would require that the energy use in every building on Earth would have to be cut 20 to 25%. Now, each of us is familiar with some energy savings in buildings on our campuses or our companies. We would have to do that 20 or 25% saving in every building on Earth to save the emission of 1 billion tons of carbon a year. Or we could increase the fuel economy of a fleet of 2 billion cars from 30 miles a gallon to 60 miles a gallon. That also will save 1 billion tons of carbon a year. And there are many other examples. If indeed we had some way to capture and store the carbon emitted from just 800 gigawatt coal-burning power plants, that would save 1 billion tons of carbon a year. And these wedges go on. They're really quite good at illustrating, and I won't go through them here. This is another example of the challenge of scale that we're facing. You can look at it in terms of energy sources to be replaced, energy efficiency to be gained, or whatever. Now, so far I've been talking as if climate is the only constraint. It is not. And if one of you were the President of the United States or Prime Minister of a leading country or the King, you would have to look at some other constraints. For example, national and international security. There are different ways to define security, but one of them is access to energy that you control somehow in your national borders. Jingoistic phrase of energy independence, maybe. But clearly, in a practical sense, the United States coal reserves, the Chinese coal supply, the India coal supply, the supplies in South Africa are attractive for each of those countries to use, and I think it's very, very unlikely, unless, Dan, you're awfully successful quickly, that people are going to quit using coal. They're going, but whatever it is, and what would appeal to a domestic source of renewable energy, as both of you talked about this afternoon, is that it's domestic. It's one measure of national security to have control over a domestic source. Then, of course, there are international security implications of what happens to the money that people spend on imported oil and what the money gets used for. So security is a broad word, and if you were in charge, if you individually were in charge of this, you would have to take this constraint into account. It's not just climate. There are financial costs, and we all know the personal financial costs of energy, the institutional costs of hospitals and universities, cities and nations, and of course of developing countries. The development of poor countries is going to be retarded by high energy costs. So if your agenda happens to be trying to help the poor people of the world develop, this constraint is also important. There's environmental constraints, and by this I do not mean climate. I mean the kind of traditional environmental issues of scraping off mountainsides to mine coal, or spending zillions of gallons of water to fracture shale to get oil, or mercury emissions, or nitrogen oxide emissions, or sulfur dioxide emissions from fossil fuel burning. So there are many other environmental constraints, including black carbon. There is, of course, the climate constraint that we've talked about a lot today. And then if you happen to favor nuclear sources, there are the continuing concerns about the safety of operation, which many people think is not that difficult. But certainly the issues of waste, everything from the sociological and political through to the physical and containment, and now, of course, the heightened concerns about proliferation, especially if we go to not a one-pass cycle for uranium, recognizing what Nate said, that the uranium supply can become limiting if we only use a once-through pass on uranium instead of recycling. If we recycle, then we have higher danger waste, although less of them. Okay, so with all of these multiple goals in place, if we take all of these constraints seriously, and not just the climate constraint, let's just put a couple of sample goals up. If your goal is to assure energy supply, then the preferred pathway might be the use of domestic coal, or wind and solar, which, as Jim Anderson pointed out today, the U.S. is particularly fortunate. Non-agricultural biofuels, as in Brazil's case, where sugarcane is an agricultural crop, but they've been able to extract biofuels from it successfully without displacing necessary agriculture. Nuclear power, drilling question mark, because it's very, very unlikely to assure an energy supply. And efficiency with an exclamation mark. If instead your goal for energy policy is to reduce carbon dioxide emissions, both to mitigate climate change and to slow down the acidification of the world's oceans, then you end up with somewhat different energy choices. Renewable sources look like a winner if you can satisfy the challenge of scale and do it quickly enough. Nuclear power looks like a winner. It brings carbon capture and sequestration onto the table. If it weren't for the carbon constraint, I don't think anybody would be talking about carbon capture and sequestration. In fact, people who think that this is going to be very difficult still have to admit that it is a worthy and necessary goal if you take this constraint seriously about carbon dioxide. And then efficiency is a winner again. Well, there are two other strategic challenges which we've glossed over a little bit today, although everybody understands them, that having renewable sources of electricity, for example, don't help us with today's transportation fleet that is based on the internal combustion engine with liquid hydrocarbons. And there's an advantage to liquid hydrocarbons, namely that you don't have to carry the oxidizer with you, so that you get about half of the mass that's necessary for the combustion for free out of the air. So the point is, when you look at today's situation, and for the perhaps next 10 years or so, until and unless there can be an electric drive fleet, reducing oil used for transportation is a strategic challenge. And similarly, reducing the carbon dioxide emissions from coal-fired power plants is a strategic challenge, given the likelihood that we're going to continue to use coal. So these kinds of observations, which are easy for us, as you learn anything about energy, are more difficult for politicians. And it's not because they're dumb. It's because they're not specialized. They're dealing with 100 issues at once, and they want to believe that there's a simple, easy, maybe not easy, but simple solution. Do one thing and do it well, and we'll solve all the problem. And they have to be reminded. For example, one of the presidential candidates is talking about solving our energy problem by building 45 nuclear power plants. Well, you might get enough electricity that way, but with our current transportation fleet, it's not going to help the internal combustion-driven cars that we have on the road for the next 10 or 15 years. So there are transition steps here also. Energy efficiency, though, for the life of me, I don't see why we haven't been able to do more with energy efficiency. And here I distinguish not conservation. Conservation is when each of us saves energy out of our own goodwill and eagerness to save money. Efficiency is more a technology matter. But it's a win-win situation, because increased energy efficiency would satisfy so many of these goals. It would decrease our dependence on foreign supplies, and this is true for any nation, not just the United States. Improve not only national security, but international security. It would decrease our trade deficit, which at about $75 a barrel, I think our trade deficit just on oil alone is about $350 billion a year. It would decrease local air pollution. It would increase national competitiveness. It would encourage the development of new products, just high-efficiency products. It would decrease household energy costs, and it would also slow down the increases of carbon dioxide and methane. So why aren't we doing more with energy efficiency? The answer seems to be that there are barriers between people who need it and people who can supply it. For example, business owners who can see the bottom lines that people like the McKinsey consultants have given them on how much money they can save on energy, but they don't have the technical staff. They don't know what the capital costs would be. So we need more energy service providers to fill these niches, to bring existing technologies into place, to make the kinds of connections that, Dan, you were alluding to with the visits you've had from companies who have technologies that won't work without some other piece in place. However, I want to give you a couple of examples of just how much science and technology can do, even without a lot of political and business cooperation. These are some measures of the traditional air pollutants that Kim mentioned this morning, that particulate matter, especially its chemical composition, has not been used as a measure of air pollutants because nobody's been able to measure it well enough. We have data like this going back 30 years on ozone levels. This happens to be Southern California, carbon monoxide, some particulate matter. And then in the red curves are vehicle mile traveled. This is a 20-year difference now in Southern California, showing that vehicle miles traveled per day or per year went up almost 60% in this 20-year period. The population went up nearly 40%, and yet these measures of air pollution were decreased. 40-some% for ozone, 50% for carbon monoxide, even though they didn't adopt Don Stedman's beautiful ideas. The measures of ozone, much more specific kinds of measures of ozone pollution, the data go back 30 or 40 years. that most measures of air pollution have increased, even though human behavior has gotten worse, with, say, 400% increases in vehicle mile traveled. How did this happen? It happened due to better formulation of fuels, cleaner fuels, better automobile engines, better machining, and emission control devices, all of which was science and technology. People didn't change their behavior. In fact, they're driving more vehicle miles in higher powered vehicles as well, but with less air pollution. And this came from science, this improvement came from science and technology. It didn't come from human behavior. So while we definitely need improved cooperation, better governance, better incentives for business, better tax policies, better ideas at the local level on how to incentivize homes to be built with insulation in them rather than having the builder in the position of building a house without insulation because it's cheaper than passing on a poorly insulated house to a customer who wants a house at a lower price. We have to intervene at local levels too. All of that is needed. But in the meantime, I think our biggest gains are going to continue to be from science and technology. So what is it that we should be doing? Well, today's a good example of educating ourselves and doing what half of the people here do, and that's educate students. Because many of the issues we're facing are going to be long-term, and it's going to take an enormous public resolve, and it's going to have to be led by the educated public, whether they be business leaders, whether they be non-government organizations, private individuals. Education is a huge part. But strictly from a scientific point of view, we have to identify and analyze options. Now, scientists have been pretty good at identifying and quantifying problems. I'm skipping over that, like the whole carbon cycle, one in climate change. But scientists have to identify and analyze options. The kind of thing that Nate did earlier today, showing the different energy pathways and what you can possibly get out of optimum application of various technologies. We have to create realistic options. We have to compare them quantitatively, and we have to do a much better job of communicating with leaders and the general public. This is not just feel good. Every one of these actions is going to have to happen. Certainly, the kind of energy research that has been discussed today from renewable fuels and then carbon capture and sequestration, a lot of fundamental biology can still bring about, and things that are in sight, from genetic modification of crops and other non-food crops to get liquid biofuels much more efficiently. A lot of nuclear issues, energy storage, I guess that was Dan's one word, and then many more challenges. So we have a huge agenda. I'm not going to talk in detail about what's going on now, but I would say in Congress there is more awareness than I've ever seen in my lifetime over the energy challenges driven by all of these goals: energy security, costs, and the climate change. There is also a lot more awareness than I've ever seen before of the fact that there's no silver bullet. It would be delightful if one particular technology in renewable energy can satisfy all the needs. But even if it can in the long run, we still have the minor problems of converting our transportation fleets off of internal combustion engine. So the good news is there's more awareness than ever before. I think people have felt the threats, and there are enormous business incentives, absolutely enormous. I think the real reason that person was sitting in your office that morning, Dan, is not that she thought that you were a star and she wanted your autograph. She saw some opportunities, right?
I gave her my autograph.
Okay, good. Well, you're especially kind. How can we bring this all together? I don't know, but I do really believe that scientists and engineers are going to have to guide the formation of all of these options, to quantify them, to figure out the inadvertent side effects, including things like geoengineering, and at every stage guide policy development of businesses and government. And I think we're going to have to do it every month and every year. It's not going to be something that happens in Congress every 2 or 4 years. It's going to be continuous. It's just an enormous challenge. I myself was staggered with some of the numbers I heard today because as familiar as I am with the scale, I heard different ways of depicting the numbers which were just mind-blowing. So let me stop here and thank you again.
We have time for a couple of questions if anybody has any. Jim?
You can't not ask questions.
Yes, you can.
Yeah, Ralph, I think one point that we should make here to keep things optimistic at the end of the day is to recognize the fact that this issue is no longer a Republican-Democrat issue. This is an issue of coherent national security, fiscal policy, foreign policy, energy policy. And there's a tremendous amount of motivation now to solve these, which are all solved in largely the same way. You picked out conservation as one of them, but this really applies across all aspects. And I think it's an issue now that there's a great deal of hope for, because it isn't this issue that divides the House. And I think this is going to be a very important point. The other issue that I would like you to comment on is the non-existence of a federal program to both study energy and to study the climate. I mean, it's a little bit like one of these Western storefronts. You know, it looks beautiful from the front. You look around the back, and there are dead chickens and dust blowing around, and it's a non-existent, pathetic treatment of a very serious problem in both energy and climate.
Well, I agree. There's probably less partisanship now than there was a couple of years ago. But there's still some questions which are going to tend to divide on political grounds. For example, the introduction of new energy technologies. We're still in a position where a lot of the oil in the world is controlled by companies whose extraction cost is a small fraction of what they can sell it for. So they can lower the price on oil at will. In fact, some of us were talking about Vinod Khosla. Some of you know him from California. He's one of the very, very bright venture capitalists. He was a partner in Kleiner Perkins, who's working on liquid biofuels and supporting research in genetics and molecular biology. And he was personally told by leaders in Saudi Arabia that they could wipe out his investments anytime they wanted by lowering the price of oil. Now, why do I say that? Because I think that's a fact, and that a lot of other people are going to have to be convinced that the market alone will not solve these problems. It's going to require some government action, and we've seen any number of corporate leaders asking for the federal government to set rules. For example, a price on carbon. There are many technologies right now, all of them are uncompetitive with carbon as a source of electricity. Coal. So unless some kind of a floor is placed on the price of oil imports, or some kind of an extra price is put on carbon, most technologies are not going to be competitive with coal as a source of energy. And that begins to get you into an ideological issue that some people say that that's not an appropriate role for government. So I agree with you, it's getting better, but there's still going to be battles.
Thank you for the comment, Ralph. I just wanted to point it out that when you put liquid fuels in your car, you put about a full tank is about 50 pounds of gasoline. That gives you a license to burn 750 pounds of air, which you didn't have to pay for and you didn't have to carry along. Liquid fuels are amazingly advantageous for transportation purposes.
That's true.
Just a very quick question. Since it is the political season, and you mentioned that hopefully we're going to be bipartisan about solving the problem, I think it was in the first debate when the two candidates were asked, do you think we're going to solve some of these problems because the government is going to invest something? Let's use the Sputnik era challenge that we had a few years ago, or is it going to be a garage door industry where entrepreneurial effects are going to have to take over? We'll put you on the spot about candidates, but just your perception on how we're going to get it done.
I honestly think that both approaches are needed, because although the prevailing view right now is that we have a series of challenges across the board that are really quite practical, there's still that possibility that someone's going to come up with a great new idea, and I think we have to invest in all of it, because as everyone showed the numbers today, we're not going to get home free here unless we exploit basically every possibility we have, unless there is some fantastic breakthrough in renewable electricity and storage. And you know what Dan talked about, a complete revolution where everybody converts their own energy or generates their own electricity. And we go away completely from the electricity distribution grid. It also means that the grid itself has to change, and that brings in thousands of practical problems. So I think an across-the-board full court press of increasing efficiency, of developing every technology, of placing a price on carbon, and of doing basic research. We're not going to get there because there are all these constraints. There's going to be a tremendous push to use our domestic coal, whether we like it or not.
We get one last question.
Okay, just very short. I like to also just point I like to blame ourselves. And for the simple reason, and I agree, we're going to need government intervention, but there are too many people in science saying, just take what we have and then use it, put some intervention in so it will get adopted. And what I will say is we spend a lot of time giving the numbers, but we aren't doing our job well enough. You get something cheap, I guarantee you will not have to worry about any government intervention. There is so much money to be made. And so I just, in everything in my life, my finger always ends up pointing at myself. And I don't think our community has done a good enough job to make it cheap so people will use it. So we better get to work now.
Get to work.
Okay.
I want to say, first of all, thank you so much for all of the speakers, organizers, discussion leaders. This has been a really fabulous occasion. I think it exemplifies exactly the kind of thing that the Dreyfus Foundation really stands for. I'm glad that it's been possible for the foundation to play a role in helping to solve these problems. They are important. I think we've heard both the difficulty of the problems that we have to solve and some ways to begin to approach them, and I think that's a really good sign. So I'd like to say, following the meeting, there's a reception in the hall. Thank you all very much for coming.